Good morning, everybody. नीलवा मैडम कहाँ हैं? अच्छा हाँ आप हैं. ठीक ठीक. Let's start this session number 5, that is on fiber laser and terahertz spectroscopy. I request Dr. J. Padma Nilay to chair this session. Please switch करिए. Dr. J. Padma Nilay is an outstanding scientist at BRC Mumbai. Her research. Oh, sorry. She is SOH at BRC Mumbai. Her research interests include gas lasers, laser-assisted surface modifications, molecular laser isotope separation, fluorescence-based biosensors. The list of awards, some of them are listed here. She has US patent and more than 80 papers in international peer-reviewed journals. Over to you, madam.
Hello. Okay. A very good morning to you all and welcome to this fifth session of NLS 33. So the very first speaker that we have with us is Dr. V.R. Supradeepa from IISc Bangalore, and his research interests include high power laser sources, fiber and guided wave systems, nonlinear optics, optical metrology, and communications. So he has got many recognitions and awards to his credit. He has this Galino DiNardo Award, International Commission of Optics, Young Scientist Award INSA, Chair Fiber Lasers and XX Conference SPIE Photonics, and SCRB Technology Translation Award. So Dr. Supradeepa, welcome to this session, and we'll be glad to hear you. So I'll just tell you after 25 minutes, and then next 2 minutes you'll have to conclude.
Sure, yeah, I'll do that.
Thank you so much.
Hello everyone. Am I audible to everyone? Okay, great. Thank you very much for the introduction, and I'm very thankful for the organizers for calling me here. This is the third time I'm here at NLS, and it's always been a very nice experience. So I'm from the Indian Institute of Science, and what I'm going to talk about today is some of our work over the last decade or so in making fiber lasers for beam combining. So to put this in context, fiber lasers are very common now. So you can get very high power laser sources, but they are not, a lot of them are for industrial applications. But if you want to reach very high power levels, and by that I mean hundreds of kilowatts to what people believe would be a megawatt in some time, then you need to be able to make small modules of lasers, fiber lasers at lower powers, which can be beam combined, right? And what I'm going to talk about is basically this beam combining. What does that require? That would be the topic of my talk. But before that, just sort of a very basic perspective on fiber lasers. So you have lasers available in all of these near infrared regions. Ytterbium, of course, is dominating. But there are very wide spaces, and the technology that allows you to bridge, if you have a technology that allows you to bridge this region, then by harmonic generation or by difference frequency generation, you can have a continuously tunable laser source. And that is actually enabled by something called a Raman laser and supercontinuum laser. So that is one of our lab's big thrusts. But today, I'm primarily going to focus on the complementary aspect, which is how do you make these lasers just very high power? So that would be the focus of my talk. I'll try to put in a little bit of basic background for some of the students so that it doesn't become too dry. So what limits power scaling of a conventional laser? So this is basically an IPG module. So we have IPG representatives in the audience as well. It can go up to 10 kilowatt in one unit, right? In a way, the 10 kilowatt module is more akin to power combining because it uses tandem pumping, which is a slightly different technology from a monolithic laser. Individual laser modules can probably reach anywhere from 3 to 4 kilowatts or so reliably in a module. This number, the last time I was here, was more like 2. Now it is 4. I assume it will be a higher number the next time I'm here, right? But generally, we don't anticipate it to go well beyond 10 because that's where real problems happen, such as fiber just gets damaged beyond that, and that's a fundamental limit. So how do we go around it? How do we make very high power? How do we make a 100 kilowatt laser? So the answer is there are 2 tricks. One is coherent combining, and coherent combining is a very simple idea. So if I take a single beam and I hit a beam splitter, then it actually just branches out into 2 arms, right? And then if I do the opposite, of course, if I don't do anything, if I do it in the opposite direction, if I send 2 beams, it's going to have light in both the ports of the beam splitter. But if I can phase compensate the 2 beams in such a way that they constructively add in one arm and destructively in the other, then you get nice bright beams. And of course, you can imagine doing that over many, many channels using a large number of beam splitters in some form, right? Why does such a coherent beam combining system require narrow line width, basically? And the answer to that is because you want your, to phase compensate multiple sources with something that is reasonable and something that holds for a lot of time. The coherence length of these individual lasers need to be relatively long. If they're very short, like if it's a nanometer class laser of the type that people use for welding, for example, you cannot power combine it at all. It's basically no different from this tube light in the form of, there's really not going to be any interference-based benefits. So how is coherent combining done? There are 2 versions. You have a tiled aperture version where in the far field you will have a bright central lobe if you compensate it, and the other approach is to use diffractive optical elements and come in with different orders onto it. Similarly, you have wavelength combining, which is much simpler. It's basically the reverse of a spectrometer. We come in with very high power modules at different angles, and then out comes a very nice high power beam. Again, why does this require narrow line width sources to do spectral combining? See, the idea is I need to be able to take multiple laser modules, combine it into a single high power beam, and then beam it over a very long distance. So what happens is I want enough dispersion in the diffraction grating, for example, to combine multiple beams into a common beam. But if the line width of each laser is relatively high, then that, because of the grating itself, will then diffract in the far field. So I want high inter-channel dispersion, but very low intra-channel dispersion. And it turns out it naturally needs narrow line width. And for us, we are mainly module people. We are technology agnostic, so we like both coherent combining and wavelength combining. And it turns out that the performance requirements for these modules is very similar. So what is necessary in a power combinable fiber laser? You want kilowatt class output power, of course, higher the better. The line width needs to be very narrow. So something less than 10 gigahertz is ideal. That is 0.04 nanometer. And to put this in context, that's at least 2 orders of magnitude smaller than the line width of equivalent lasers used for industrial applications. Now, the beam quality has to be perfect, 1.1. And then, of course, there's all these weight, form factor, efficiency constraints, and so on. Now, it turns out when we have to build a laser of that form, then we'll have to read through all the chapters of the nonlinear optics textbook, because all of them, unfortunately, are problematic. But the one which is really nasty is called stimulated Brillouin scattering. So what exactly is stimulated Brillouin scattering? So whenever you have a high power laser source, but which is narrow line width, see, this SBS doesn't happen in broadband lasers. If it's narrow line width, then some noise-initiated backscatter is going to interfere, and because of electrostriction, you're going to have moving gratings that creates a nonlinear inelastic coupling. And after a while, as shown in the picture below, most of the light starts coming backward. And I'm sure we can all agree that if we are making a system finally for directed energy, or the fancy word for laser weapons, the direction has to be very correct, and light coming back is definitely not what we would like, right? So I'm sure many of you would be, okay, why don't I just increase the fiber size, because if I reduce the intensity, Brillouin scattering will go down. But unfortunately, there's another problem called modal instability, which is if I make the fibers bigger, my fiber laser fibers bigger, then they become a bit multimoded. And when they become multimoded, then you have this nonlinear coupling between modes. So I have this small video here. So as you can see, as the power in the laser increases, but you support more than one mode, then at some point it just breaks down into multiple modes. This is called modal instability, and it's a very hard problem to solve. The other term people use for it is stimulated thermal Rayleigh scattering. Okay? So this was the context in which we came into this work. So the first thing we had to do is firstly understand how SBS in amplifiers work and how is it different. But before that, I want to make sure that it's clarified here. When we say narrow line width, there are a lot of people, I'm sure there are quite a few people here in DAE who think of narrow line width as true single frequency, like kilohertz to hertz level line widths. That's not what I mean. When we say narrow line width, it's just narrow line width, narrow enough for beam combining. So of the order of gigahertz line width is what. So that does give us some benefit in reducing SBS. So what is done generally is we take, and for these narrow line width lasers, you don't need any intensity noise, right? So a laser diode is taken, it is a DFB laser, we phase modulate it to get a required bandwidth, the gigahertz level, and then this gets sent into our amplifiers. This does enhance the SBS threshold by this scaling factor related to the bandwidth. And the way we understand this is we broaden the line width, so the peak, the spectral peak power reduces, so automatically my Brillouin scattering also reduces. So how is that generally done? There are various ways. People use sinusoidal waveforms, but of course with discrete lines, you only get scaling as the number of lines. People use pseudo-random bit sequences, but you know, when we have to make these modules in very large volumes, having a PRBS generator with each module is just not a cost effective. So what we have identified is using a filtered noise source, which is basically just an amplifier with the input shorted, so that you just create noise, and then you send the noise into these phase modulators, and then you get this bandwidth, okay? So how does that really work? So I put in the noise to the phase modulator, and by increasing the amount of power, I can get tunable line width of the laser source. Now the problem is, all this was nice, but it turns out that Dr. Agarwal has this very nice nonlinear fiber optics book, which I'm assuming most of us have read. And then if you look at the SBS threshold after line broadening, that is a fixed formula, which is 1 plus delta F by the phonon bandwidth. But it turns out in these amplifiers, it becomes a length-dependent phenomenon. And that results in, and because amplifiers tend to be short lengths of gain fiber, you don't really get much enhancement at all by doing line broadening, and that is a real problem. And our first work was basically trying to understand why this happens. And it turns out that is primarily because whenever you think of a noisy process, a random process, there's a big difference between the power spectrum and the power spectral density, because the power spectral density is just the limit case of the power spectrum. That is what really causes SBS. And then when we model all of those things together, then we can really explain very well with a modified formula for SBS threshold in amplifiers. Okay, so this was something we started. But unfortunately, that was not the only problem. You get these spectral spikes in the spectrum in the amplifier, which can enhance SBS. And the third issue is that whenever I have an amplifier fiber, Brillouin scattering happens in the opposite direction. And if there is end facet reflections or Rayleigh scattering in the fiber, then it seeds the SBS process, which results in much faster growth of stimulated Brillouin scattering than, let's say, a conventional textbook model. And so we really need to model this. And so, and the reason why this happens is, of course, if it's true single frequency, Rayleigh scattering is an elastic phenomenon, so it doesn't matter. But these are line broadened systems. So as you can see here, as my line width increases, then there's more and more power that shows up in the Brillouin shifted band, which is roughly 16 gigahertz away from the peak of the spectrum. And that will then get fed back. And so your own signal is seeding itself in the Brillouin domain because of the line shape. So we really need to get it. So the way to understand this, of course, is we have to then solve the pump signal ASE equations, and then we have to have a Brillouin coupling equation where we need to include the Rayleigh terms, and then we have to have a population inversion. So there's quite a bit of coding that we ended up doing to critically understand Brillouin in these amplifiers. And turns out when we did the experiment, there was smoking and evidence where we artificially created the amplifier with a little bit of poorer end facet reflections using an angle cleave versus an AR coated delivery cable, and then we could see very different threshold differences between the AR coated cable versus the angle cleave. So which sort of tells us very clearly that reflections from end termination is very important, and that needs to be resolved. But even when we do it, there is still the effect of Rayleigh backscatter that just cannot be avoided. So to summarize, there is length dependent effects because of the statistical properties of the signal. There is spectral spiking that comes because of transient gain dynamics. And then there is Rayleigh scattering, which feeds SBS. And putting all these three things together, we have a very good model of what the SBS performance in these amplifiers are, which is very distinct from textbook models. And when I say very distinct, sometimes as big as 5 times. It's 5 times lower than what a textbook model would allow us. So with all this information, we started putting things together. And as I said, our first phase was making modules. So this is how a narrow line width optical module would look like. So I have a line broadened seed, which is a DFB with a phase modulator, then 2 chains of amplifiers. We start from milliwatt level and then go all the way to a kilowatt level. So that's basically how the system achieves. In our first set of development, we were able to do half a kilowatt at 10 gigahertz of line width, so 0.04 nanometer. And some of the key innovations this required us to do was the entire process. So if you look at only the power amplifier at the bottom right there, that alone is how your industrial class laser would look like. So it's a much simpler system than a narrow line width laser. So a good comparison is you want your commercial lasers to be like a Toyota Corolla, whereas a narrow line width laser is more like a Lamborghini. And that comparison is very accurate because I have been told that Lamborghinis are really nasty to drive also. It's just for the fun of it for very niche applications. And that is basically how these narrow line width lasers are. So we did transfer this technology to LASTEC back in 2018, but as we know, unfortunately, LASTEC got shut down. They got merged into a different lab. But around the same time, we built multiple of these units, and they're reliable enough that we could replicate it. And then they were shipped to Balaji Srinivasan at IIT Madras, who started using them in coherent combining experiments, which gave some very interesting results. So it was around this time that we really wanted to crank up our module development programs. But unfortunately, as you know, 2020 came, COVID hit us. But in a way, something which was not very nice for some of my students, but which turned out to be reasonably good for me, is I really had a confined audience confined group of students who are stuck in the university with nothing to do. No restaurants are open, they can't leave the campus, and suddenly, working in the lab seemed a lot more exciting to keep themselves busy. So we had this really productive time. So the question there is, okay, if the thresholds are being reduced because of BRIL1 getting seeded, why not just make my line shape like a brick wall, like a nice rectangle? But I'm sure most of you here realize that when I have a fixed structure like that, the Fourier transform of that will automatically have intensity noise, so it is not a very good system to use. So what we ended up doing is we had to implement it with phase modulation alone. How do I make a line shape like the green one purely with phase modulation? And turns out there's a very simple approach to that. You do a dual modulation with a sinusoid and a filter noise source, and by balancing the powers in the arms and getting the right signal parameters, you actually end up making your line shape very nice trapezium shapes with very sharp cutoffs in such a way that your SBS gain spectrum is completely offset. So this kind of solves the SBS seeding problem. So we were really excited, but we weren't sure how well this would do in our practical system, so we went ahead and took the same amplifier that we had before, which gave us 500 watts at 10 gigahertz, and then put this modulation in, and we were immediately getting a 2x improvement. So we had 1 kilowatt at 10 gigahertz until modal instability was seen. But what I have to point out here is this module that we developed was a narrow line width but polarization maintaining architecture as necessary for coherent beam combining, but a lot of applications like spectral beam combining doesn't require the polarization maintenance. Now, for such systems, this architecture should go around to give us at least 1.5 kilowatts of output power. But then, so I did go around talking about this quite a bit and said we are very happy about our 1.5 kilowatt amplifiers and so on. But I realized that there is a subtle negative aspect to being a bit confident about our systems, because very rapidly the way people heard it is, if it can potentially give 1.5 kilowatts, maybe we should just push with industries to make 2 kilowatt packaged rugged modules, right? So this program actually initiated from DRDO started in 2023, late 2023, where it directly became a development contract of sorts to make 2 kilowatt. But the thing is, it's very hard to make narrow line width modules even at 1.5 kilowatt based on a lot of these problems. And then this probably was one of the most challenging periods that I have faced. I have to point out here that even when we work with industry, only the optical modules are coming from us, but then there's a lot of additional aspects like the mechanical packaging, the cooling, the electronics, the control systems that either come from DRDO or from the industry's own internal development. So to put this work in context, our amplifiers look like that in our lab, tabletop, spaghetti wound, coated in heat paste and with fibers floating around and so on. But we had to go from that to something which was 2 times the output power, fully packaged in a rugged form factor, state of the art internationally. And more importantly, this would be the first time industries in India would even be attempting to make narrow line width laser modules. But things worked out well. So recently these 2 units were delivered. So we have one from BEL, which gave 2 kilowatt at 10 gigahertz in a rugged platform, and one from SFO Technologies from Cochin, which also gave 2 kilowatt at 10 gigahertz. In this context, I would like to thank Dr. Upadhyay here, along with Dr. Anjan Sen and Professor Balaji Srinivasan at IIT Madras, who were in the sort of the review process for this development, and some of the insights that we got was very useful in reaching this deliverable in this very tight timeline. So I'd like to sort of conclude my talk, and I think I'm doing reasonably well on time, to put this in context. So in 2018, we were able to make multiple of these modules as proof of concept for beam combining, then some research deliverables reaching a kilowatt or so in 2021. The red module there, and when I'm talking about narrow line width modules here, I'm talking about 10 gigahertz modules. So you can always scale the line width and get more power, but that automatically means that the number of channels you can beam combine will automatically reduce. So there is no benefit in scaling the line width and getting more power in terms of how the beam combining performance will be. So what really works is to preserve the line width as narrow as we can while only increasing the power. So at the 10 gigahertz level, the red bar, of course, I'm sure there are internal developments across the world which have better performance, but because of the sensitive nature of this technology. But this is the awareness that we have that the currently accessible modules are somewhere there, and now we have 2 kilowatt class 10 gigahertz modules, which easily should give us, with a properly designed beam combined system, something at the 100 kilowatt or so level. State of the art internationally, even on a tabletop, is still less than 3 kilowatts. So our goal is how do we overcome some of the problems here and continue with the module power scaling in the coming years. So there's a lot of very interesting nonlinear optics that we'll have to solve, but we are really hoping that the coming years are going to be very exciting. And with that, thank you very much for listening to me, and I'll be very happy to answer any questions.
Thank you. Thank you very much, Dr. Supradeepa, and thank you for finishing well on time.
Very happy to do that.
Yeah. So your targeted output is 100 kilowatt, you're saying?
No, we are only the module people. So we will just push towards higher and higher power modules.
So how many modules have been able to you have been able to combine? I mean the low power modules?
We are not doing the combining.
Okay.
The combining is currently being done in multiple places.
Okay.
So IIT Madras in Balaji Srinivasan's group, they look at coherent beam combining.
Okay.
Then BEL has demonstrated spectral beam combining.
Okay.
And then DRDO themselves have
so you
units.
have actually given the method of reducing this SBS
right. So
noise,
our
etc.
deliverable would be modules like this, which will go into a beam combined system.
Fine.
So these are the hardest to access because they're generally not available at these power levels. So the thing is, if we have a beam combined system which can give me 30 kilowatts by taking 30 1 kilowatt lasers, and if I switch them with the 2 kilowatt lasers, but also with reduced line width, so I can put in more channels, then I should be able to go to 100 kilowatt. Yeah. So, but it's a large development effort. So we are more in the early stages of making modules, and then there's a different set of people who do the combining.
Questions, please. Yeah.
Go ahead.
I have a question not exactly related to the topic, because we have a requirement of coherent beam combining for sub-100 Hertz lasers. Sub-100 Hertz.
Okay.
So the topic what you have covered is 10 gigahertz.
Correct.
So any solution of how to scale up the power and how to
Sub-100 hertz.
sub-100 Hertz.
Very narrow width.
Very narrow
Very
line.
Oh, that is a much easier problem. The line width, the smaller the line width, the longer the coherence length, so the easier the beam
SBS management.
See, of course, individual modules like this, something like this which achieves 2 kilowatt, for example, at 10 gigahertz, achieves roughly a 100 watt class laser in true single frequency. So whether it's 100 hertz or 50 megahertz, the SBS performance is the same because the SBS bandwidth is 50 megahertz. Now, of course, if you want kilowatt class of that, then you will have to make 10 of these and then coherent combine it. But that is easier because now the coherence lengths are much longer.
Agree. The SBS thresholds works out to be 105 watts for a typical 30 micrometer diameter fiber.
Right. This is not 30, this is actually a 2400 fiber. But
because we have this special requirement for LIGO.
Yes, I kind of assumed where you're coming from.
Okay, I think
can
you
have the
can
discussion
discuss
Sure,
during
sure.
tea time. Yeah, Dr. Upadhyay. Yeah.
So let me congratulate you and for developing these 2 kilowatt fiber lasers with narrow line width. And it is, I can say, it is the world's state of the art, and it is the world's first such kind of laser in the world. So it will be very useful for DRDO. And next thing is, I wanted to just know two things. One is, why can we control TMI in such fiber lasers? Because you said that up to 1 kilowatt you started getting TMI.
Correct.
And beyond that, how you reached that? And,
Right, right. So
next.
it turns out even TMI, for example, in our original work, we mainly were looking at the scaling. So we weren't really optimizing for TMI. It turns out when you go from a polarized to unpolarized architecture, even TMI scales by 2x, purely because now the modes are split into two orthogonal states. So you do get that benefit. And in addition, we had to optimize the coiling configurations quite a bit. But then the question you're asking is really fundamental, which is this scaling arbitrary? It turns out, unfortunately, not. At some point, we need to have bigger fibers, which will become multimoded, and so it will be very hard to control TMI. But then, simultaneously, there's a lot of interesting work going on in fiber design itself, in such a way that the fibers are selectively single mode because of varying structures in the cladding. So there's quite of interesting work there. So we are really hoping to lean on such people to give us the next generation fibers for these lasers.
Okay, thank you. Just one small query.
Sure.
Can we make these, because there are several oscillator, and then from seed we are amplifying several stages. So is it possible to have in a oscillator itself, about kilowatt, 2 kilowatt from the oscillator itself? Because that will make it very easy to work.
Right, so the conventional lasers are made like that, so you have a single oscillator. But I assume what you're asking is there a way of doing narrow line width from a single oscillator? That unfortunately is very hard. I mean, so what people do is in a fiber laser, in a cavity-based fiber laser, the intensity noise is unavoidable because of, it looks like a partially coherent source with some mode beating noise in a cavity. So intensity noise cannot be avoided. And when you have intensity noise, as you keep scaling power, then you have this curve-based cell phase modulation, cross phase modulation type line broadening, which actually results in the output line width being directly proportional to power. So it turns out that in such cavity lasers, even with 2400 type large fiber, it's very hard to do sub 1 nanometer line width, which is still 2 orders of magnitude wider than what we want. But I can imagine certain niche applications, and we have done this before, where we don't want 0.04, but we want something like 0.1, where I can do a frequency doubling in nonlinear materials to go to the visible wavelength, so go from 1064 to green at very high power. Then what we can do is we can take a cavity laser, we don't run it all the way to 100 watts or so, but we run it at say 10 watts when the line width is still relatively narrow, say 0.1 nanometer, then send it then through a MOPA backward pumped amplifier where you sort of, you play around, but it never really gets to this true narrow line width regime in a single oscillator configuration.
Thank you. Thank you.
Okay. Last question. Please make it short.
What is the best way to reduce the Rayleigh scattering for narrow line width amplification?
That unfortunately Rayleigh scattering is not, it's fundamentally there. It's very hard to get rid of it. So the Rayleigh scattering occurs in fibers because, you know, the way I visualize it is if you fly over an ocean, you know, the waves feel frozen in place, right? So it's just frozen like that. So when glasses solidify, that refractive index perturbations get frozen. And the only way, there are a lot of people, especially the transmission people, are really working very hard to reduce what they call this fictive temperature or something, so that you reduce Rayleigh scattering, but you're still talking about linear improvements, but not the kind of improvements that would be helpful to solve our seeding problem.
Okay, thank you.
Right?
So we shall thank Dr. Shupradeepa for a
Right.
very
Thank you very
wonderful
much.
presentation.
Thank you very much.
May I request Dr. Nilay to present a memento to Dr. Supradeepa?
So the next speaker in this session is Dr. Shyamal Mondal. He's from Defense Institute of Advanced Technology, Pune, and his research interests are ultra-fast fiber lasers, terahertz photoconductive antennas, engineered optical fiber sensors and optical nonlinearities. And he too has many scientific recognitions to his credit. And this is, I think, very recent National Science Day 2025 award by DRDO, awarded Rutherford International Postdoctoral Fellowship in 2017 and Postdoctoral Fellowship 2016 of ZEC Academy of Sciences. So with this, I invite Dr. Shyamal Mondal. 25 minutes, huh? And then I'll tell you. 2 more minutes after that.
So, a very good morning to all of you. I'm honored to be here, and I'd like to thank the organizers, especially RRCAT people and University, Medicap University. So, I'm here to discuss about the harnessing of nonlinearity of optical fibers for stable all fiber figure 8 mode-lock laser system. So I'm from DIAT, Defense Institute of Advanced Technology. It's an autonomous organization under DRDO, Ministry of Defense, and we are situated at Pune, in the southwest of Pune, in the bank of Kharakvasla Lake and opposite of NDA. So this is the outline of my talk. So we will discuss about the basics of ultrafast lasers, why ultrafast lasers are important nowadays, and what are the types of artificial saturable absorbers, and there are few artificial saturable absorbers I will discuss, among them that nonlinear optical loop mirror, nonlinear absorbing loop mirror based artificial absorber based YB doped fiber laser systems, dual stage amplification using double clad fiber, and the ongoing and future work that we are doing at Ultrafast Photonics Laboratory at DIAT. So why we need these fiber laser, and what is fiber laser? Before me, Dr. Supradeepa told about the CW fiber lasers, right? So we are at the extreme point. We are at the ultrafast regime, so where the time is very, very short and the spectrum is very broad. So a fiber laser which is having the active gain medium, like different rare earth medium, it can have like erbium, ytterbium, neodymium, thulium, holmium, etc. So there are different wavelengths are coming out when we are doping with different rare earth materials. So it can be useful for different application, for telecommunication, medicine, surgery, spectroscopy, imaging, and lot. It has a very small footprint and good electrical efficiency, low maintenance and low operating cost. So we can operate it in CW or in pulse mode. So in pulse, if we want to get a really very short pulse, so we have to do the mode locking, right? So in mode locking, there are different kinds of mode locking. So I'll discuss a little bit about that in the next slide. So we have to consider the pulse energy, pulse duration and repetition rate here. So let us discuss a little bit about the types, how we can get that ultra fast laser. So we know that in a laser we must have pump, gain medium and the feedback, right? So apart from that, we should have the mode locking mechanism and dispersion compensation mechanism inside the optical cavity to have the ultra fast laser. So in the cavity, we know that there are many longitudinal modes. So and all the modes are in random in phase. So when it is random in phase, we are getting the CW laser out from the cavity, and when we can lock the phases of those modes, longitudinal modes, we can able to get maybe the ultra short pulse. So we can say that weak pulses are suppressed by the mode locking mechanism, that is saturable absorber, and the strong pulses it can be shortened and it can be amplified to have some useful application. So after many round trips, even a weak saturable absorber can yield a very short pulses. So why ultra fast fiber laser? Because it gives us the flexibility, the adaptability to the environment. It reduces the thermal effect due to the large surface to volume ratio. It can produce the diffraction limited beam quality due to the wave guidance nature of the optical fiber and the compactness form factor as we can coil these kind of fibers, and it is reliable and easy to maintain and turnkey operation. So that is why people are now very keen to go towards the ultra fast fiber laser if you compare with its bulk counterparts. So there are important parameters, right? There are different attenuation losses, different kind of fiber losses. Here my previous speaker, he has discussed about the Rayleigh scattering or other kind of scattering inside the optical fiber, the inhomogeneity the optical fiber that can give you the losses, the dispersion, different like second order and third order dispersion, the nonlinear effects, self-phase modulation, self-amplitude modulation, stimulated Brillouin scattering, stimulated Raman scattering. All these we have to balance each other to get the ultra short pulses. So there are two cavities I am showing here with real saturable absorbers, right? So one is that linear cavity. In one side we can have the CFBG, charp fiber bracketing, that can act like a mirror and filter spectral filtering inside the cavity, and in the other side we can have different like topological insulator based mirrors or nonlinear loop mirror or TISA mirror. So this kind of saturable absorber we can include to have the mode locking. So this is a ring cavity where we can use this kind of real saturable absorber and we can get the mode locking. So now in our case we have chosen ytterbium doped gain fiber. So why ytterbium? Because it can give you very huge amplification, the people have achieved up to 10 gigawatt peak power by using the charp pulse amplification method, and it always give you the option to amplify in free space if we are working with in tandem with YB KGW, YB YAG, YB glass, YB YBO4, these kind of crystals. You can amplify further in the bulk crystals, bulk gain crystals, and recently in that YB doped YBO4 crystal are gaining a lot of interest because of some key advantages offered by YB3 plus ions, such as low quantum defects, high efficiency, and energy conversion, high efficiency in energy conversion, long fluorescence lifetime, and emission at around 1 micron. So it can be used with Tysafer laser amplifiers as well, regen and multipass amplifiers. It has a very low defect, low quantum defect for the ease of thermal management of these laser systems, and it allows us to reach the hundreds of watts average power in ultra short regime. So that's why maybe YB is very, very useful for different applications. So saturable absorbers, as I told earlier, that it can have the real part, a real saturable absorber, like material based saturable absorber and artificial saturable absorber. So the key, it is a key component in the ultrafast laser, and it has particular light absorption that decreases with high optical intensity. The real saturable absorber depends on the material property to achieve the saturable absorption, while the artificial saturable absorber depends on the nonlinear effects that taking place inside the fiber. So the saturable absorber employed in phase mode locking for the longitudinal modes in the laser cavity. You can see there is a classification of the saturable absorbers, the artificial saturable absorber and real saturable absorber. Artificial saturable absorber can be exploited based on the spectral effect, based on the spatial effect, or based on the polarization effect, or based on the reflection effect. So we are working on the reflection effect of the artificial saturable absorber. There are again a few divisions. You can say that nonlinear optical loop mirror, nonlinear amplifying loop mirror, nonlinear absorbing loop mirror. So these kind of things are very, very rugged, and the fibers, that inherent nonlinearity, that we can utilize those things, and we can get the we can get the lasing output, ultrafast lasing output. So you can see that these nonlinear dependencies of their transmission that gives us the artificial saturable absorber mode locking. So what is nonlinear optical loop mirror? Let us discuss. This is actually made of a coupler with a maybe length of fibers. Okay, so this exploits the nonlinearity. So this exploits the nonlinearity on optical fiber and gives us the nonlinear phase induced self phase modulation. So where we don't need any interferometric alignment, and it is very simple to construct and robust mechanism. The single input is split into two counter propagating waves, two counter propagating fields that remerge at the coupler and give you the intensity modulation. So the optical route that travel at each is same, and by orientation are obviously opposing and allowing them allowing for separate nonlinear effects to occur the two counter propagating paths. So if we choose the 50-50 coupler here, we'll get very less or negligible mode locked output because of its destructive interference at this port, at this output port. So for this NOLM, nonlinear optical loop mirror, we have to choose that output coupling ratio which is not equal to 0.5. So it is, the relation is like this, the that length, nonlinear length, and this N2 is the refractive index, that nonlinear refractive index, and this I is the intensity. So we are incurring the phase, nonlinear phase shift here, and this N2 is the car nonlinearity, as I told earlier. So what is happening here? Here two counter propagating waves, that is E3 and E4, are coming here in the coupler, and we are actually getting the output from here, that is E2 square. So the E2 square is the intensity part of this electric field, and we are getting the nonlinear phase shift at this port, nonlinear phase shift and nonlinear cell phase modulation at this port. Due to that, mode locking is happening. So a nonlinear device based, this is another thing. Earlier there was no, only the simple fiber that in that loop. So instead of that, we can use another gain fiber in that loop to amplify or to absorb the, to amplify. So how it is amplifying? We are actually coupled with a WDM coupler, and we are pumping here, and this can pump here again. So to overcome the loss that is happening inside this figure of 8 laser, so we can overcome this by the amplifying loop mirror. But the problem is, in the nonlinear amplifying loop mirror, it actually enhances the noises inside the optical cavity, and ultimately it can destabilize the output, laser output, what we are getting. So instead of that, if we can use an absorber here. So absorber is nothing but a piece of gain fiber inside. So we can get a fiber absorber inside the amplifier, and it actually equals with the power of 2 counter propagating waves when they meet at the coupler. The fiber absorption is independent of the direction here. Either it is coming in the clockwise or counterclockwise. Okay, so while this is interfering, the power can be shifted to the output port with NOLM and NALM as it is happening earlier. So we are getting a peak power which is 2 pi divided by 1 minus beta into gamma into L. So gamma is that nonlinear coefficient, and peak power is A gamma divided by 1 minus beta into N2 into length of the fiber. So from here we are getting the NALM output, NABLM output. So if we change the coupling ratio, so the coupling ratio here it is 15%, here it is 45%. We can see the depth of modulation, it is also changing. The transmittivity inside the fiber, it is also changing. So the close coupling ratio, if we are having a close coupling ratio of 0.5, the greater would be the difference between the maximum and minimum power. A large ratio could help in accumulating the nonlinear phase shift more and adverse effect with the nonlinear depth modulation depth. So the initial transmission is higher for larger splitting ratio, and the switching happen between the saturable absorber and reverse saturable absorption for the increasing input pump power. So now there is another point I have to mention, that why we are using the PM fiber and the double clad fiber. So here our fiber lasers are double clad fiber based fiber cavity. So PM fiber leads to the environmental stability against the thermal and mechanical perturbation, and it is very useful for the outdoor applications. And the PM YB doped fiber laser cavity was first reported in 2013 by Aguirre and his research group. It is giving the efficient pump coupling in double clad fiber. Generally we know that in double clad fiber we need a longer fiber length, but slowly it is getting absorbed if we are put the pump in the cladding. So slowly it is getting absorbed in the core, and it is giving you the uniform pumping. So the double clad fiber in PM YB doped fiber cavity generates a high pulse energy from the cavity itself, and it is first reported by Borodkin et al. In 2021. So you see that this kind of panda fiber we are using in our cavity, and this double clad fiber for the gain fiber we are using double clad gain fiber. So this is a figure of 8 cavity where in one loop we are giving the employing the fiber gain fiber YDF DC double clad, and we are coupling with the pump signal combiner and a 2-pin laser diode that we are using for this pumping. And this other loop we have varied the loop length to optimize it, we have got some interesting results out of that. So we are getting the tunability of around 30 nanometer with respect to the input pump power, as we have not used any filter, fiber filter inside the cavity, and the repetition rate is around 12 megahertz, and the achieved stable pulse with it is around greater than 70 dB. So if you see at the different time scale, so the millisecond, nanosecond, microsecond and millisecond time scale, the whatever the pulse stability, it is very, very stable, and the signal to noise ratio, it is almost or more than 75 dB. And this is the spectral characteristics. If we measure the spectrum, this is the pump, unabsorbed pump at the output, and we are getting the tunability from let's say from 1070 nanometer to 1040, 1039 nanometer. So we are getting the tunability with respect to the pump power. So there is no report of this kind of tunable wavelength output from the artificial sexual absorbed mode locked pulse laser cavities till now. So if we can see the when we are changing the loop length, nonlinear loop length, we are getting, so we have varied it from 7 meter to 10 meter, then 11.5 meter, and we gone up to 50 meter. We can see that the spectrum is getting narrower, and it is actually attenuating the signal. So, and this is the central wavelength that is varying with the input pump power, we can see here. So in the previous works, in the nonlinear absorbing loop mirror, it has started in 2021 or 2020, you can say, with holmium, ytterbium and thulium fibers. They are getting in ytterbium, the repetition rate they have achieved around 24 megahertz, and the central wavelength is around 1063 nanometer, and the bandwidth, spectral bandwidth, it is 20 nanometer, and the pulse duration, they have achieved about 124 femtosecond. So we have also started working in this domain, and this is our achieved results. So we have used an absorbed this in that nonlinear loop mirror side, we have used this fiber, gain fiber of about 8.5 meter, and this is the loop, in that loop length, the gain fiber is 1.5 meter. So the threshold pump power, we can see the threshold pump power, it is actually coming down when we are using this nonlinear absorbing loop mirror. It is coming down from 799 milliwatt to the 570 milliwatt. And this multipulsing also, it is when we are increasing the pump power, we have observed the multipulsing in the NOLM at about 1.7 watt, but here it is very less. That multipulsing is not actually achieving in nonlinear absorbing loop mirror. So these are the results of nonlinear absorbing loop mirror based laser cavity. So we have achieved that the periodicity, it is around 88 nanosecond, which gives us around 11.35 megahertz and around 70 dB of SNR, and the spectral bandwidth which we have achieved, it is 5.89 nanometer, and these are the different time scale, and this is the tunability. So we can see that with the input pump power, we are getting the maybe a sinusoidal tunability here. So if we see the variation of nonlinear loop length, the results of nonlinear loop length, so we can see that with CSAM, the people have achieved the threshold mode locking about 190 milliwatt. But our threshold power is quite high, as we have not used any spectral there is no component of the filter, fiber filter for spectral cutting of this, and there are in NABLM. Okay, so the nonlinear absorbic loop mirror, what we have used, the spectral bandwidth, it is coming around 6 nanometer, and the threshold pump power, it is quite low with respect to the NOLM that we have studied earlier. It is 558 milliwatt in the with the 2-pin laser diode what we have used with the double clad fiber, and the bandwidth limited pulse width, it is about 196 femtosecond. So after that we have done the dual stage amplification with the double clad fiber. So in this architecture, and these are the results of dual stage double clad fiber amplification. So we have achieved more than 1 watt of output power from this, and the pulse duration, it is a normal dispersion cavity. So the pulse duration that we got, it is around 29 picosecond. So and if we compress it, if we can compress it, this pulse, it can go around 200 femtosecond. So that we have calculated according to the GVT in our laser cavity. So these are the ongoing and future work that we are doing. So we are actually making this high power ultra fast fiber laser at a different wavelength regime, and that UFL assisted compact terahertz spectroscopic system and novel broadband terahertz sources and detectors that we are making in our lab. And this UFL based pump probe spectroscopic system, we need that supercontinuum generation and supercontinuum laser for the spectral broadening and compressing of the pulse far into the maybe the hundreds of less than 100 femtosecond. So we need that supercontinuum sources and UFL for RF photonics applications, and this MOPA system for DW applications, and fiber based pulse compression systems for ultra fast fiber laser. So, and we are also working with engineered optical fiber for making sensors for physical, chemical and biological applications. So this is the ultra fast photonics lab at DIIT, and we are actually having this glass processing system. With that we are doing this tapering and this ball lensing and different things. So this one product we have made with this Ytterbium dot fiber laser system, and this is one small video. Sound. Okay, so this is the oscillator and the fast stage amplifier, and we are pumping with 2-pin laser diodes here. This is another.
After the first amplifier, it is followed by the second amplifier over here. We can see that fluorescence in each case where the gain fiber is present, starting from oscillator followed by the 2 amplifiers. Altogether the power is boosted up to more than 1 watt, and the output is at 1060 nanometer regime. If you see the pulse train in the oscilloscope, right now this is in 1 nanosecond time scale. Right now I'm changing the time scale into a couple of tens and hundreds of nanosecond, even into microseconds, and you can see that the pulse train is very stable. Right now it is at 2 microseconds per division. The repetition rate of our laser system is 13.2 megahertz. The signal to noise ratio of this particular laser system is more than 70 dB. This is the layout of our all polarization
Dr.
maintained Ytterbium dot fiber
Dr.
laser.
Mandal.
And we can see over here, this is the first stage.
Yes.
Hello, just finish?
Yeah, almost. So
Just 1 minute then, please conclude.
So we have showcased this kind of laser system in that PLAIM, the industry academia meet during LWOP, Laser World of Photonics 2024, Geo World Mumbai, and these are some publications in the recent year 2024 and 2025. And I should acknowledge our DIT Vice Chancellor and the present and previous students and colleagues from DIT and my collaborators and funding agencies like DIT, Grantinet and this UGC and DRDO. So these are my lab members, my students, and thank you for your kind attention.
Thank
So
you
I'll be
very
happy
much.
to take any questions.
Thank you very much,
Yeah,
Dr. Mandal,
thank you.
for your nice presentation. Just one thing, you have this absorber in the propagating and counter-propagating way.
Yes.
What kind of absorber is this? Is
So
it again a
it is
saturable
nothing
absorber?
but the same fiber that we are
Huh.
using for the giving the gain in the main loop. So
Okay.
the same double clad fiber we have used for this absorption.
And how do you decide the length of that fiber?
So
that absorber as an absorber?
Yeah, so that we have seen that how much length it is required according to the residual pump that we have inside the fiber, and how much length we have actually optimized, and the simulation also we have done regarding that. There are different noises are there. We know that in the cavity it is a random process, so the different noises. So we have optimized that length accordingly by the simulation as well as through the experiment.
Experimentation.
Yes.
Okay, any questions, please?
Yes.
You have shown in the NOLM based mode locked oscillator that it gives about 30 nanometer tunability.
Yeah, 25 to 30 nanometer
Okay.
tunability.
So it is just, you have shown in the results, it is by just increasing the pumping strength, you get different wavelength outputs from the laser.
Exactly.
Are you doing any extra effort to control it, or it is just governed by the NOLM mechanism itself?
It is governed by the NOLM mechanism itself inside the cavity. We don't have that fiber filter earlier, so we have just made our cavity like this. So I believe that if we can use that fiber filter inside the cavity, it will be much stable also, and it will give you the wavelength that you want.
Yeah.
Your desired wavelength.
Fiber filter basically will restrict the
Wavelength.
output wavelength, whatever you want.
Exactly. So
Okay.
that wavelength only it will get the gain inside the cavity.
Another thing I could not see in the results was you in the previous two oscillators,
Yes.
you have shown the characterization of laser system, but what about the pulse duration?
Pulse duration we have measured with our frog-based autocorrelator, and I have shown here.
It was in the last one, it was 25 picosecond.
Yes,
What
it
about
is.
the
It is
previous two?
around 30 to 25 picosecond only, because we are not compressing it. It is all normal dispersion cavity.
You have not tried pulse compression?
No, we have not tried pulse compression. We need to amplify it more further. So we are going for this LNA based amplifier right now.
Okay.
So maybe I'll show you in the next meeting. Maybe I'll show those things. Yeah.
Compared to NOLM and NABLM cavity, you are able to reduce the threshold when you use extra gain fiber inside your loop part.
Yes.
How are you able to reduce the threshold? It increase the overall loss inside the cavity.
Yes, we know that in NOLM case, so there are little bit of unabsorbed pump power, right? And we are not using any filter, as I told earlier. So and basically we are giving the gain of whole gain bandwidth. Okay, whatever it is coming, the restriction is coming from the components and the fibers. So that whole gain bandwidth we are actually pumping. So in that, if we are using that absorbing loop mirror, so then you can suppress some of the noises inside that, and that residual gain, the residual pump power. So that's why it is with low pump power also you can get the mode locking, self-starting mode locking.
Okay, thank you.
Yes. Thanks.
Yeah.
Yes.
Yeah, here.
Patidhar sir.
Are you doing any efforts for higher order dispersion management?
We will do that.
Acha,
We have not
okay.
started doing that because you know that higher order, we have not seen that higher order. But I should mention about the Raman peak here. So if I go back, so in our spectrum now, Here you can see we are about to get the Raman peak. So my main concern is to suppress this, because it can actually get you take the gain, most of the gain in the next amplification things. So we have to control the AC and we have to control this Raman peak. So
even that pedestal in the main spectral also will affect your compressed duration.
It can take the gain also.
Yes. And then second thing is just curiosity driven. What is the dynamic range of your frog setup? Means what is the scan range? Because you are saying that you have measured something like 25 to 30 picosecond.
Yes.
So what is the scan range
so
of
up to 150 picosecond we can measure.
Okay.
Yes.
Okay, thank you.
Yes.
So if there are no more questions, then we'll thank Dr. Shamal Mondal for his excellent talk.
Thank you.
Now I request Ms. Tulika to bring a memento.
So the last talk in this session is to be delivered by Professor Shri Ganesh Prabhu from TIFR Mumbai. His research interests are far infrared spectroscopy in condensed matter physics, terahertz spectroscopy and imaging, pump probe spectroscopy, near field terahertz spectroscopy, and the recognitions, awards, etc. are 2 patents have been filed by him, more than 90 international journals, and more than 70 papers in conferences. So, Dr. Shri Ganesh Prabhu, welcome to the session. We are ready to hear your talk.
Oh, thank you so much. And first of all, let me thank So let me first thank the organizers for inviting me here and giving me this opportunity to speak in front of you. So thank you very much once again, and also thanks the chairman for such a kind introduction. I'll be talking about far field and near field terahertz spectroscopy. That's what we do in TIFR. My laboratory is the ultrafast spectroscopy laboratory. If you want to see my web page and what we do, this is the QR code for that. You can scan it and have a look at it. So in today's talk, what I will talk about is some activities about various terahertz setups. I'll also talk about some pump probe studies of some topological materials, because those are the ones that we have been studying. Then I will talk about the far field spectroscopy of some of these materials, and then the time resolved pump probe on BATI-03, which is a new work, and then I will talk about the near field spectroscopy of the metamaterials. So now, okay, we are located in Mumbai, the southern part of it, and Professor Bhabha actually formed this TIFR and were supported by JRD Tata. Now, in the terahertz radiation, if you see, basically it has this part of the electromagnetic spectrum contains a lot of these activities. I mean, there are a lot of phenomena that one can study for molecular rotations, lattice vibrations, superconducting things, so piezo-Josephson junction thing, the electron plasmons, magnons, polarons, a lot of these things one can study, and terahertz is very powerful tool to study this. And this part of the spectrum is actually currently getting very much into the foray. A lot of new techniques have been coming in, and that's why this is a very interesting part. So our topics have been, we have been interested in studying this near field scanning terahertz microscope, which is a home built one, and that some results I will talk about that. We have been also working on waveguides, fiber designs, whispering gallery modes for very sensitive detections, but none of these things I will speak today. Our future work has been to have terahertz materials, study these materials under high terahertz field as well as study of materials under the magnetic field. So these are the setups which we have, and these are the resolutions that we have among them. So one is the terahertz time domain spectroscopy, again which is a home built, that has a resolution about 4 to 7 gigahertz. The other is the terahertz continuous wave spectroscopy. This is what we use it for extremely sensitive measurements of plasmonic resonances or whispering gallery resonances, and those are having almost of the order of 2 to 4 megahertz. It's a very high resolution if you compare it to the main terahertz. Then we have optical pump, optical probe, time resolved reflectivity, OPTP, that is optical pump terahertz probe, time resolved transmission, etc. And we are currently building this high field terahertz spectroscopy setup. Now to start with the topological materials, these are the, so I will only speak about PTAL. There have been many other ones we have worked on, but I will just show some results of this PTAL. So this PTAL actually crystallizes in this non-symmorphic space group, and this has a very chiral crystal like structure, and as a result what happens is you can look at, you can do the pump probe spectroscopy and then look at how the nonlinearity of this is changing. You can also do it as a function of pump probe spectroscopy. So here I will only speak about the nonlinear generation. So this is a very simple experiment, most of you are very familiar with it. So you pump it with a different color pump, and then you probe it with another colors, and this is where you focus it in the on the sample. So this is a very nonlinear process. So again, all of you are very familiar with it. So the polarization that you generate has several of these structures. So we linear, and then the square, and then the cube like this. And sorry. So what we have concentrated is on the phase matching condition. Now this phase matching condition can occur when you rotate the crystal or the polarization of this light, and several experiments have been done in the past by people, and they have actually looked at these topological materials to study. So basically they have sent actually the beams, the red beam, you can see that it has gone on here, and then they have looked at the reflected second harmonic, and then these kinds of structure, these are the type of things that you can look at, and then from this you, I will tell you some of the theory also little later. So the experimental setup is very simple. You put the femtosecond pulse on this, and then look at the filter out the 800, and then only look at the second harmonic generation. Now here again you have to do this phase matching condition by rotating it, and what we found out was the SHG, which is actually which is quite broad here, and this is slightly narrow, 400 nanometer. You can see that we have the dependence which is coming, which is about 1.59. Now this happens because this is a very surface related phenomena. So when you are rotating the crystal, the interaction is happening in the first few layers of this crystal. This is mainly a metallic crystal, so most of it is getting reflected. If you do this on the gallium arsenide, you will see that we get a coefficient which is up to 1.96, which is almost close to 2. So that also shows that it's a almost E square kind of behavior. Now this is the polarization dependent SHG, and that gives you a lot of information. So here you put a polarizer with a polarized light, and then look at the analyzer after rotating it. Now this is given by this following tensor. So since this is a highly anisotropic crystal, so with the specific point group symmetries of 23T, you only have one component of it, which is 2 into D14, which is the one which is valid here, and this actually tells you that this is a chiral crystal. That's why most of it components will become 0, and only these components will survive, and these are the ones which will contribute to this. This work was done by Utkarsh. He's also done many other works, so this is one of the part of this. And what we did was we looked at the parallel and the perpendicular components of this, and this is where the results are. Now we actually started with gallium arsenide and zinc telluride, which are the samples which we have in our lab, So we did this experiment on these samples, studied their nonlinearity, and we actually fitted it with the formula that was given earlier. And you can see that the fits are very well done, and then we use this on the PTAL, and you can see that the theoretical thing that we have used actually has worked out really well for this. Now we also studied this Weyl fermionic, I mean this is also actually also a Weyl fermionic material. So here we wanted to look at the pump probe with an excitation. So what happens here is we actually looked at the excitation in this PTAL by exciting it with the 650 nanometer, and you can see that it generally it suddenly gives a big sharp thing here. So this is where the non-linear generation has taken place of these carriers, and then they are actually slowly decaying. So they are cooling down, and you will see that there are some kind of oscillatory structure there. Now you have to actually model this in like a temperature. This work was done by Ruturaj, one of my students, and with this formula you can fit the carrier temperature, and then you can see that this fit you can do and then subtract out. And now this portion, which actually was very small, you will see that if you enlarge it, it will look something like this. Now here there is a very interesting part. You will see here as the intensity is changing, there is this oscillation amplitude is changing, but at the same time you see some another amplitude which is coming, which is a slowly varying thing. So now you have two oscillations here, one is a very sharp one and another with a very slow envelope. So if you take the Fourier transform of this, you will find that the one part which gives you the acoustic phonon, which is at 60 gigahertz, and the other one is a 2.93, roughly about 3 terahertz, which is an optical phonon. Now this actually matches exactly with the experimentally observed Raman thing. So we have been able to actually excite the phonon inside that crystal, and that you could actually combine it together, and then we could see this modulation in the reflected signal. So these are the things that to sum up, that we have been able to actually see this excitation as a function of the fluid. So another way to look at it is that suppose this is the surface, you are basically banging it, and as your banging thing goes on increasing more and more, you will basically create a shock wave. So this is a shock wave, this is what we are actually seeing it. So the other part that we are working on is the study of ferroelectric materials. So these are the ferro materials which have a lot of interesting dynamical effects. Now these are also very important because most of you are familiar with the magnetic systems where you can flip the magnetic things into other ones and use it as a memory things. So you can also do the same thing with the ferroelectric thing, and that if you can combine with the pulse laser, then you can have extremely fast memory system. So that is why a lot of interest is in this, and also from fundamental physics point of view, that has got a lot of these interesting domain switches, etc. So what we did was we basically did something called the ultra fast imaging of this. So here what we did, we basically passed this beam through this crystal. There was a pump, and then the SHE that was imaged in the thing. So this was done by my postdoc. Now he's in Netherlands for these future things. So here what we did was we did this polarization resolved imaging using the lens, and you can see that these are the domains actually which are creating this second harmonic generation. Now when you rotate the crystal, you will see that this effect is there, and now this is an ultra fast sort of a movie which we have made, and you will see that as this around 3 or 4 picosecond is where our zero is, and at that time when the pump pulse comes, suddenly you will see that the polarization of those domains have switched, and now you see that this part is come. Now it takes certain time for it for the depolarization going back to this. So here you can see that we have been able to do this imaging. This is done this on barium titanate. So this work is yet to be published, but I just showed you this initial So these are the static images of the same. So without spending much time on this, I have already explained to you that these are, so in the beginning there is nothing, this is at the negative delay, and this is where as the pump starts coming in, you will see that a lot of these domains are getting formed as a function of time, and as within hundreds of femtosecond or few tens of femtosecond, this whole thing starts becoming. So this is kind of a stochastic polarization switching dynamics. Why this is not? So now I will talk little bit about the terahertz study of various materials. This is another work that we do. So this is on the single crystal beta gallium oxide, and these are a very popular material. And this work is done in collaboration with Professor Anna Bhattacharya and Professor Tamilvel. So their student actually made this, grew this, Manisha, she grew these samples, and they are excellent crystals. So you can see that this is a very transparent, colorless and wide bandgap semiconductor. It has a bandgap of around 4.87, and it has very high breakdown field of about 8 megavolt per cent, which is very high. And these crystals were grown by this optical float zone, and you can see these are very beautiful crystals. And it has a structure that it is along the two axes, it looks very different. And as a result, what happens is when the terahertz passes through this, it actually sees two different, it sees two different for two different polarizations, it sees two different refractive index. So we have seen the largest difference of refractive index, which is about 0.3, and this we wanted to actually check that how we look at this polarization state. So this is the ellipse, and this is the formula that you use. So this is basically the signal that we measure, and these are the different portions which I will explain to you. The delta is the phase difference between the two components of the this. So now this is the arrangement of our overall thing. So you will see that the main beam goes here with certain polarization, and then it has this A and B and with a phase change, and these two components with the polarizer and the analyzer we go on changing, and if you solve this formula you will get the final answer. And what we found out that at these two specific frequencies it acts like a half wave plate, and then at the corners it acts like a quarter wave plate, but we had to prove this. Now the only way to prove this is by the ellipticity and the orientation. So these are the Stokes parameters that you have, and these are these are given like this, and then you can have the ellipticity and the orientation angle, and you can see that at exactly those corner points you have this entire crystal behaving like a quarter wave plate. And we did actually a lot of study of several of these, and in that we found out that the nickel one shows the maximum amount of the nickel doped gallium oxide shows the maximum amount of polarization change. Now I will switch to the last part of the talk, which is the terahertz frequency domain of the metamaterial studies. So first of all, what are these metamaterials? Now those of you who are familiar with the photonic crystal and all that, they will quickly understand this. So these are materials where artificial materials which are not naturally occurring. The previous ones are well all naturally occurring materials, and these are the ones which you actually design them on the computer, fabricate them, and then only look at what are the things that we, what are the properties that we are looking at. So you have these small portions, and those you can have at a periodic structures. Either you have them in 2 dimension like this, like these are the split ring resonators that you can have them in 2-dimensional array, or you can have them in the 3-dimensional array. The most important thing is that you should have them in the periodic structure. So to start with, suppose if you just start with a one single rod kind of a thing, and if you have a periodicity of this, what happens is this polarization actually, this light will actually excite a dipole, while the horizontal one will just pass through. It will not excite that dipole because the length will be proportional to it. And then what happens, exactly because it is acting like a resonant antenna, when you look at the spectra, you will find that only this portion, that frequency will be attenuated. So we actually fabricated these cut wire metamaterial, and we actually also saw that is exactly as you rotate it, you will see that the specific band is completely blocked in this region. Now we did this because we wanted to also look at the periodic array of these slits, and so my postdoc, now he is a faculty in Thapar, Dr. Arnab Patnaik. So what we did is we actually started with a slit. So instead of the rod, now you have a slit, the rest is all a metal. Now here what happens is this polarization light will just pass through the slit, while the horizontal one will excite the dipole, which is shown here, and this dipole will actually cause that beam to particularly get blocked, and as a result you will see that this is, I mean we have been able to see, I mean the theoretical and the experimental ones are matching pretty well, so for two different polarizations. And if you do this on the computer, you will get these periodic array structures, you will get all these resonances, these are the modes which are stuck. Now these are all done by computer, okay, these are all simulations, very beautiful results. We wanted to do this experimentally, so for that we had to design the near field. So that was done by my first student Ajinkya. So what he did was, he basically made this probe tip was brought right next to the sample. So as soon as the terahertz which is generated here, it passes through these four parabolic mirrors, gets focused on the sample, and as soon as it just comes out, you just measure what is the field, and this you bring this tip very very close to the surface, and then you measure it before it gets completely moved out. So here what you are doing is at every point you are measuring this signal of the terahertz. So this signal has got two components now when you take the Fourier transform of this. So one is the amplitude and another is the phase. So using this you can actually create two different types of things. So here you see that you put the sample and then put the tip, and at each and every point you measure this terahertz. So like this you move it along the x and y, and then you generate these different images. So this is like one shot that you have generated in time, and as for different times you generate them, and then you just stack them together, and then you will be able to generate this. So there are different tips for this. So if I give you that example that I just have one single rod like say thing, then I can bring this tip very close, and this is where the gap is. So if I want to measure it along say y, then I have this gap right next to this. So this is horizontal, so it will measure y. Now if I turn the tip in the other direction, then the gap is along the x axis, and I will now measure y, and sorry, along x, and then along z if I want to do, then I have to have a gap which is perpendicular. So these are the different tips that you need. X and y tip are the same, but z tip is slightly different. Now so this is the setup which we have, and this is where the tip is. You can see that this is the tip right next to the sample. So this is again a home built setup, and then so again I'll recapitulate that this is where you generate the terahertz, pass it through the sample, and normally you measure it in this zinc telluride. So this is called far field because the field that is passing through this is getting measured at far away distance, but then you can actually bring in this tip right close to the sample and then measure it. So I'll talk little bit about the work because about Samuel, because Samuel actually made certain changes to this, and those results are also very very interesting. So here I will first show you, some of you have already seen this. So here there is a set of these slit arrays, and the tip has been moved and scanned across, and you can see rest of the part is completely metal, and there are those 4 holes, and as you start putting in, you will see that this counter is changing. So this is 17, 18, 19, like, so this is changing, and now the light will start coming out from the back side. So rest is all a metal, there are holes, and now this is how the light comes out as a function of time, and you can see this we have several femtoseconds this light is coming out, and there are different modes of these lights. So this is as a function of time. Now we switch to the, for each and every point we have a Fourier transform, so you can also see as a function of different frequencies what are the modes which are coming in. So these are different modes that you can see which are coming in. So dipolar mode, quadrupolar mode, and those modes you can very easily study. So this work of course was done by Ajinkya, now he is in Cambridge. Now this is the last part that I want to talk about. So we were working on this metamaterial design with Professor Gagan Kumar from IIT Guwahati. So he made basically this metamaterial, which is a structure, periodic structure you can see, and this has uneven circles. So the idea here is the even structures if you have, then these are called symmetric metasurface, then there are certain resonances which only they are very unique. But when you start making them asymmetric, that is you know, this is a asymmetry between the two, and then you can make them all four of them of different type. So now what happens is there are certain resonances which are occurring here, which is I will show you in the next slide. So those are actually the broad ones, and now you have, because of the coupling of these two different things, so these are called bright modes and dark modes. When the dark modes couple to these energy levels, you start seeing a very sharp thing. So this is called Fano resonance. So those of you who are familiar with the nuclear one, they will immediately see that this is a Fano resonance, and this is the experimental one. So this is a theoretical one, this is the experimental one, and we wanted to actually probe this. So again we went through this our setup, and you can see that the tip is actually moved across this periodic structure. And now you see this is the simulated one. So using the computer you can get very beautiful such structures, and this is something which we measured it experimentally. Now you will see that you don't find any correlation between this and this. So how do I convince you that this is so? Now this problem is because the tip which we have,
Dr.
although
Prabhu,
it is,
you have 2 more minutes.
yeah, I'm finished. So the whole reason is because the resolution of our tip is, although it is 10 micron, which is under wavelength of terahertz is 300 micron. So you will say, oh, it is lambda by 30, but no, it doesn't. We found that this is actually giving us 30 micron kind of resolution, and because of that, I told a student that why don't you just take this image and use a kernel which is 30 micron wala and then convolute. So when you convolute this image with that 30 micron thing, now you will see that this and this, they will start looking quite similar. So you will see here. So this is theoretical, this is the experimental one. So we are actually working on it. We tried artificial intelligence based thing, machine learning things, etc. But we are still, so anybody who is expert on AI or something, they can always guide us on this. Now the last part is we have this high field terahertz setup which has just come up, and we using the LINBF3. This is done by Vivek. So we have got about 1 milliwatt or 1 microjoule power, and this is the spectrum. You can see it is quite broad, and currently we are having, because our crystal is small, it is 200 to 300 kilovolt per centimeter, but we would like to increase it to 500 to 1 megavolt. One of my another student, she is an engineer, she has made these A-B silicon balance photo detectors. So if you are interested, you can always take them. They are very much useful for pump probe and those kinds of studies. Again, this is indigenous, so they are quite good. So these have been our research, current and future. So right now we are into this materials with high terahertz field. Hopefully next year time I will have some results to talk about this. These are the people I wish to thank. We collaborated with Professor Gopal, who is the director of NPL. I talked about the work of Ajinkya and this Dhanashri and Yamuna have finished their PhD now, and also funding from DAE is heavily appreciated. These are all our collaborators with whom we have collaborated. With Dhanveer and Professor Krishnamani, we work on strongly correlated system thin films. With Professor Kamaraju, we work on this, it's on ISER Kolkata, on these magnetic systems. Then Professor Gagan Kumar and Professor Dibakar Rai Chaudhary, we work on the metamaterials related work. With Dipanshu Bansal, we have started with these ferroelectric things. Professor Ranjan Singh, 3D metamaterials, and Professor Rajiv Kumar Mitra, we have worked with him on this bio terahertz. So he's an expert on proteins and those things. So today I talked about the work with Ruturaj, Utkarsh, Utsam. These are my two postdocs. I mean, who have both left. Vivek just left last 2 weeks back, and Arnab is already a faculty, and Gajendra is our scientific officer. So thank you very much. If you are interested, you are always welcome for the collaborations. Thank you so much.
Thank you. Thank you for the very nice talk. Any questions, please? Yeah.
Hello.
So you have mentioned about the tip. What is the material that you are
That
using?
is low temperature gallium arsenide, and the gap is exactly the same photoconducting antenna. So the gallium arsenide substrate has been removed and only the portion. So this is roughly about 2 micron thin, and width is about 10. The tip part is about 10 micron.
So you are able to guide the terahertz into that tip.
No, what happens is, suppose so this is how the tip is. So I bring the tip close to the surface, and there is already a red light which comes in. That 800 nanometer pulse that comes and gets the gap. So I just need to put this fixed and then scan move the sample to and fro. So this remains fixed, and it keeps sensing different portions of the terahertz as it's coming through different designs.
Very nice, very nice.
Oh,
thank you.
Thank you so much.
Yeah, there's a question here.
Professor Prabhu,
Yeah,
very wonderful talk.
Thank you,
and
sir.
you have covered too much of information just in 25 minutes. It's very difficult to follow. But just one curiosity. You showed one measurement where the depolarization of light was measured, and
Yes.
the time you have measured in tens to hundreds of femtosecond. And that's very wonderful, because people say that if you excite the material, the dipoles are induced, and you are measuring the depolarization of them. But is there any effect if you change the intensity of light or the polarization of incident light, whether the depolarization time will change, or what do you say?
Okay, beautiful question. Actually, we are investigating that portion as a function of the polarization. So what we have found out was the intensity of the second harmonic is changing. Okay, but the depolarization which is taking place, that is, so the one which I showed you, there we see that it is lasting for very long. Okay, initially when we had it at very high power, we started getting a very sharp decay, but then we realized that it was happening more because of the damage that was occurring to that sample. So it was really not a right thing. But when we did it at a moderate portion where the sample is not getting damaged, in that region we have been seeing that the polarization times are large. So I have not talked about the 2D materials that we have studied, because it will become too much. So there we have actually seen very sharp decays, like graphene or MOS2 or those kind of things. So there we have seen this decay as well as the depolarization. But in here, in this ferroelectric material which we have studied, we have that's why you will see that after the excitation, even after several picoseconds, you see that it's a blue patch. But the change from the red to blue, you will see that it is slowly changing, because that is where in hundreds of femtosecond we see that the domain switching is taking place, and then the entire thing starts becoming bluer and bluer. So that portion, the rise, that is the most interesting part for us.
Yeah. Any more? If there are no questions, then we thank Dr. Prabhu.
Thank you, Dr. Prabhu, for a nice talk. Now I request the chair to present a memento to our speaker. I request Nitika to bring the.
Thank you. Thank you. Thank you. Thank you so much.
Thank you, madam. Thank you. We would like to thank the chair for chairing the session very nicely. Now I request, as a token of gratitude, we would like to present a memento. I request Dr. S.K. Majumdar, Director, Material Science and Advanced Technology Group of RRCAT, to present a memento, please. I request Nitika to bring the memento. Thank you, sir. So there is an important announcement from the Transport Committee. Symposium participants are requested to furnish their departure details at the help desk, provide transportation to railway station, bus stand or airport. So now it is time for tea. Let us assemble here for the next session just after 15 minutes. So it is now 11:30. We will assemble here 11:45. So tea is just in front of the, ILA exhibition, industrial exhibition at the lawn outside.
सब नीचे है ना?
अरे ये उनकी है, वो कल चश्मा पहन यहाँ की थे शायद, चश्मा पहन रखा था ना इन्होंने। सर कौन सी स्टेशन में आपका?
अभी जो सेशन है सेकंड वन। अभी कौन सा खत्म हुआ?
पाँचवा खत्म। यार एक बार सर से पूछ लेते तो ज़्यादा अच्छा रहता। इनको म्यूट करो ना, इनको माइक को कर दो यहाँ से।
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EPI 2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging. In particular, it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In the nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It's easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
Today, thermal imaging is more accessible and affordable than ever. More and more professionals rely on FLIR's wide range of cameras to reveal invisible heat issues and to capture valuable temperature data. Our own innovation, development, and manufacturing capabilities give FLIR the agility and efficiency to produce such a complete line of thermal imagers, and to do it so economically. Volume cameras can be useful in the world of R&D and science. But when it comes to the fine points, researchers and product developers demand the highest level thermal imaging performance, the kind FLIR science cameras are famous for. They need technology that captures high-speed thermal events in high resolution, and with the most reliable results to help discover new phenomena, test new developments, and prove findings. They need to record detailed thermal distribution and variations in real time to measure heat patterns, dissipation, and other critical temperature factors. For years, FLIR has been committed to developing thermal imaging cameras that advance research and development projects worldwide. We still are today, with dedicated production and R&D facilities in Sweden and Florida. The FLIR Niceville facility is fully immersed in the design, engineering, and production of cooled cameras. Here, FLIR creates cameras for all wavebands, including near, mid-wave, and long-wave IR, and builds all kinds of detectors, including InGas, INSBE, and SLS. The Niceville team also develops software that is completely tailored to R&D and science professionals. The FLIR Research IR software works seamlessly with all FLIR R&D and science cameras that allows live viewing and provides detailed analysis of the most complex experiments. In Täby, Sweden, engineers in FLIR's state-of-the-art design, engineering, and production facilities focus both on cooled and uncooled cameras, targeted at the most demanding applications. These cameras offer a highly efficient and cost-effective way to capture accurate temperature data. No other thermal imaging company is as committed to researchers and scientists as FLIR. With its dedicated facilities in Sweden and the US, FLIR continues to be the industry leader in cutting-edge infrared technology for R&D and science. You can count on it.
The TPX3 cam from Amsterdam Scientific Instruments is a pinnacle innovation in ultra-fast imaging detector technology. At its core, the detector features a photon-counting hybrid active pixel sensor based on the advanced Timepix3 ASIC developed at CERN. Unlike slower frame-based digital sensors, the TPX3 cam operates using continuous event-driven readout. Each sensor pixel works like a precision stopwatch with an ultrafine time resolution of 1.56 nanoseconds. activated pixels simultaneously record both the event time of arrival and response duration, or time over threshold, processing up to 80 million hits per second at an effective frame rate exceeding 500 MHz. Individual pixel responses are intelligently filtered by signal intensity and pixel grouping to afford noise-free detection and remarkable contrast. The TPX3 cam is flexibly formatted to detect photons, electrons, neutrons, and molecular ions. Configured for velocity map imaging spectroscopy, the TPX3 cam captures time-resolved images of gas phase reaction dynamics at exceptionally high repetition rate. Combining the TPX3 cam with an image intensifier enables single photon detection for versatile applications in quantum optics, neutron imaging, and fluorescence lifetime microscopy. Dedicated device software provides an intuitive acquisition control interface and data processing workflow. Users are also offered a robust API package for the freedom to customize data management and device operations using popular language libraries. Amsterdam Scientific Instruments' premium detector solutions empower researchers across the world to see beyond limits with unprecedented speed and accuracy. To find out how you can use the TPX3 cam in your research, contact our experts at info@amsins.com.
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EPI 2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging. In particular, it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter-long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In the nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It's easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
Today, thermal imaging is more accessible and affordable than ever. More and more professionals rely on FLIR's wide range of cameras to reveal invisible heat issues and to capture valuable temperature data. Our own innovation, development, and manufacturing capabilities give FLIR the agility and efficiency to produce such a complete line of thermal imagers, and to do it so economically. Volume cameras can be useful in the world of R&D and science. But when it comes to the fine points, researchers and product developers demand the highest level thermal imaging performance, the kind FLIR science cameras are famous for. They need technology that captures high-speed thermal events in high resolution, and with the most reliable results to help discover new phenomena, test new developments, and prove findings. They need to record detailed thermal distribution and variations in real time to measure heat patterns, dissipation, and other critical temperature factors. For years, FLIR has been committed to developing thermal imaging cameras that advance research and development projects worldwide. We still are today, with dedicated production and R&D facilities in Sweden and Florida. The FLIR Niceville facility is fully immersed in the design, engineering, and production of cooled cameras. Here, FLIR creates cameras for all waves.
Welcome you all to the next important session, that is on laser materials. So we have the pleasure to have Dr. S.K. Dixit, outstanding scientist, Group Director, Laser Group of RRCAT, to invite the session. Dr. Dixit, please. Dr. Dixit is credited to have expertise in beam quality improvement of laser system, and he has proposed a novel concept to obtain diffraction limited beams in the laser system. Apart from that, he has expertise in nonlinear optics, high resolution photoisotope spectroscopy, and fiber grade sensors and laser-based sensors. And he has also credited up to 25 publications. Apart from that, he has edited 2 books in the field of laser science and optical resonators. Now I request Dr. Dixit to start the session, please.
Good morning. So this session is going to have 3 talks from 3 distinguished speakers. And the first speaker is Dr. Sandeep Dhara from IG Car, Kalpakkam. His title will be Material Properties Beyond the Physical Limit of Lights. And his research interests are nanoscopy and nanospectroscopy, photonics, nanoscience and nanotechnology. And he has got a lot of awards. First is Homi Bhabha Science Technology Award 2019, DAE-SRC Outstanding Researcher Award, Senior Member Optica USA, Fellow Institute of Physics UK, and Fellow Royal Society of Chemistry London. Now I invite Dr. Dhara to give a talk. So Dharaji, you've got about 20-25 minutes for talking because let people interact with you. Otherwise, it's up to you. Full 30 minutes you can also talk.
Fine. Thank you. Thank you for the NLS organizing committee for giving me the invitation. It's my honor to be in the laser community. I don't know whether I fit in. I'll just use the laser and many of its own natural utility. And also I thank the chairman for introducing. Of course, this is being done by the automatically. It's a very fantastic display of biodata, precise, and Dixit for his kind introduction. So I'll be just going about it. My talk will be a little bit loaded. Let me see if I can do justice. So this is my first agenda, acknowledgement, where mostly, unlike many other DAE scientists, I have worked only with the students. I was never been given any faculty, unless I think Kishore is here or not. Yeah, Kishore is here. So he is the only faculty who joined, who also started doing PhD with me. So they are all students to me. I'll be talking most of them work, except few of the work which I may not be able to cover, like Reshma and Raktima. Those work I cannot cover. So I could have started this because it was a dilemma when I gave the title, because it's a material properties or material characterization which I am will be doing in this talk. I am not very sure. So as I thought that if it would have been properties, then it would have been slightly different. I would have talked the fundamental acoustic modes, like every object is vibrating, and Raman can also catch that apart from the molecular vibration. That means you can breathing or stretching mode any object. It need not to be semiconductor, it can be anything. We have done it by Raman spectroscopy, and these modes, by these modes you can determine the size of the particle, and so once this is basically sound wave and the acoustic mode. If you can, we can get the size, and also we can address, I could have also addressed, or I would have gone in this talk, address where I have observed the electron really spills out when the atoms numbers are very small. And it has been reported in case of potassium, but also I could have shown in the gold nanoparticle when it is in the matrix. So I could have also gone, if I would have taken my talks to the surface optic mode. Yes, as you know that the breakdown of the momentum conservation occurs at the surface atoms, because surface atoms normally normally the momentum is conserved. If momentum conservation occurs because of the defects, and which is most prevalent in the nanostructure. As you know, surface optical mode is not observed easily in the bulk semiconductor, and that too you have to do the time domain Raman spectroscopy. But in the frequency domain itself, we can see it time domain is more powerful. So in frequency domain itself, you can see nanostructures where you have periodic defects, and that defects can invoke surface optical mode. But instead, I'll be talking like more on properties, so I'll breach my talk title back and forth. I'll be talking of properties also, interestingly at the end. So here I'll be just briefly telling about the, this is a coveted, this community is very well learned, so I don't have to spend much time on the overcoming subdiffraction limit. Then I'll be talking of the evanescent wave. Once the evanescent wave is established, then we'll be talking a little bit interestingly, which is also the laser cavity or the cavity mode and confinement of polarized light in those cavity. And then the TAR study, that means steep enhanced Raman spectroscopy, which is at nanoscale, where I'll be utilizing its change of polarizability and many other, mostly it will be properties until properties of semiconducting nanowires. But otherwise it is mostly silicon nanowire, where I'll give some interesting properties, which is actually nanometric property. Then I'll conclude. Of course, I have a mini conclusion for everything. Everything of this talk will be covered in this book which we have edited recently. And as you know, I'll be working in this space. You know Abbe's limit. And I'll be working because most of my laboratory objectives are either 40x, 50x or 100x. And these are the wavelengths normally I have used. So we'll be working in so in principle, according to that's what the point of saying is that in principle, I will not be able to see below 300 nanometer, but I will be talking of 30 nanometer, 40 nanometer stuff. So as you know, there are two ways to confine light and to trick away. One is cavity mode, which has been talked in different way, of course, for lasing or laser mode, different kind of exploitation of laser. But interestingly, that because in the cavity mode, the problem is that it's constant by the diffraction limit. But whereas in plasmonic modes, we can overcome the diffraction limit, which I'll be talking very briefly. So if you can, but cavity mode, you have a low loss. So if you can combine them, then you have a hybrid system, and that's what we'll be normally doing by metallic coated apertures or tips or fibers, where we can study the materials which are beyond the diffraction. Okay. So this is briefly the surface optical modes, surface plasmon mode, as you know, is then also surface plasmon polariton, which has been normally observed at the metal dielectric interface. Then this most important to understand this light for the students at least, that if you have the normal frequency, angular frequency wave number, that plot, this is normal light, this is the light line, okay, frequency inversely proportional to lambda. So, you know, this is, we can represent as wave number. You put a metal slit, it becomes slow because your slope constant, slope becomes different. Just simply h nu equal to c lambda if you can think of. So nu and c lambda you can do it. So c here changes with the dielectric or the refractive index part. But once you put a dielectric media in between, then it becomes nonlinear. And this becomes extremely slow. See here the slope change, so light becomes slow. But if you can do a metal dielectric constant where SPP comes into play, it becomes extremely slow, and in principle you can see an atom. You can go perfect lens or super lens, which have been already demonstrated in silver, where we can use, you can achieve with the 500 nanometer line, sorry, this 500 nanometer line you can achieve 70 nanometer easily or beyond. So here you have the, and also you must know that in this geometry, you have, it is not dependent on the excitation wavelength at all. Whether it's 514 or 633, it depends on the aperture size, and what kind of plasmonic materials you are using. It is very simple. It has been demonstrated in 1984, and had he been there in US Carnegie, then he would have got the Nobel Prize, because he was actually Bettig's lab head, but he left to make Jerusalem because he was born in India. Aaron Lewis, and he is from Calcutta actually. So he first showed in his early paper in 1984 ultradiactomy, where he has used metal and dielectric, and he could focus the light of 30 nanometer light. You can pass light through a 30 nanometer hole. Okay. So it is very simple from the, you can understand it again for the student, that from the simple uncertainty principle you can convert it, this P to lambda, and then you can find out, see what is lambda by 2 now can be lambda by 4 pi. That means lambda by 16 you can achieve easily by using the evanescent wave, and if you use the dielectric matrix. And once it is understood, various beautiful things started happening, that you can pick metal rods and can focus a light. That means it is a metallic lens. I'll spend very less time. I hope that people will understand it, because otherwise I have too much loaded. And then if you know SPP wave, then how to see the SPP wave, that is first time observed in carbon nanotube. There is, as you know, the graphene, which is a metallic in nature and is the most lightweight, so we could see it easily. And then later on I will demonstrate in some degenerate semiconductor also we have observed. And then we can do, once you can focus light, beauty is that you can even study RNA. Some of you have done AFM, but you can image the chemical imaging of a RNA or DNA. You can image many properties of single wall carbon nanotube. It is of old studies. This is, but my study will be, interestingly, the question is that if so many things have been achieved, what you are going to show? In this, the problem is that when it's in our when it is ionic material, because so far as carbon, Raman is perfect. But once it's ionic material, which is mostly industry or semiconductor industry use gallium nitride, gallium arsenide and all, then it start behaving. Up to silicon it is fine, but when it's wide band gap material, it does not respond. You know, polarizability is so poor that Raman's intensity. So one of the smartest study was done in indium gallium nitride. As you know that the precipitation of indium or segregation of indium from indium gallium nitride faces the major hindrance for developing this blue laser, and that has been mapped with the accuracy of, if I remember, 35 nanometer there. But that is also by a lot of tricks like autocorrelation studies and all. That is the best study so far made in a spectroscopic measurements. So this is my instrument where we have a Raman's spectrometer periscopically attached to a system where we have 4 different probes, and these probes can be anything you can imagine. It can be AFM or STM. It can be also, it is also where you can pass light, we can pass fluid, we can also shine light, which when gold and chromium is coated, and there is a, this is for ensom tip, and there are terse tip where you directly can coat the nano ball here, this metallic ball here, and can focus light, as previous speakers Prabhu was speaking, where you can take that, of course the tip is made of fully there, in that case gallium arsenide, but in this case, or gallium arsenide as he told, I remember, but in this case the geometry is slightly different. This is a system where we work with 4 different, all 4 independent probes controlled by separately, and this is the typical tip where a gold ball is attached at the top of in the tip, which is for, now see, coming to the subject. So where I promised, I don't know how much I can cover. So here it is first time we observed, it's very interesting. We saw that proximity induced confinement was known, but the study is very interesting. But just to tell briefly that here you have the laser light direction is perpendicular, wave vector is perpendicular to the x direction, say. That means your sigma polarization will be perpendicular to the x, that means parallel to the x axis, which is a pi polarization, and in the sigma cross polarization is sigma polarization. So as you know that in the image force, due to the difference of dielectric constants in the nanowire and matrix, because there are AR gap also, so they absorption and emission coefficients are different, and that exactly will match like that. In case of a emission, in case of a pi polarization, that means parallel to x axis, it will be exactly the same, but in the cross polarization, there a factor will come, and that factor will give the polarization ratio. And the polarization ratio is very interesting, and this has been also shown in a microcavity. Parcel factor has been demonstrated, And they have shown there is increase in the intensity as it is demonstrated long back in a single author physical review paper by Purcell. And there we have done the study. First, interestingly, actually why I am telling is interesting, because we were studying aluminum gallium nitride, or actually slightly minimally doped gallium nitride with aluminum. And then when we studied this nanowire, we could see it's a far field measurements, remember it. And when we did the polarization measurement, we saw that for this smallest single nanowire of 100 nanometer, we could get a polarized information. Polarization, if you know the proto configuration, if you have the polarization condition in the XY and XX, that means pi and sigma polarization you can think of. In this case of sigma polarization, in this case of, sorry, this is sigma, this is pi polarization. And from the proto configuration, you should get only A1 yellow mode and E2 high mode. E2 high mode should be common to both. But nevertheless, this study has been done in resonance condition where E2 high mode cannot be seen, only the optical mode will be seen. And you see in one configuration there is no Raman mode, in another configuration got A1 yellow mode. So from that we configured that they are C-axis oriented nanowire. So this we published in APL. Then while coming, we went to a conference actually before publishing to APL even, to student and myself. Then it stuck to me in his presentation itself, how you can see because nobody asked this question, but question was in my mind, how you can do a measurements in a single nanowire with a far field. Then we devised this, student is very intelligent. So what he did is that he studied this material. You see this pi polarization, sigma polarization, this is our typical polarization ratio. With this study, he studied various gaps, because these nanowires are, see, if you have seen the image, remember the first image, there are close by nanowires, and he started doing this close by nanowires measurement of different gap, L by D. They are not always oriented very keenly, but typically the gaps is 6.5. So from different D variation, he started measuring and the photoluminescence intensity, and he found out that it varies with 1 by L cross D. This is typically a two-dimensional Purcell factor. That means this is inversely proportional to the, in Purcell factor is inversely proportional to the volume. In case of, in this case, it's because of 2D, inversely proportional to the area. And this we published with another bright scientist in our group, Manas Sardar, and with all this absorption and emission rate equation he solved, and he showed that optical density can be increased and there will be certain nonlinearity in the material, and you can really confine the light. And with that confinement of the light, only we could measure the photoluminescence or the polarization we achieve the polarization confinement, and we could measure that APL paper. Then we also naturally, then we could see we could do a single nanowire, 100 nanometer nanowire imaging in that paper. So the conclusion is that we could study the crystallographic orientation during using the confinement of the polarized light, and evanescent to enhancement of the emission intensity has been demonstrated. That's Purcell effect. And we have shown also a photoluminescence imaging of a single nanowire of 100 nanometer, which is subdiffraction limit. But all these remember all these measurements are in the subdiffraction, in the far field. So we are not in the really near field unless the cavity was helping us. So then we have studied the T-enhanced Raman spectroscopic imaging in the subsequent studies. Here also there is a story. If you see gallium nitride nanowire, it was already reported in Journal of Raman Spectroscopy by some author. But the issue is that they never could image the spectroscopic image. It is an optical image. Remember, this is an optical SEM image. This is an optical image. And they did the corresponding, because it's a big nanowire, so they could do the Raman studies of that. So single nanowire gallium nitride Raman studies was reported, but no spectroscopic images was done. So once our instrument was established, then we could first image a single nanowire. This is the nanowire as the AFM image. We could do a part of this. That time we were learning only. But nevertheless, in the learning, we have also done a lot of things, because this nanowire we already doped with magnesium. So we could find out the local vibrational mode. As you know, that if you replace magnesium in place of gallium, then there will be a change of the mass. So spring constant being remaining, spring constant will be different. So there will be another mode appearing with the same symmetry. So LVM mode was observed, and also few more things was observed. And then we studied it is a perfect imaging of a gallium nitride nanowire. And as you can see it very easily that we had a gold tip, because in the VLS technique, if you have to go nanowire, you have a gold tip. Gold should be, is gold that is assisted grown. You see in an AFM image, gold is present. In a TARS image, gold is missing. That's the typical proof of this, or demonstration of the single nanowire. Then we have of course shown, as I told you, the major problem, why you are telling so much about a small image you have done, because doing a Raman spectroscopy and that too image it in a for the ionic crystal is almost a horrendous task, and when it is a very small size particularly. So we have shown these things. This has become even more difficult when it is a gallium nitride and aluminum gallium nitride. See, in this case it is gallium nitride and it is aluminum gallium nitride or aluminum nitride. So this aluminum nitride is ionicity is even, what do you call that factor? I forgot that. A FIC, I think that it is more ionic than even gallium nitride, and we can see that this is a nice AFM image. But when you do this is the spectroscopic image. This is the spectroscopic image, and this is the Raman image. This is the spectroscopic image, TARS image, and this is the Raman image. We could see the AFM image of this. This variation is because we are not auto focus corrected, so there will be change of the small change in the autofocus, because they are not always lying in the same plane, and we have to do continuously without changing the focus point. So that becomes less intensity. Nevertheless, you could image this AFM to the TARS, but when it is aluminum nitride, though even it is bigger, we could not image it properly, just because its polarizability is lower than, and this we studied with the FTDD calculation, and we saw that here also the intensity is, you see the near field distribution, electric field distribution is much stronger than in case of aluminum nitride. So now coming to the picture, to the silicon. Here is the interesting thing. Silicon, these are the different experimental conditions which I will describe it. So we try to understand that time the phonon colonization. What happened exactly if a particular object is staying isolated, localized, or if they are staying together. Because the problem is that you have to understand that phonon, though we understand that it's not affected by the electron, but it is very much. Particularly when it is within the band gap. When your excitation energy close to band gap, it is far more dangerous. But even if it's slightly higher than the band gap, where you are pumping a lot of carrier in the system, then nasty things starts happening. How much time I have, Dixit? Oh, that's good. I don't know what people have understanding or not I am going through. So, here is the beautiful property. This is more than 70 years or 60 years old problem. If you take a silicon single crystal for characterization, we see you have a nice peak, single peak, that is every Raman spectroscopist use it. This is around 520.5. There are controversy, 521, 520. My student is very stubborn. He tell it precise. He is from BHU. 520.5 centimeter inverse with the FWHM around 3 centimeter inverse. Now, if you take a silicon nanowire, you see starts, even the micro rod, it is a nanowire. Even a micro rod you take, you will see that there is asymmetry and there is a shift. He tried to understand all alone without telling me. Actually his paper should be single authorship paper. But anyway, I got the opportunity he has put, because he was RA with me. He was my PhD student. He is a gem of a guy. He still not got job. He was in Israel, but he had to leave because of he had an HR recently also. So in MOSC2, I think, yeah. So here he has started all this, tried to understand all these fits, Fano fits, and Lorentzian fits with the two curves, Lorentzian fit with a single curve. But now the question is that why this broadening happened and why this rate shift happens because it goes to the lower side of the frequency. You have seen 517 centimeter inverse or so. So we did that 16 nanometer nanowire, and we started doing and 1 second we have done the acquisition, and this is your Raman image. You understand each and every point we have collected a Raman across X and Y direction, and we mapped it. Each data taken for each area, 1 point, 1 point, 1 point. I have a 100 nanometer, our scanning resolution is 100 nanometer. And this is the corresponding image, and he has taken every point a collective sample image spectra for that. And then when you try to fit it, these fittings are like this, and this is not a single peak, there are double peaks. And if he has done with more time, then there is, and it is perfectly connected to we have placed this nanowire on the copper base, so that there will be no thermal conductivity problem. But even if that, with the extreme low power, he has used some lowest power possible in the laser, because you have to work in the long distance. So 1 second, 4 seconds, 10 seconds, the broadening changes and multiple peaks comes, and exactly it happened also for this 10 seconds data. For torch data, he has seen the double peaks are there. Now he did it further lower. It is 25 nanometer. The focusing become even more dangerous or difficult, and so this nanowire is not completely seen. It is a 25 nanometer. You can image it. This is the AFM image corresponding to the nanowire, and we started seeing the single peak, and that is FWHM is, you remember, that is 34 kilowatt per centimeter square, and that's around 3 centimeter inverse is here it is 5, and lifetime correspondingly is around 1 picosecond. So then we started understanding. It is not that we target, then we did the KPFM study, because the same equipment can be done KPFM, because I was telling that we have a STM peak. We did the KPFM of those nanowires there, and we found out that eventually for silicon grown in that particular technique, CVD technique, it has been predicted, and he also measured that is completely, this is depletion, width of depletion is around 25 nanometer. That means now the phonon is completely localized, and it is a completely depleted system, so there will be no electronic effect, and that's how we started getting this single peak. So basically then we try to understand this is what he has done, and then so then all these studies we have started doing this. Is it because of the phonon confinement of the size? Very bad. So as you know, this is the phonon Gaussian shape of your optical phonon. Is it due to that? That has been crossed out, because we have shown it that this is changing just because time is changing. Same size, time is changing, the shape is changing. Then size and shape, it is not also correct. Thermal excitations, we have already we have on the copper base, even 1 second data also have that with the lowest power possible. So possible for the Raman measurements, I will say. There also it is negated. So all models, Fano model didn't give you the perfect fit. So then we started, and then we found out after this last KPFM measurement, the size dependent localized phonon population induced charge depletion. That means if you have a depleted system, if you can have a system where carrier is not available, free carriers are not available, or intrinsic semiconductor, then you can find out that broadening is smaller. And this was a problem for silicon for long back. As you know, silicon is very important material for electronic industries. So this is the typical property of which is bigger. So the TAR study, we have demonstrated Woodside gallium nitride phase and imaged it, and also we have found out magnesium as a dopant, oxygen defects, I forgot to mention it there. Then we have observed the MG mode, that is local vibrational mode, and also as I told you that we could not map, that was the silicon nanowire, sorry. So silicon, 16 nanometer silicon nanowire we could image very well because it is more covalent bond, but whether aluminum nitride, which is ionic bonded, we could not image it better. So, and finally we could show that this is the fraction of ionic component, a Fick property. Fick component is 0.5 for aluminum nitride. So anyway, so this is all about spectroscopy, but As you know, as I
only,
told you,
only 3 minutes left now.
Thank you very much. So, so I'm also in the correct phase. So here, now I'll talk of nanoscopy. We call it microscopy, as you know, but when you want to see the object at the nanoscale, you must term it nanoscopy. It is not that it's my terminology, maybe I have boldly used in as a book title for the first time, but this jargon was there in the literature. So nanoscopy, so in the nanoscopy you can see first time we could make a 10 nanometer gallium nitride nanowire in the, this is AFM image, this is the AFM image and corresponding, this is, sorry, one is AFM image and another is ENSOM image. Which one is ENSOM image? This is the phase image, right? This is the phase image. This is the ENSOM image, this is the AFM image. You can see it, 10 nanometer nanowire also AM image. This is an optical image, remember it. And this is an AFM image. This is the nanoscopy. Nevertheless, interesting is the physics. That's fine, that once you have the tool you can do it, but we started doing it, this is with Tapas Ganguly. We measured the UPS study with that and found out where the, because you know indium nitride is a degenerate semiconductor, and because of the natural nitrogen vacancy you get doped, because stoichiometric indium nitride formation is very difficult. And we started seeing is the ENSOM image corresponding, this is the AFM image, corresponding ENSOM image, corresponding ENSOM image. We started getting these rings, then we started talking with Aaron, who was my good friend, and then he told this may be the SPP wave. You can see this two SPP wave have done the interference and constructive and destructive interference has formed this wavelet formation. So we reported first time for the, other than the graphene in indium nitride system, indium nitride system, the SPP wave. And then we started the last one is our patent on titanium nitride, this is TINX film with the CIMED group, where we had made the metamaterial for this. This is the material for, we tailored its refractive index or SPR wave for biological applications with different content of titanium to nitrogen ratio. And in one of the, it's not a very systematic study, in one of the composition we could start seeing the wave again. It is around 900 nanometer, in that case around 272 to 75 nanometer. So we did then again this SPP wave was observed by the NCM. So this is the conclusion, and optically imaged gold nanoparticles on 20 nanometer, below 20 nanometer using, okay, this is not shown, sorry. Plasmonic wave indium nitride 2D electron gas system we have seen, and wavelength of SPP wavelength of titanium nitride film on glass estimated around 900 nanometer. So just to say thank you for your kind patience. We have also, this is not covered, but just I showed, because there is a school for that, 5th and 6th I heard, that is on the structural material, color, artificial color with structural materials. Here we have made hole on silicon nanowire, and we could see the different colors, and right from light blue to red, and not only that, with different aspect ratio or different aspect ratio of the whole length, we have we can create also different hue of blue. With this, thank you very much.
Yeah.
I think I'm in time, more or less.
Oh no, you are finished well in time. You took 31 minutes, 1 minute more than 30 allotted. No problem. We may have few questions from him. Anybody? Give the mic to this fellow.
Ganeshan has some question, I think. Dr. Ganeshan might have a question.
Yes. You can ask. You are close by, so you can ask.
Now others have to listen. No? What is the question?
देखो उसका. You can use this.
It's a very simple question. You have used AFM to detect this scattered and backscattered electron waves, you said. Okay, in the slum, induced what you call local phonon mapping. It must be an optical mapping, number one, optical phonons.
Yeah.
And second two is how do you do it in AFM? You must have a conducting AFM to do at least.
No. I don't know exactly what you are telling, but AFM we do, AFM and ensemble strategy is totally different because here, this of course same
How
team
do you
we are
say,
using.
how do you say it's electron waves? It is like for
No,
example.
it's not electron wave. It is a phonon.
Okay. Or I have misunderstood something.
You misunderstood.
Okay.
It's phonon. It's not electron wave. It's a spectroscopic image.
Sir, my question is a little bit technical. I just wanted to know. Yeah, sir, here.
Okay.
Yeah. So I'm more interested in knowing the acquisition parameters for generating those Raman images which you have generated.
Because if there is no other go more than a second, because otherwise you cannot cover it. But suppose your material is not affected by the heat, and if you take care of the heat dissipation or heat effect, then you can dwell on as much. But if it is this is it takes otherwise whole night. So we normally do it 1 second for acquisition. But sometimes we have to do it for 10 seconds also, depends on the material. That is the typical acquisition time for each Raman spectra. For imaging you can understand how many, because our resolution is 100 nanometer. That's the typical. Of course you can tell, but we don't know exactly at the tip, within the presence of tip. When you are doing a TARS imaging, in principle my resolution is 10 nanometer. It touches down to 10 nanometer. So I can scan up from 10 nanometer also. But there will be not much information we will get, because in 10 nanometer, because yesterday also I was telling that Raman is a basically molecular information. So you don't get big gain out of 10 nanometer, really not, unless just you can image it and show its demonstration. After all, information is one molecule. Only you increase the intensity by collecting the volume.
Okay, since we are getting late, Dr. Dhara is available for lunch and dinner time also, so one can interact with him. Let's thank Dr. Dhara for a very excellent talk.
Thank you very much.
So now I request Nitika to bring a memento, please. Okay. And I talk.
Welcome.
Thank you, sir.
Okay, now let me invite the next speaker, Professor Karunakar Nanda, Director, Institute of Physics, Bhubaneswar.
Hello. Okay.
So Dr. Nanda research interests are in synthesis of nanostructural materials, gas sensing, catalysis and optoelectronic properties, and he has a lot of awards. Samantha Chandrasekhar Award for year 2006 by Odisha Vigyan Academy, Government of Odisha. Material Research Society of India Lecture Model Battle for year 2010. Japan Society Promotion of Sciences JSPS Fellowship year 2013 and 14. So please, Dr. Nanda.
Yeah.
You have got full total 30 minutes. If you speak 25 minutes, people will ask more questions.
Okay, so what should I do?
25 minutes you can
Okay.
stop. I'll tell you in 5 minutes in advance.
Okay, great. Okay, so first of all, I would like to thank Professor Satpathy actually for inviting me to this conference. Initially, I thought I'm a misfit to this conference, especially when you talk about laser. But then he said that no, you should speak whatever you have done. So I go back to my postdoc time. Okay, this is the work actually I have done in my own hand. But so far actually I have understood few things and I have not understood many things also. So as you see, first of all, laser-assisted aerosol route to synthesize spherical nanoparticles with narrow size distribution. So this topic is quite different from the previous two talks which I heard today. So hopefully, you'll get some information, but maybe boring for some of the audience. But please bear with me. You'll definitely get something new. So what is actually, before I proceed further, so what is the meaning of definition aerosol? So that probably the curiosity comes. So aerosol means a suspension of particles dispersed in air or gas. Just keep this in mind. Then I will proceed further. So these are the contents of my talk. Why should we have spherical nanoparticles? So why do we need a spherical particle? And what are the importance actually when I'm talking about? Okay. So then why narrow size distribution? Then I will briefly discuss few methodologies for spherical and narrow size distribution, and then I'll come to the aerosol route. And I'll discuss also in that what are the importance associated with laser. So why spherical nanoparticles? So whenever we compare some findings, some results, we, in a mind or in theory, we assume that these particles are spherical. And then we try to deduce some of the physical properties. Okay. And as I said, to compare theory and experimental results and deduce some physical parameters correctly or accurately, spherical nanoparticles are required. Otherwise, the value will be erroneous. And then change in properties is much more in zero-dimensional system, basically a spherical particle, compared to one-dimensional system or two-dimensional system. As an example, here energy levels of flattened cube PBS. So basically the height of this lead sulfide flattened cube is smaller than the width. As a result, as you see here, the band gap of 4 nanometer nanoparticle is 5 electron volt. This is basically STM studies. Okay, one can probe individual particle, and the band gap deducted from the STM study is 2.35. Whereas, if you take effective mass approximation that is generally used to understand the size dependency of band gap, so one get actually 1.55 electron volt. So the experiment tells us that the band gap is 2.35 electron volt, whereas theory says it's 1.55. So there is a huge discrepancies. Okay, because 1.55 that assumes the particles are spherical, and that's why the discrepancy comes. So if somebody deduce the effective mass from the size dependent band gap, and especially from the experimental band gap studies, then you use a spherical system. Okay, so that's why one can get, or one gets erroneous value of effective mass. Same thing if you look at properties, the band gap or melting temperature or whatever, the change in properties as I have already mentioned, the properties change will be much more in case of zero-dimensional system compared to OARs or one-dimensional system or two-dimensional systems. Same thing for melting. And also as a consequence, sometimes you get a non-linear behavior. Okay, like we know that the surface to volume ratio is 1/d. So the melting temperature should behave as 1/d, but it sometimes deviates from the linearity. And that probably because of the non-sphericity of nanoparticles. So far actually I gave some example and why you need actually spherical nanoparticles and why so important. Now it comes to importance. So size nano where? Why narrow wire? Narrow distribution. And generally, metal nanoparticles like gold especially must be knowing that gold nanoparticles are used as seed for the growth of nanowires. This is an interesting study if you look at carefully, that the seed nanoparticle is 50 nanometer plus minus 5, 30 nanometer plus minus 3.3, 20 nanometer 2.1. This is the seed of gold nanoparticles, and the nanowires, as you can see here, 93, 30 becomes 43, 20 becomes 39. Okay. But interesting is the standard deviation, basically the width that directly correlates. It is 8.8, 7.9 is 11, 10, 11, 9.5. So basically the distribution, size distribution of the nanoparticles gets translated when you grow the nanowire. And this is how you can see how the importance the narrow size distribution is. And there is another interesting stuff here. If you look at, this is a schematic of the energy level for a individual nanoparticle. And for optical measurement, see for STM, you can basically locate individual nanoparticles and do in STM study and can find out the band gap. But what we do generally, we deposit a film and take the optical absorption spectrum. Okay. So if it is, say for example, narrow size distribution, you can see this kind of features. You can see these humps like behavior. But imagine if you have if a huge size distribution. So in that case, this feature may be lost. Like, if you have narrow size distribution, this feature can be prominent. If you have a wide range of distribution, it will smear out. So we will lose that feature basically. And this feature basically corresponds to this level to this level. And the next one is this to this level if you have two or more. So it's very interesting to have narrow size distribution actually. Okay. So far, so good. We need spherical nanoparticle, especially when we are comparing with theoretical model, and we need narrow size distribution as well. But there is another interesting, problem we can think of is that what's about substrate dependency? Okay, say suppose earlier probably this conference was known as pulse PLD, pulse laser deposition. Okay, so in case of pulse laser deposition, what happens? You vaporize the material pulse, a laser, and the deposit on a substrate. And the morphology of the thin film or nanostructure material what you deposit, that definitely depends on the substrate itself. So if you can have a methodology where you get spherical nanoparticle, you get narrow size distribution, and you get substrate independent nanoparticle. Basically the size and shape both are independent of the substrate. But is it that easy? That's the question. So to get something, you have to lose something. So let's see, to get all these features from one technique, what we have to lose. And if we lose something, then can it be improved or the loss can be minimized? This is the question I'm going to address in the next maybe few minutes. So what is the desired features? Nanoparticles with size as small as possible. Monodisperse nanoparticle. So if you look at literature, if your variation is 10%, say suppose I'm targeting to synthesize 10 nanometer, and I'm getting between 9 to 11, then I can consider it a monodisperse system. It's very difficult to synthesize 10 nanometer means 10 nanometer without any distribution. Sphericity means aspect ratio is exactly 1. Okay, these are the constant experimentalist has. So, the last one is the shape and structure should be independent of the substrate. And the region probably that for TM studies what we do, we deposit the metal on a carbon grid. For optical studies, for band gap evaluation, we deposit on a transparent substrate like glass. For STM studies, we need to have a conducting substrate. And for AFM studies, suppose you want to see, then it has to be a uniform surface, like mica is basically usually taken those days. Okay, so these are the constant we have. So suppose I want to study the optical absorption, so I have to deposit on glass substrate. Okay, and now I have to deposit to know the size on carbon grid. So I have to have a methodology where really my size, shape, crystal structure, everything should be independent of the substrate. Then only I can correlate. Okay, otherwise, suppose that from TM I am getting nanoparticle, but when I am depositing on a glass substrate, maybe the morphology will be different, the size will be different. So I have to have a methodology, okay, and that's my point here. And so then I try to look at what are the techniques actually where we can grow spherical nanoparticles with narrow size distribution. One is the chemical capping methods generally used, and then centrifugation. Okay, you centrifuge, and then basically you collect with time, so that bigger nanoparticles settle down first, so that on the solution, the upper part of the solution, you have a smaller particle, so that can be collected, and in that scenario also one can achieve monodispersity. And there are also reports which have found actually that, as you see here, they are more or less, this is a cobalt nanoparticle on silicon nitride, uniform nanoparticles, but same cobalt nanoparticle I cannot deposit on another substrate. The morphology will be different. Here you can see monodispersity, but if I try to deposit on the other substrate, things will vary. So aerosol route offers the synthesis of monodispersed spherical nanoparticles with size and structure independent of the I don't know what happened. So before I go to the technique, I just discuss, suppose you have a tube furnace. Most of our lab has tube furnace. You take a material with relatively high vapor pressure. Okay, the furnace, see generally in the lab we have furnaces which can go up to 1200 degrees centigrade or so. Okay, so we can handle with these techniques which I am going to discuss in the first few minutes, is that thermally assisted. Okay, then we can go for laser assisted. We should know actually what are the problems we have with thermal assisted. So suppose I have a tube furnace, I take any material like zinc or whatever, gold, silver and whatever, and in this case it is basically zinc and indium, and both sides open basically, so one can get zinc oxide and indium oxides. But you can see different morphology, okay, different morphology and different sizes. Okay. So now what one can do? So this is the way actually, this is the schematic of the experimental setup which gives us monodispersed nanoparticle. What is done here, as you see here, there is a furnace, a tube furnace, and there is a mass flow controller, and this nitrogen flow is introduced through this mass flow controller, and the flow rate is precisely 1.5 SLM, standard liter per minute. Okay, that is the flow rate used by aerosol scientists. Okay, I got a chance to work with some engineers, so I have learned that from them. And here we take the material. You can take silver, gold, lead sulfide, and indium, gallium, or whatever. You can take it. And then, as you see here, there is a radioactive charger. Basically, it's americium or krypton. Okay, and the purpose of this radioactive charger is that, like, if once you vaporize the material and introduce a flow, if you don't introduce a flow, there will be a deposit on the inner wall of the tube. But once you introduce a flow, that vapor gets dragged along with the nitrogen flow. And when they exit from the furnace, they try to form nanoparticles, agglomerates and whatnot. Okay. And from that, how one can produce the size selected particles, this is the question. So then there is a radioactive charger which charges this particle in both ways. It can be positively charged also particle, one can have also negatively charged, it's almost equal distribution. And then there is a differential mobility analyzer. Okay. This is very important, the heart of this setup actually. Okay. Differential mobility analyzer, it classifies the size based on their mobility. So that's the reason you need to charge those particles. Without charging, it's not possible. So to classify the particle or agglomerates, whatever exits from this furnace, okay, is selected based on their differential mobility analyzer. In a next slide, I will describe how it does. And then we have a second furnace, because in this case you may have agglomerates. If you are lucky, you may get compact particle. If you are not, then you get agglomerates. And then you sinter in this furnace and one get actually nice spherical particle. And why you get spherical particle? Because if you look at your PLD, it's a substrate and you bombard atoms. Okay, and on the surface it is get deposited. So more or less you expect a kind of a hemispherical particle. In this case, the vapor comes from all the directions. So basically uniform. And that's the reason it is expected to have spherical particle. And then an electrostatic precipitator is used to collect, because they are charged particle, you just apply a voltage and gets deposited. So the particle itself will get deposited on any kind of substrate. So that's the key actually. On any kind of substrate, you have a electrostatic precipitator, you put your substrate and gets deposited. What are the other advantages in this case? You can count the number of particles you are depositing per second. You can have an electrometer or a particle counter, okay. And so per minute or per second, per hour, how many particles you are depositing, and you can look out also with experience, okay. You can see the area of deposition. So you know the area of deposition, you know the particle size, you know the rate of deposition. So for one monolayer, how long it will take, you can estimate. You can find out. Okay. And the beauty of this also that you can have n monolayer without compromising with the size of the nanoparticle. But there are methods. Let me remind you here that there are methods like, at least I know, electrochemical deposition. First monolayer, you have a smaller particle. If you try to deposit the second monolayer, or if you try to increase the thickness, the particle size gets bigger and bigger. Okay, but in this case, that problem is not there. So one can handle, more or less the materials which have high vapor pressure. And these are the basically a differential mobility analyzer. This is the photograph of this, and it is written nano DMA because this DMA is specifically designed. Basically, the dimension is such that it can classify only nanoparticle. Okay, so polydispersed aerosol means you have the particle, the flow exits from the first furnace, because you have a lot of distribution. Basically, the distribution is from 100 nanometer to 1 nanometer up to 100 nanometer, or even more. So that's why it's called polydispersed aerosol. And here it's called monodispersed aerosol, basically more or less size classified. So what happens, you introduce the polydispersed aerosol here and it gets distributed here. It comes like this and enter this chamber. And there is a seed air, basically it's 15 SLM. So that ratio is 1.10. So if it is 1.5, this should be 15. So 15 SLM of nitrogen is introduced and then they interact here in this chamber like this. So polydispersed aerosol enter here, sheath air 15 SLM enter here and come like this. And when you apply a voltage to the DMA, especially to the center electrode, what happens? So suppose I apply a positive bias, then negatively charged particle gets attracted to the center. Okay. But on the other hand, there is a flow, it's a huge flow, 15 SLM. So the electric field will try to drag the particle towards the center, whereas this flow, the strong flow, that drags along with it. In that scenario, the resultant path is like this. The resultant path will be like this. So the particle smaller than, say suppose I have to choose, say for example 10 nanometer, I have to apply a bias or voltage of 850 volt. So what happens in this scenario? Particle size smaller than 10 nanometer, that gets deposited here. The drag force will be less effective, and if the particle size is much bigger than 10 nanometer, that gets dragged. So, and here there is a slit, so only 10 nanometer comes out. Suppose now I want to choose 5 nanometer, so then I have to apply 200 nanometer, 200 volt.
20 minutes over, 10 minutes left.
Okay. So if I apply 200 volt, then only say 5 nanometer particle will come here. 5 particle smaller than that will get deposited here. Nanoparticle bigger than 5 nanometer gets dragged. So as I said, there is a compromise here. You have to gain something, you have to lose something. Here you are discarding all the materials except 5 nanometer. So basically the material loss is huge. Okay. But so there are electrostatic precipitator, and here the size distribution is log normal. Okay. So I will skip this because of time constant. So these are the basically why you need a second furnace. What happens? This is the results when you just don't sinter it in the second furnace. After DMA you classify it. Okay. So that mobility equivalent diameter is 50 nanometer. When you choose, you will have this kind of structure. But then when you sinter it in the second furnace, at 673 you get this kind of morphology, 748 you can get this kind of morphology, and 773 you can see this one. So in this case, the optimum temperature of sintering is 748 K. If you increase further, the material evaporates. In the second furnace, the material evaporates and you get smaller particles. Okay. So you have to choose depending on the diameter, the mobility equivalent diameter, you have to optimize your furnace temperature, second furnace temperature. And the particle are monodisperse is, the sigma is, the standard deviation is 1.12. Same thing, size distribution is of silver nanoparticles, as you see here, it varies from 1.12 to 1.16. But how do you know that this is spherical? This is the question again. Okay. So we try to address this in two ways. One is that we took the gold nanoparticle in this case on a TM grid and then try to rotate it. Okay. But we could go up to 36 degree if I remember. Okay. And then we use this formula. Okay. And this is d theta basically, whatever you get, and then we found that 8.8, see that like normal incidence 8.8, and if you rotate it to, assuming that the size is different, see if it is perfectly spherical, the diameter as well as the height should be the same. But because there is a slight difference here, you can see, I cannot claim that it's exactly spherical, but it's close to spherical, nearly spherical. Okay. And also you can see that these are more or less monodisperse. This is a gold nanoparticle, high resolution. This is another one. What we did in the previous case, we tilted it, but we have done another studies also where we have shown that actually, like we took the diameter from the TM and height from AFM. And as you can see here, the diameter is around 21 nanometer from the TM, and the height is around 20 nanometer. And because we didn't take this lateral dimension from AFM, because this will be much more compared to the height. So from this also we concluded that actually that diameter is more or less equal, close to height. And of course, depending on your requirement, you can here, before the second furnace or a sintering furnace, you can pass oxygen, arsine, ammonia, phosphine and all, and you start with gallium, indium and zinc, you can get different compounds. Okay, gallium arsenide, gallium nitride, gallium phosphide, gallium oxide, indium oxide, zinc oxide, all these combinations one can get. But there is a catch here. Basically, you discard other particle, only you are selecting that particular whatever your requirement is there. So I'll come to the last part. So pros and cons. Nanoparticles are nearly monodisperse and nearly spherical, independent of the substrate, because the particle, the synthesis takes place or the particle formation takes place before we deposit, and can be deposited by electrostatic precipitation, and ideal for the correlation between particle size and the properties. But yield is very low. Metals with high vapor pressure can be handled. Okay, like suppose silicon. This cannot be, because the furnace can go up to 1200 or the one we have. Okay, so and also the materials that vaporize stoichiometrically can only be synthesized. Lead sulfide. Lead sulfide vaporizes stoichiometrically. But suppose you take CDS, it will not vaporize stoichiometrically. So in that case, your starting material is CDS, the target material will be CDS, but the result will be different. You will have more cadmium probably. So then that comes laser actually. So how can the shortfall be addressed? Solution is laser assisted vaporization. So in this case, the technique, the diagram if you look at, is more or less similar. What we have replaced? We have replaced the first furnace with a chamber with a rotating target, and we have a laser. Okay, and then as you see here, we have not used the radioactive source. Okay, it's not that we have not done the experiments with radioactive source. We have tried also with radioactive source americium, and without, we didn't find substantial difference. So that means the laser is sufficient to vaporize the material as well as produce charged particle. And then there is another thing also. We had our own DMA, low pressure. And why low pressure? Because I'll come to that. And then there is a second furnace. Because if you have amorphous structure or agglomerated structure, then that can be sintered here to get compact particles. And then we have electrostatic precipitator where you can collect the nanoparticle. So neither radioactive charger nor mass flow controller. That is one of the things. See, the mass flow controller doesn't work properly when you evacuate the system. So what we did, instead of mass flow controller, we used critical orifice. And the critical orifice, the flow depends on the diameter of the orifice.
Last 2 minutes.
Okay. Okay. So these are the DMA actually what I have designed. That is called cylindrical differential mobility analyzer, and this is a radial differential mobility analyzer which we produced actually 10 years before. So this is indigenous, I say, because when I was doing my postdoc I had developed this. Okay, but as you see, I have plenty of results also still I have to publish. I don't have time, but this we could publish in 2014. So though my postdoc I finished before 2003 actually. And this is a different design altogether, and we are very successful to do this. I'll skip this one. This is critical orifice, and these are the results like you see here. As I am reducing the pressure. So this is, say, for example, for 1000 millibar, this is 400, and this is for 30 millibar. So as I am reducing, because I couldn't reduce the pressure further because it is limited by the 1.5 SLM, that flow I am introducing. Okay, so I cannot go beyond 30 millibar, but the beauty of this is that as I am reducing the pressure with same laser fluence, I am getting more number of, smaller particles. That's the beauty of this. Okay. Whereas, if you lower the pressure in case of thermal assisted route, then what happens? The yield becomes much lower. Because when, see where is in the tube furnace, you have the tube and the thermometer is outside the tube. And when you are introducing a large flow or trying to evacuate, then what comes, the effective temperature goes down inside, because your thermometer is outside, but the material which is vaporizing is inside. Okay. So if you increase the flow or lower the pressure, the effective temperature goes down, so the amount of material that vaporizes also goes down, so the yield comes down actually in case of thermal assisted one. But in case of assisted one, irrespective of, it is basically independent of the pressure. But why then you have more number of smaller particles? Because the resistance time, lower the pressure, the resistance time from the chamber to the DMA, that is going down. And that's the reason we have more number of smaller nanoparticles. And we have actually synthesized lot of material using this. And as you see here, as I increase lower the pressure, the concentration also increases. Say for example, when the pressure was around 200, the concentration is very low, but as I am reducing to 30 millibar, it's 10 to the power 4 times. So more number of nanoparticles I am able to deposit. Okay. So that's the beauty of this laser system. And here the iron nickel nanoparticle, we have grown. We tried to actually deposit gallium nitride also. Okay. And then there are reports also, like this is not ours, like PZT nanoparticles, then silicon nanoparticles, okay, which were not possible without laser actually. Okay, so yield is very high. Smaller particles can be obtained by lowering the pressure. No requirement of radioactive source, but the laser adds to the cost. So basically, as I said, sometimes you have to look at the money you have and go for the system. To conclude, so aerosol routes offer the synthesis of spherical nanoparticles with narrow size distribution, and it's independent of the substrate, independent of the thickness, and the particle density can be monitored by knowing the deposition area and deposition rate. So one can actually find out in this case how much nanoparticles you are depositing per minutes or per second. So laser can be used as synthesis of variety of nanomaterials, and you can have actually gallium nitride or any complicated system actually using this one. Okay. So with you, I would like to thank all of you. And one of the interesting basically information one can take from here is that one can DMA in environmental research. Okay. This is basically in Japan, there is a study. This is weekday and this is Sunday. You can see in the weekday a lot of particles in the atmosphere, but on Sunday you have less number of particles. So using differential mobility analyzer, one can do this kind of study also. Okay. So thank you for your kind.
Thank you, Professor Nanda. Now that this talk is open for 1 or 2 questions. Or maybe you can, if no more questions, maybe you can interact with him during the lunch time. So let us thank Professor Nanda for a very nice device which you can select nanoparticle based this thing.
So now I request Nitika to bring a memento, and I request the chair to present the memento to our speaker.
Okay,
Thank you, sir.
Without wasting time, let me invite third speaker, Dr. Prahlad Kumar Barua on the stage. Dr. Barua's research interests are in laser matter interaction, pulse laser ablation, plasmonics, laser micromachining, energy and biomedical applications, and he has been recipient of Marie Curie Fellowship by European Commission, CRB ITS Young Scientist, early career professional member of SPI Optica. So you have total 30 minutes, better to speak for 25 minutes,
yeah,
so people can ask us questions.
Sure. Pointer. Okay. So good afternoon everyone. I can understand all of you must be very hungry now. But I
don't think people are hungry. People have enough breakfast and they have enough for this thing.
Okay.
Anyways, I'm going to skip the lunch also.
So I am standing between you and the lunch. So thank you so much, sir, for the nice introduction, and thanks to the organizers for giving me this opportunity. So yeah, I'll be talking about the role of liquid and the external fields in advancing PLAL for controlled nanoparticle synthesis. So what this PLAL stands for, that is pulse laser ablation in liquid. Thing again I'll be talking about. So this is the outline of my presentation. So I'll be giving a brief introduction, and then I'll be explaining what are the benefits of this pulse laser ablation in liquid technique is, and what controls the properties of the nanoparticles synthesized via this technique, and wherein I'll be focusing on two particular aspects, like one is the effect of the confining liquid, as my title suggests, and of course, the effect of the external fields. And then some of the results I'll be discussing. Yeah. So first of all, we need to understand what laser ablation is. So this being a very focused audience, so I'm sure all of you are aware, but still, let me just say that, when a high power laser beam is focused onto a target, so once the ablation threshold is crossed, so you have the ablation, the removal of the species, ablated species that you have here, and then along with that, there may be certain cracks that may occur on the surface as well, and this process is used in many applications. Like so, if you see in materials processing and fabrication, like we do, so we have thin film deposition in the form of pulse laser deposition, then nanoparticle synthesis, which I work on, surface texturing also, and then in biomedical applications, laser ablation is used for laser surgery, dental applications, and in LIBS, that is laser-induced breakdown spectroscopy, in medical diagnostics as well. And talking about environmental applications, so the materials synthesized using PLAL are used in pollutant degradation and carbon capture, etc. And these materials are also synthesized by this technique, can also be used for energy applications. So like in hydrogen generation and thin film solar cells, etc. And then finally, in industry also, this the material synthesized by this technique has got a lot of applications like laser cleaning, defense and security. There also these materials can be used. So today I'll not be focusing on the applications much. In fact, although we work on surface enhanced Raman scattering and laser induced breakdown spectroscopy, etc., but I'll rather be focusing more on the pulse laser ablation in liquid, the technique itself. So this is the mechanism of pulse laser ablation in liquid. So here, as there is liquid, so a high power laser beam is focused using a set of optical components onto a target that is immersed in liquid. So what happens once the high power laser beam hits the target, so the plasma formation will take place. And in the next step, what happens is that the plasma expansion and shock wave emission will take place. This plasma is getting expanded. And since because of the confinement effect, the shock waves are formed. And then finally what happens once the plasma cools down, so there is the shrinking of the plasma, and then because of the presence of the liquid around, so we have the formation of cavitation bubbles here. And the nucleation of all the ablated species within the bubble takes place in the cavitation bubble itself. In the next step, so the cavitation bubble also expands, and then within the bubble, as I already said, the nucleation had started, so we have the nanoparticle formation taking place. And then the particles are still within the bubble, and in the next step, the cavitation bubble also collapses, and because of the ambient pressure and everything, so then the particles that are within the bubble, that get released into the solution itself. So final product that we have is the colloidal solution of nanoparticles that we have here. Yeah. So next, what are the advantages of this technique? So first of all, this is an environment friendly technique because unlike the chemical synthesis routes, so we don't necessarily have to use any chemicals for the synthesis in this process. Then flexibility in terms of size and types of nanomaterials. So depending on, suppose my target is copper, I get copper nanoparticles or copper oxide nanoparticles. If I use a gold target, I get gold nanoparticles, and so on and so forth. Even alloy nanoparticles can also be synthesized if I use a target which is in alloy one. So then wide range of nanoparticles are already covered. So then the experimental setup is very simple, and we can synthesize stable, pure and ligand-free particles, and it is cost-effective one. Of course, bearing the initial investment on the laser system, there is hardly we need to invest anything in. And here, most importantly, we don't need any vacuum chamber or anything because the ablation or the synthesis is taking place in a small cuvette or a small glass, jar, you can say, you can use that. Now, what are the key factors that affect this kind of a synthesis process? So these are the, some of the parameters that we can play around with. So one is your, laser parameters that we have. So laser wavelength you can play with, pulse duration, the fluence and the repetition rate. Then the liquid environment itself, like you can use different kinds of liquid, so which will affect the properties of the nanoparticles that we have. And then the plasma and the bubble dynamics, because the cavitation bubble, shock wave, etc., they play a huge role. In fact, everything is getting determined by them only, right? And then the target material. So elemental composition and the surface characteristics will depend on the nanoparticles that we have. And again, the external fields, like if you use electric field and magnetic fields, so they are going to affect the properties of the nanoparticles that are there. So as promised in the title of my presentation, so I'll be focusing more on, in fact, only on the two aspects here. First is the liquid environment, and the second is the effect of the fields. So first, let us show you some of the results of confining liquid. So if you look here in one of our previous works, so we had observed that if we carry out the ablation in a distilled water, so there what happens, we get oxidized nanoparticles, right? But then if the same process is carried out in oxygen deficient solvents like some organic solvents, etc., so you see that there is a carbon encapsulation. So, and that helps us to get core shell kind of a structure that we have. And this we have verified using transmission electron microscope. And as you can see, the graphitic carbon phase is obtained at the periphery. So this ensures that, or it proves rather, that we have core shell kind of a nanostructure. So carrying on from there, so my PhD student first, Kawil, is sitting here. So what we did was, so we tried to vary the viscosity or we chose the liquids having different viscosities, and that is what we have focused on in this work. So our liquids were distilled water and propylene glycol and glycerol, these liquids we chose, and then we carried out the ablation in this normal kind of a setup of PLAL. So laser pulses there, and using optical components we have focused the beam onto this target, that is immersed in liquid, and the liquid here is either distilled water, propylene glycol or glycerol. And these were the laser parameters that we have used. The wavelength was 1064 nanometer, and the focal length of the focusing this lens is around 20 centimeter, and ablation time was 15 minutes. Liquid thickness that is above the target was around 4 mm, and energy we kept on changing. So here in this case it was 32 millijoule. And upon carrying out the SEM analysis, we saw that these were the particles that we got. So this was in distilled water, this was in propylene glycol, and this was in glycerol. And from these images we found the size distribution, as you can see here. So for the case of distilled water, the size was coming to be around, average size was 35 nanometer, whereas in the case of propylene glycol and glycerol, we found higher or bigger size nanoparticles, the average ones. So this was the kind of pattern that we observed. So the size of the nanoparticles had increased with the increase in the viscosity of the liquids. Now the question is, how do we explain these results, right? So what we did was, first important thing that we need to do is we need to understand the dynamics associated with this process, right? So we need to understand, that is very important, and for that there are a couple of techniques. There are in fact many techniques, but we have focused on two particular techniques. So one being the beam deflection setup. So what this setup or the technique, how it works, basically you have this, the same setup that you have. So you have a, pump laser beam that comes and, ablates the target, and the nanoparticles are getting here, this is the cavitation bubble formation. And then we send a probe beam. So now depending on the refractive index change that is taking place because of the formation of the cavitation bubble, shock waves, etc. So there will be a modulation in the signal that is observed in the photodiode here. And by analysis of those signals that we get, so we can find a lot of information about the pressure and temperature within the bubble itself. And this is the actual one of the setups that I had made earlier. So as you can see, so this is the pump beam that I was showing in the schematic diagram, probe beam, sorry. And then to give you some more idea, so the deflection, the normal laser pulse, it is like this. So this is not quite very nicely visible. And then this is the modulation that we get. So this modulation, the first dip, it signifies the primary cavitation bubble that we have. And so next one is the secondary cavitation bubble. So these are the bubble formations that we have. And then if you see here, so suppose you are getting a peak like this. So any small peak is usually, it is attributed to the shock waves that are formed. And if you see, if I consider two particular locations like x1 and x2, and if I take the signals corresponding to these, you will see that there is a time delay, right? And from this distance and the time delay, we can easily find the shock wave velocity, so that will give you a nice idea. And then another technique that we use is the shadowgraphy technique. This is another simple one, but here we either use a CCD camera or a ICCD camera. So this is the probe beam, so which is usually expanded for better viewing. So either using a microscopic objective or a beam expander you can use, and then this region is illuminated, and finally it is imaged onto the sensor of the CCD camera that we have. And this is the actual setup that we have. Now coming back to the results that we had obtained, so for the viscosity of the liquids, so what we observed using the beam deflection technique was that, so we could find the, these were the dips in distilled water, glycerol and the propylene glycol. So we found that the time of collapse. So what is this time of collapse? So 2 Tc. So this is the time of 2 Tc is the total time that we have for the primary bubble, and Tc being the time of collapse of the primary bubble. So from the information obtained from all the three cases, what we have done is we could find the So there is a relation that gives you the, that relates the time of collapse and the maximum bubble radius. So from here, because we know the time of collapse, and these are the known values for the liquids that we have taken, so I can easily find the R max from this, right? And then from here, yeah, so this is the time of collapse I already said, and rho is the density of the liquid, P infinity is the ambient pressure, and PV is the vapor pressure that we have taken. And from this TC that we observed using the optical beam deflection, we have found the maximum bubble radius from here. And there is another model, a very well-known fluid dynamical model, that is the Gilmore model, and by fitting in all the parameters that we have, the radius, maximum radius and the radius, the time with time how the, the radius of the bubble changes, we can find the temperature or pressure within the bubble itself. And we have observed that as the radius of the bubble decreases, and the pressure will, normally it will increase. So more pressure inside the bubble induces nucleation of large particles on the seed ions inside the bubble, and this prevents basically the fragmentation of the nanoparticles, and which leads to the formation or the synthesis of higher sized nanoparticles. So just, in order to, understand this in a better way, so if you can see, so this is what we have got. So these were the, higher viscous liquids, and these are the bubble, cavitation bubble sizes. So what we observed was the size of the bubbles was more in the case of the liquid having lower viscosity. So from here, what we can conclude is basically that the average size of the nanoparticles which we found using the same images, so those were around 35, 52 and 65 respectively for the liquids that we have chosen, and the increase in nanoparticle size is due to the reduction in the cavitation bubble and also its period of oscillations that we could see from the optical beam deflection technique itself. Now coming to the next effect, so that is your another very important aspect is that, so we can change the properties of the nanoparticles using external fields, right? So you can use magnetic fields and also electric fields. So in our case, the one that I'm going to show here, we have applied external electric field to the very process that we have synthesized here, right? So this is in the scenario that we have, without electric field. So there are, this is very plain and simple, but upon application of the electric field, the electric field is symmetric in this particular region, so that we have ensured using some COMSOL simulations as well. So here the setup remains the same, only thing we have incorporated the copper electrodes that is there, and this is the plasma expansion direction, and this is the electric field direction as is shown in the schematic diagram. So some of the parameters that we have, so again in this case also we have used silver target, and the liquid we used here we have kept it simple, the distilled water that we took, and the wavelength of the laser is 1064, energy around 78 millijoule, and the focal length of the lens is around 20 centimeter, liquid volume was around 2.8 milliliter, and the liquid thickness again in this case also we kept at 4 mm, and the duration of ablation we kept in this case as 5 minutes only. And again regarding the electric field parameters that we have, so the scheme was again the simple positive negative scheme that we have, and we have used copper target as you can see here, and the distance between the electrodes is 32 mm, and we have used high power power supply, high voltage power supply, and the direction as I have already shown in the schematic, so it is like this. So we have used electric field values or intensity of 100 volt per centimeter, 500 volt per centimeter, and 1000 volt per centimeter. So these are quite high values of electric fields that we have used, and this is the actual setup that we have, which this setup was made at Physical Research Laboratory, Ahmedabad. We also had good support from our collaborators there at PRL Ahmedabad. Yeah. So upon the application of the electric field, so these were the nanoparticles that we got. So as you can see, mostly they were spherical, but again for higher electric fields, some other shaped particles were also observed. Now, on drawing the histograms of the particle size, what we could see is that in the case of when no electric field is applied, So the average size of the nanoparticles was around 30 nanometer, and while on application of the electric field, we saw that the average size decreased to 19 nanometer, and which kind of remained the same at 500 as well as 1000. But the more important thing here was that there was a drastic reduction in the particle size distribution that we observed in this case. So the distribution narrows down by around 4 to 5 times, as you can see from here, right? And the nanoparticle size also reduces by around 1.4 to 1.7 times, which although is not very significant, not much significant, but the reduction in the size distribution is very much significant. And we all know, like in the previous talk also, we heard about how getting narrow size distribution particles is very important. And this being a very easy technique, so we can easily synthesize this, but in the market when you go to buy such nanoparticles, they are of very high cost. So this is again the setup clearly shown here. So this is the electrodes that we have, and for imaging in this case we use ICCD camera, and the gain was kept at 500, and it was done in single shot mode, and the triggering was done using the digital delay generator that we have, and the gate width was fixed at 1 microsecond. So some of the images that we captured using this technique, so all these this was at 0 volt per centimeter. So I'm just showing the images, although without talking about the size of the bubbles, it does not give you much information, but that is something that we have done. So this was at 100 volt per centimeter, and this was at 500 volt per centimeter, and this is at 1000 volt per centimeter. So from the images, what we did was we obtained the size of the bubbles with respect to time. So here, this was the variation in the bubble size that we could see, and this is for the ones that we did using the electric field that we applied. So maximum bubble size was found to be 1.96 in the case of no electric field, whereas it was found to be higher in the case of electric fields that we applied. So we found that the Rmax increases, that means the maximum bubble radius increases in the presence of electric field, and there is negligible change in the maximum bubble radius because there is not much change. So with the increase in the electric field that we have. From the bubbles, what we have found out, bubble size, so using again the Gilmer model, what we have found the pressure within the bubble. So from that pressure, you can see this is the bubble pressure which is in megapascal range. So you see that this is the variation again, it will be same as the ones, but just the opposite one. So the bubble pressure, as you can see, so the bubble implodes at lower pressure in presence of electric field. As you can see, the bubble implodes here at 24 megapascal, whereas this value keeps on decreasing as we increase the intensity of the electric field applied. So then comes your, how do we explain the changes that we have observed? So basically it is attributed to the excess electrons from the plasma phase that we have, and which charges the nanoparticles that are within the bubble. And because of this distribution that we have, the nanoparticle surface actually gets, there is an electrostatic interaction, and which leads to a pressure which we call as the electrostatic pressure. And then from here, when the electrostatic pressure exceeds the bubble pressure, the bubble implodes like we saw in the previous case, right? And the nanoparticles are released into the solution. So the electron density of plasma increases in presence of electric field, causing enhancement of the plasma charging effect. There is another effect that is known as your plasma charging effect, because the nanoparticles are basically, it's kind of charging the nanoparticles basically because of the electrons. So due to the excess electrostatic pressure, the bubble will burst at lower pressure, which we again saw in the last slide. So now coming to the conclusion. So what I would conclude is that the PLAL, that is pulse laser ablation in liquid, is a very efficient technique. So you can easily, with a very simple setup, you can use or synthesize all kinds of nanoparticles that are there, and the nanoparticles being in colloidal form, you can easily spin coat it or spray coat it onto any substrate, and that can be used as thin films as well. And the viscosity of the liquid, we saw that it affects the size of the nanoparticles. The external electric field also affects the size of the nanoparticles. And we also observed that the size distribution of the silver nanoparticles synthesized in the presence of electric field, it reduces the size distribution by around 4 times. And finally, we can say that because one demerit associated with pulse laser ablation in liquid is that there is a low yield, right? But again, people are working on it. And one way of doing it is by understanding or by using different kinds of liquids that we have, and also by the application of more confined, like, here we have used electric field, you can use magnetic fields as well, or you can use both simultaneously, that can also be tested. So by doing all these things, and now people are also working on chambers which are having this liquid flow. So by that also the yield of the nanoparticles can be increased. So yeah, I would again like to thank the organizers of this symposium for giving me this opportunity, and special thanks to my PhD student. The results that I have shown mostly was part of his PhD thesis, and the other students and my university PDU and Physical Research Laboratory Ahmedabad as well for providing the necessary facility. Although now we have developed the setup in our institute as well. And this is the group of students that I work around with. So Kavil, he has already completed his PhD. He is doing a postdoc at PRL now. And Rashid is working on laser-induced breakdown spectroscopy, whereas Vaishnavi is working on biomedical applications. And these are some of the UG and PG students which are working on nonlinear optical materials like Z-scan technique and all we have used. So this is all that I have. Thank you so much.
Thank you, Dr. Barua, being well in time. Now people can ask, some question can be asked.
Yeah, my question is related to the electric field assisted generation. You are applying 100 volt, 1000 volts. And so beyond 100 volt, you don't see any improvement.
Yeah.
So my question is, the inherent electric field of the incident laser is in more than megavolts. So how does this small voltage plays an important role?
So in order to see this only, we are not talking about the plasma part. So we are talking about the externally applied confinement that is there. So because of that, there is a lot of change. And that is what we have observed here. So you are talking about the plasma phase one, right? So the electric field because of the plasma. So that will have an effect, but this electric field externally applied one will be affecting the cavitation bubble, which which is there long after the plasma is gone. So that is why this externally applied field has a lot of significance.
Yeah, my question is about the experimental setup, whatever you have used. So typically, whatever I found that you have used some amount of energy with the laser pulse and 3 different liquids.
Correct.
Okay, it is water and 2 organic liquids.
Yes.
So definitely it is true that all liquids will not give same kind of transmission to the 1064 nanometer.
Absolutely.
So if your depth is fixed, if your energy is fixed, and if your liquids are different, then how really you compare the results, which is real actual fluence which is coming of the substrate. So definitely it will change.
It will change, and that is why, okay, you are talking about the fluence there. I got your point. So that we have tried to ensure by keeping the same spot size. And of course there will be some absorption, of course, depending on the liquid, but that we have kind of ignored, and we have mostly considered the bubble dynamics because of the presence of the viscosity more than the plasma phase. The bubble properties will change because of that. So it will not allow the bubbles to expand much because it being a viscous one.
You are using a pulse laser, right?
Correct, sir.
How does the duration of the pulse affect your experiment?
The pulse duration you said?
Yeah.
So here we are using nanosecond laser, and mostly nanosecond lasers will give you better results that we have seen in the literature as well for this particular case, synthesis. But we have not used picosecond and femtosecond lasers. So, but definitely there will be a change. So.
When you do it under organic liquids, anytime have you found any fire hazard?
Yes. So that also
how
we
to
need
get rid of?
So by again adjusting the the layer of the liquid as well as the fluence, that also we need to optimize. Because that I faced a lot of issue during my PhD as well. But that can be easily be solved.
Any more questions? Since there are no more questions, let us thank Dr. Barua for excellent talk.
Now I request the chair to present a memento to our speaker, Dr. Barua. I request Nitika to bring the memento. So as a token of gratitude, we would like to present a memento to Dr. Dixit. So I request Dr. V. Ganeshan, ex-director, UGC DAE CSR and Dean, Research Affairs, Medical University, to present a memento to Dr. Dixit. I request Savestina to bring the memento. Thank you, sirs. Now it is time for lunch.
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EPI 2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging. In particular, it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter-long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In the nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It is easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
near, mid-wave, and long-wave IR, and builds all kinds of detectors, including InGas, INSBE, and SLS. The Niceville team also develops software that is completely tailored to R&D and science professionals. The FLIR Research IR software works seamlessly with all FLIR R&D and science cameras that allows live viewing and provides detailed analysis of the most complex experiments. In Täby, Sweden, engineers in FLIR's state-of-the-art design, engineering, and production facilities focus both on cooled and uncooled cameras, targeted at the most demanding applications. These cameras offer a highly efficient and cost-effective way to capture accurate temperature data. No other thermal imaging company is as committed to researchers and scientists as FLIR. With its dedicated facilities in Sweden and the US, FLIR continues to be the industry leader in cutting-edge infrared technology for R&D and science. You can count on it.
The TPX3 cam from Amsterdam Scientific Instruments is a pinnacle innovation in ultra-fast imaging detector technology. At its core, the detector features a photon-counting hybrid active pixel sensor based on the advanced Timepix3 ASIC developed at CERN. Unlike slower frame-based digital sensors, the TPX3 cam operates using continuous event-driven readout. Each sensor pixel works like a precision stopwatch with an ultrafine time resolution of 1.56 nanoseconds. Activated pixels simultaneously record both the event time of arrival and response duration, or time over threshold, processing up to 80 million hits per second at an effective frame rate exceeding 500 MHz. Individual pixel responses are intelligently filtered by signal intensity and pixel grouping to afford noise-free detection and remarkable contrast. The TPX3 cam is flexibly formatted to detect photons, electrons, neutrons, and molecular ions. Configured for velocity map imaging spectroscopy, the TPX3 cam captures time-resolved images of gas phase reaction dynamics at exceptionally high repetition rate. Combining the TPX3 cam with an image intensifier enables single photon detection for versatile applications in quantum optics, neutron imaging, and fluorescence lifetime microscopy. Dedicated device software provides an intuitive acquisition control interface and data processing workflow. Users are also offered a robust API package for the freedom to customize data management and device operations using popular language libraries. Amsterdam Scientific Instruments' premium detector solutions empower researchers across the world to see beyond limits with unprecedented speed and accuracy. To find out how you can use the TPX3 cam in your research, contact our experts at info@amsins.com.
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EPI 2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging. In particular, it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter-long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In the nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It is easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
Today, thermal imaging is more accessible and affordable than ever. More and more professionals rely on FLIR's wide range of cameras to reveal invisible heat issues and to capture valuable temperature data. Our own innovation, development, and manufacturing capabilities give FLIR the agility and efficiency to produce such a complete line of thermal imagers and to do it so economically. Volume cameras can be useful in the world of R&D and science. But when it comes to the fine points, researchers and product developers demand the highest level thermal imaging performance, the kind FLIR science cameras are famous for. They need technology that captures high-speed thermal events in high resolution and with the most reliable results to help discover new phenomena, test new developments, and prove findings. They need to record detailed thermal distribution and variations in real time to measure heat patterns, dissipation, and other critical temperature factors. For years, FLIR has been committed to developing thermal imaging cameras that advance research and development projects worldwide. We still are today, with dedicated production and R&D facilities in Sweden and Florida. The FLIR Niceville facility is fully immersed in the design, engineering, and production of cooled cameras. Here, FLIR creates cameras for all wavebands, including near, mid-wave, and long-wave IR, and builds all kinds of detectors, including InGas, INSBE, and SLS. The Niceville team also develops software that is completely tailored to R&D and science professionals. The FLIR Research IR software works seamlessly with all FLIR R&D and science cameras that allows live viewing and provides detailed analysis of the most complex experiments. In Täby, Sweden, engineers in FLIR's state-of-the-art design, engineering, and production facilities focus both on cooled and uncooled cameras, targeted at the most demanding applications. These cameras offer a highly efficient and cost-effective way to capture accurate temperature data. No other thermal imaging company is as committed to researchers and scientists as FLIR. With its dedicated facilities in Sweden and the US, FLIR continues to be the industry leader in cutting-edge infrared technology for R&D and science. You can count on it.
The TPX3 cam from Amsterdam Scientific Instruments is a pinnacle innovation in ultra-fast imaging detector technology. At its core, the detector features a photon-counting hybrid active pixel sensor based on the advanced Timepix3 ASIC developed at CERN. Unlike slower frame-based digital sensors, the TPX3 cam operates using continuous event-driven readout. Each sensor pixel works like a precision stopwatch with an ultrafine time resolution of 1.56 nanoseconds. Activated pixels simultaneously record both the event time of arrival and response duration, or time over threshold, processing up to 80 million hits per second at an effective frame rate exceeding 500 MHz. Individual pixel responses are intelligently filtered by signal intensity and pixel grouping to afford noise-free detection and remarkable contrast. The TPX3 cam is flexibly formatted to detect photons, electrons, neutrons, and molecular ions. Configured for velocity map imaging spectroscopy, the TPX3 cam captures time-resolved images of gas phase reaction dynamics at exceptionally high repetition rate. Combining the TPX3 cam with an image intensifier enables single photon detection for versatile applications in quantum optics, neutron imaging, and fluorescence lifetime microscopy. Dedicated device software provides an intuitive acquisition control interface and data processing workflow. Users are also offered a robust API package for the freedom to customize data management and device operations using popular language libraries. Amsterdam Scientific Instruments' premium detector solutions empower researchers across the world to see beyond limits with unprecedented speed and accuracy. To find out how you can use the TPX3 cam in your research, contact our experts at info@amsins.com.
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EPI 2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging. In particular, it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In the nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box. No installation by technicians is needed, and it comes with a pre-installed software. It's easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
Today, thermal imaging is more accessible and affordable than ever. More and more professionals rely on FLIR's wide range of cameras to reveal invisible heat issues and to capture valuable temperature data. Our own innovation, development, and manufacturing capabilities give FLIR the agility and efficiency to produce such a complete line of thermal imagers, and to do it so economically. Volume cameras can be useful in the world of R&D and science. But when it comes to the fine points, researchers and product developers demand the highest level thermal imaging performance, the kind FLIR science cameras are famous for. They need technology that captures high-speed thermal events in high resolution and with the most reliable results to help discover new phenomena, test new developments, and prove findings. They need to record detailed thermal distribution and variations in real time to measure heat patterns, dissipation, and other critical temperature factors. For years, FLIR has been committed to developing thermal imaging cameras that advance research and development projects worldwide. We still are today, with dedicated production and R&D facilities in Sweden and Florida. The FLIR Niceville facility is fully immersed in the design, engineering, and production of cooled cameras. Here, FLIR creates cameras for all wavebands, including near, mid-wave, and long-wave IR, and builds all kinds of detectors, including InGas, INSBE, and SLS. The Niceville team also develops software that is completely tailored to R&D and science professionals. The FLIR Research IR software works seamlessly with all FLIR R&D and science cameras that allows live viewing and provides detailed analysis of the most complex experiments. In Täby, Sweden, engineers in FLIR's state-of-the-art design, engineering, and production facilities focus both on cooled and uncooled cameras, targeted at the most demanding applications. These cameras offer a highly efficient and cost-effective way to capture accurate temperature data. No other thermal imaging company is as committed to researchers and scientists as FLIR. With its dedicated facilities in Sweden and the US, FLIR continues to be the industry leader in cutting-edge infrared technology for R&D and science. You can count on it.
The TPX3 cam from Amsterdam Scientific Instruments is a pinnacle innovation in ultra-fast imaging detector technology. At its core, the detector features a photon-counting hybrid active pixel sensor based on the advanced Timepix3 ASIC developed at CERN. Unlike slower frame-based digital sensors, the TPX3 cam operates using continuous event-driven readout. Each sensor pixel works like a precision stopwatch with an ultrafine time resolution of 1.56 nanoseconds. Activated pixels simultaneously record both the event time of arrival and response duration, or time over threshold, processing up to 80 million hits per second at an effective frame rate exceeding 500 MHz. Individual pixel responses are intelligently filtered by signal intensity and pixel grouping to afford noise-free detection and remarkable contrast. The TPX3 cam is flexibly formatted to detect photons, electrons, neutrons, and molecular ions. Configured for velocity map imaging spectroscopy, the TPX3 cam captures time-resolved images of gas phase reaction dynamics at exceptionally high repetition rate. Combining the TPX3 cam with an image intensifier enables single photon detection for versatile applications in quantum optics, neutron imaging, and fluorescence lifetime microscopy. Dedicated device software provides an intuitive acquisition control interface and data processing workflow. Users are also offered a robust API package for the freedom to customize data management and device operations using popular language libraries. Amsterdam Scientific Instruments' premium detector solutions empower researchers across the world to see beyond limits with unprecedented speed and accuracy. To find out how you can use the TPX3 cam in your research, contact our experts at info@amsins.com.
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EPI 2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging. In particular, it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter-long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In the nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It's easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
Today, thermal imaging is more accessible and affordable than ever. More and more professionals rely on FLIR's wide range of cameras to reveal invisible heat issues and to capture valuable temperature data. Our own innovation, development, and manufacturing capabilities give FLIR the agility and efficiency to produce such a complete line of thermal imagers, and to do it so economically. Volume cameras can be useful in the world of R&D and science. But when it comes to the fine points, researchers and product developers demand the highest level thermal imaging performance, the kind FLIR science cameras are famous for. They need technology that captures high-speed thermal events in high resolution, and with the most reliable results to help discover new phenomena, test new developments, and prove findings. They need to record detailed thermal distribution and variations in real time to measure heat patterns, dissipation, and other critical temperature factors. For years, FLIR has been committed to developing thermal imaging cameras that advance research and development projects worldwide. We still are today, with dedicated production and R&D facilities in Sweden and Florida. The FLIR Niceville facility is fully immersed in the design, engineering, and production of cooled cameras. Here, FLIR creates cameras for all wavebands, including near, mid-wave, and long-wave IR, and builds all kinds of detectors, including InGas, INSBE, and SLS. The Niceville team also develops software that is completely tailored to R&D and science professionals. The FLIR Research IR software works seamlessly with all FLIR R&D and science cameras that allows live viewing and provides detailed analysis of the most complex experiments. In Täby, Sweden, engineers in FLIR's state-of-the-art design, engineering, and production facilities focus both on cooled and uncooled cameras, targeted at the most demanding applications. These cameras offer a highly efficient and cost-effective way to capture accurate temperature data. No other thermal imaging company is as committed to researchers and scientists as FLIR. With its dedicated facilities in Sweden and the US, FLIR continues to be the industry leader in cutting-edge infrared technology for R&D and science. You can count on it.
The TPX3 cam from Amsterdam Scientific Instruments is a pinnacle innovation in ultra-fast imaging detector technology. At its core, the detector features a photon-counting hybrid active pixel sensor based on the advanced Timepix3 ASIC developed at CERN. Unlike slower frame-based digital sensors, the TPX3 cam operates using continuous event-driven readout. Each sensor pixel works like a precision stopwatch with an ultrafine time resolution of 1.56 nanoseconds. Activated pixels simultaneously record both the event time of arrival and response duration, or time over threshold, processing up to 80 million hits per second at an effective frame rate exceeding 500 MHz. Individual pixel responses are intelligently filtered by signal intensity and pixel grouping to afford noise-free detection and remarkable contrast. The TPX3 cam is flexibly formatted to detect photons, electrons, neutrons, and molecular ions. Configured for velocity map imaging spectroscopy, the TPX3 cam captures time-resolved images of gas phase reaction dynamics at exceptionally high repetition rate. Combining the TPX3 cam with an image intensifier enables single photon detection for versatile applications in quantum optics, neutron imaging, and fluorescence lifetime microscopy. Dedicated device software provides an intuitive acquisition control interface and data processing workflow. Users are also offered a robust API package for the freedom to customize data management and device operations using popular language libraries. Amsterdam Scientific Instruments' premium detector solutions empower researchers across the world to see beyond limits with unprecedented speed and accuracy. To find out how you can use the TPX3 cam in your research, contact our experts at info@amsins.com.
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EPI 2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging. In particular, it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter-long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In the nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It is easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
Today, thermal imaging is more accessible and affordable than ever. More and more professionals rely on FLIR's wide range of cameras to reveal invisible heat issues and to capture valuable temperature data. Our own innovation, development, and manufacturing capabilities give FLIR the agility and efficiency to produce such a complete line of thermal imagers and to do it so economically. Volume cameras can be useful in the world of R&D and science. But when it comes to the fine points, researchers and product developers demand the highest level thermal imaging performance, the kind FLIR science cameras are famous for. They need technology that captures high-speed thermal events in high resolution and with the most reliable results to help discover new phenomena, test new developments, and prove findings. They need to record detailed thermal distribution and variations in real time to measure heat patterns, dissipation, and other critical temperature factors. For years, FLIR has been committed to developing thermal imaging cameras that advance research and development projects worldwide. We still are today, with dedicated production and R&D facilities in Sweden and Florida. The FLIR Niceville facility is fully immersed in the design, engineering, and production of cooled cameras. Here, FLIR creates cameras for all wavebands, including near, mid-wave, and long-wave IR, and builds all kinds of detectors, including InGas, INSBE, and SLS. The Niceville team also develops software that is completely tailored to R&D and science professionals. The FLIR Research IR software works seamlessly with all FLIR R&D and science cameras that allows live viewing and provides detailed analysis of the most complex experiments. In Täby, Sweden, engineers in FLIR's state-of-the-art design, engineering, and production facilities focus both on cooled and uncooled cameras, targeted at the most demanding applications. These cameras offer a highly efficient and cost-effective way to capture accurate temperature data. No other thermal imaging company is as committed to researchers and scientists as FLIR. With its dedicated facilities in Sweden and the US, FLIR continues to be the industry leader in cutting-edge infrared technology for R&D and science. You can count on it.
The TPX3 cam from Amsterdam Scientific Instruments is a pinnacle innovation in ultra-fast imaging detector technology. At its core, the detector features a photon-counting hybrid active pixel sensor based on the advanced Timepix3 ASIC developed at CERN. Unlike slower frame-based digital sensors, the TPX3 cam operates using continuous event-driven readout. Each sensor pixel works like a precision stopwatch with an ultrafine time resolution of 1.56 nanoseconds. Activated pixels simultaneously record both the event time of arrival and response duration, or time over threshold, processing up to 80 million hits per second at an effective frame rate exceeding 500 megahertz. Individual pixel responses are intelligently filtered by signal intensity and pixel grouping to afford noise-free detection and remarkable contrast. The TPX3 cam is flexibly formatted to detect photons, electrons, neutrons, and molecular ions. Configured for velocity map imaging spectroscopy, the TPX3 cam captures time-resolved images of gas phase reaction dynamics at exceptionally high repetition rate. Combining the TPX3 cam with an image intensifier enables single photon detection for versatile applications in quantum optics, neutron imaging, and fluorescence lifetime microscopy. Dedicated device software provides an intuitive acquisition control interface and data processing workflow. Users are also offered a robust API package for the freedom to customize data management and device operations using popular language libraries. Amsterdam Scientific Instruments' premium detector solutions empower researchers across the world to see beyond limits with unprecedented speed and accuracy. To find out how you can use the TPX3 cam in your research, contact our experts at info@amsins.com.
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EPI 2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging. In particular, it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter-long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In the nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It is easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com. What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EPI 2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging. In particular, it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In the nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It's easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
Today, thermal imaging is more accessible and affordable than ever. More and more professionals rely on FLIR's wide range of cameras to reveal invisible heat issues and to capture valuable temperature data. Our own innovation, development, and manufacturing capabilities give FLIR the agility and efficiency to produce such a complete line of thermal imagers and to do it so economically. Volume cameras can be useful in the world of R&D and science. But when it comes to the fine points, researchers and product developers demand the highest level thermal imaging performance, the kind FLIR science cameras are famous for. They need technology that captures high-speed thermal events in high resolution and with the most reliable results to help discover new phenomena, test new developments, and prove findings. They need to record detailed thermal distribution and variations in real time to measure heat patterns, dissipation, and other critical temperature factors. For years, FLIR has been committed to developing thermal imaging cameras that advance research and development projects worldwide. We still are today, with dedicated production and R&D facilities in Sweden and Florida. The FLIR Niceville facility is fully immersed in the design, engineering, and production of cooled cameras. Here, FLIR creates cameras for all wavebands, including near, mid-wave, and long-wave IR, and builds all kinds of detectors, including InGas, INSBE, and SLS. The Niceville team also develops software that is completely tailored to R&D and science professionals. The FLIR Research IR software works seamlessly with all FLIR R&D and science cameras that allows live viewing and provides detailed analysis of the most complex experiments. In Täby, Sweden, engineers in FLIR's state-of-the-art design, engineering, and production facilities focus both on cooled and uncooled cameras, targeted at the most demanding applications. These cameras offer a highly efficient and cost-effective way to capture accurate temperature data. No other thermal imaging company is as committed to researchers and scientists as FLIR. With its dedicated facilities in Sweden and the US, FLIR continues to be the industry leader in cutting-edge infrared technology for R&D and science. You can count on it.
The TPX3 cam from Amsterdam Scientific Instruments is a pinnacle innovation in ultra-fast imaging detector technology. At its core, the detector features a photon-counting hybrid active pixel sensor based on the advanced Timepix3 ASIC developed at CERN. Unlike slower frame-based digital sensors, the TPX3 cam operates using continuous event-driven readout. Each sensor pixel works like a precision stopwatch with an ultrafine time resolution of 1.56 nanoseconds. Activated pixels simultaneously record both the event time of arrival and response duration, or time over threshold, processing up to 80 million hits per second at an effective frame rate exceeding 500 MHz. Individual pixel responses are intelligently filtered by signal intensity and pixel grouping to afford noise-free detection and remarkable contrast. The TPX3 cam is flexibly formatted to detect photons, electrons, neutrons, and molecular ions. Configured for velocity map imaging spectroscopy, the TPX3 cam captures time-resolved images of gas phase reaction dynamics at exceptionally high repetition rate. Combining the TPX3 cam with an image intensifier enables single photon detection for versatile applications in quantum optics, neutron imaging, and fluorescence lifetime microscopy. Dedicated device software provides an intuitive acquisition control interface and data processing workflow. Users are also offered a robust API package for the freedom to customize data management and device operations using popular language libraries. Amsterdam Scientific Instruments' premium detector solutions empower researchers across the world to see beyond limits with unprecedented speed and accuracy. To find out how you can use the TPX3 cam in your research, contact our experts at info@amsins.com.
What do you expect when you hear multimodal microscopy? A bulky, expensive, and difficult to install device? No, the MPX microscope from Perspective Instruments are quite the opposite. It is an all-in-one device with second harmonic and third harmonic, as well as EPI 2 and 3 photon emission fluorescence imaging, also allowing for C-stack flexibility, as well as whole slide imaging. Due to the high flexibility of the MPX series, there are almost no limits to application areas, just to name a few examples. Single cell and live cell imaging, label-free digital histopathology imaging. In particular, it brings along process improvements in immunohistochemistry and immunocytochemistry imaging. Due to C-stack capability, 2D and 3D cell cultures and organoids can be imaged. Last but not least, label-free in vivo and deep tissue imaging is easily achieved. The microscope allows for flexible configurations, upright and inverted, horizontal scanning, larger volumes under the microscope for scanning bigger animals. It has a 2-meter-long flexible umbilical connection between controller and scan head. The scan head can be moved easily in translational and rotational directions. In the nutshell, this microscope is a truly turnkey multi-photon microscope ready for the wet bench. No optical table is required. It works out of the box, no installation by technicians is needed, and it comes with a pre-installed software. It is easy to transport, therefore easy to share with other researchers. For further questions, please contact us at www.p-inst.com.
Ladies and gentlemen, are you ready?
दुनिया के बाकी हिस्सों में जब इंसान अपने वजूद के लिए लड़ रहा था, तब भारतवर्ष में महान संस्कृति का निर्माण हो रहा था, जहां हर धर्म के लोग एक परिवार की तरह रहते थे। पर इस मंदिर को बाहरी आक्रमणकारियों की नजर लग गई। 16वीं सदी में पानीपत का युद्ध जीतकर दिल्ली के तख्त पर लहराया मुगल सल्तनत का परचम। उस समय कई शासक और सल्तनतें खुद को जिंदा रखने की कोशिश कर रहे थे। भारतवर्ष में अगले 100 सालों तक कोई और शासक मुगल सल्तनत को मात ना दे पाया। 17वीं सदी में मुगलों का सबसे ताकतवर दुनिया के बाकी हिस्सों में जब इंसान अपने वजूद के लिए लड़ रहा था,
काश इस समय
Good afternoon. After having a poster session and all were diving deep in science and technology, and whatever we are doing cannot be done unless we have good instruments, good equipment, isn't it? And this cannot be done unless we have a very good industrial partners who support us for this. You must be, thinking, why did I try you guys to come in front and that? Because if you sit at the back, our industrial partner will think we are keeping distance. So the amount of the discount they are likely to give will be reduced. And so we have to, I'll say that the people who are sitting first one may have more discount rather than sitting at the last. And some of us people now who does theory, they think that they don't need equipment, but it is not the truth. Because for the simulation also you need validation, and that needs a really good equipment. You may not need it, but your colleague may need it who will do the validation for you. So it's better to sit in the front and have a more discount so that you can have more number of the equipments and a better class of the equipments, and which will make the things better. So with this introduction, I'll start the industrial session. And first I will ask our platinum sponsor, Atos Instruments Market Services, and Mr. Om Sethia. He's a joint director with them, and the discussion he's going to keep is on innovations in scientific instruments. So we'll all be hearing to him, patient hearing, and try to see what can we buy from them if it's really needed for that. So, and with this, I'll take my seat, and Om, just try to have your presentation within 15 minutes. Yes. And if we have any questions, we'll see. If you finish in 12 minutes, we'll have 3 minutes for further discussion.
Sure.
Otherwise, we will discuss in the tea time, right?
Sure.
Okay, thank you. With this, start.
Good afternoon, everyone. I am Om Sethia, Joint Director at Atos Instruments Marketing Services. Many of you might already be knowing and familiar with this company, but for those who don't know, we have been formed in the year 2013 under the leadership of Kaveri Huku. And we believe ourselves as the bridge that, makes which bridges the gap between the one who innovates the instruments and till your lab. So for your experiments, for your high-end experiments and all those research that you do, we help you get those instruments till your lab. So do I have my presentation here or how? Okay. Yeah. You got it? Yes. So we are spread across India with our offices in all the 5 major cities. So we are never really far from wherever your lab is. And this is the product cluster of our product portfolio, which revolves around photonics and anything that if you have got to do with light, then I'm pretty sure that we have the right products, to suit your experimental needs. So in today's topic, I will keep myself limited to few products that is really, you will find it of interest. Basically, I'll talk about few detectors. Then I will go to cryogenics. I'll speak about some laser sources, laser measurement and analysis tools, and I'll end my topic with some details on the spectroscopy. So let's start with some detectors. The detectors have been around since many decades, but you researchers are always being greedy and asking more in terms of efficiency, speed, time resolution, and that's what helps us bring the new technology, which is the SPADS detector, or the single photon avalanche detector, where you get a single photon sensitivity, a very high frame rates. We are talking about 1 lakh FPS, definitely at the reduced bit rates, picosecond time resolved, time resolutions between the pixels. And the magic of these kinds of detectors are each pixels here can act as a single individual camera. So when you want to, with the advancement in the quantum technology, you also need to, you don't just need to detect a photon, you also need to detect the time of arrival of the photons with respect to different scenarios where these cameras excels, where the earlier camera failed to achieve those targets. So this brings us to the SPAD, which is one of the recent advancements. Then we come to sphere. You know, when you talk about shortwave infrared, there is always an inherent problem of dark noise and, you know, slower readout speeds, because inherently the dark noise and the read speeds really affect your measurement tools. And, you know, if you're working with low light level signals, then, you know, the SWR was kind of tabooed in that domain. This is what has brought us this latest cameras from First Light, where we have improved the frame rates with latest generation of electronics and reduced drastically the dark counts that you achieve, that you really face when you talk about 900 to 2200 nanometers of wavelength range. Definitely we need to have cryostats, or whenever you want to work under low temperature. So, you know, you place your sample and you want to study its characteristics under low temperature, that is 4 Kelvin or less, using helium or liquid nitrogen. This is where we have our cryostats, and we have various cryostat modules to help you work with optical studies, magnetic measurements, as well as electrical measurements as well. Sorry, I'm keeping it fast. I'm not going too much into technical because of the limited time I have. Now let's talk about certain sources, because without excitation, how would you, jumpstart your experimental data? We have supercontinuum white light laser, which gives you the spectral range from 450 to 2300 nanometers with an average combined power of 3 watts. It's a very stable, 10 picosecond is the pulse duration, and very stable source that we have with us. Then we have lasers, tunable diode lasers, which is a workhorse in majority of the spectroscopy applications. Very narrow line width, tunability from UV to NIR range, and with Litman and Litro configurations, and you are free to choose between free space optics or fiber optic couplings. Then we have our excimer gas lasers in UV. Whenever you think about pulse laser deposition kind of experiments or laser-induced breakdown spectroscopy, these becomes, you know, a very dominant part of your scientific equipment. So we do have this, and very high power, around 700 millijoules of pulse energy is what these lasers are able to provide you. Whenever you have laser light sources, you definitely want some tools to help you measure and characterize them, and that's where the wavelength meter spectrum analyzers and the autocorrelators, you know, help you to really know what kind of lasers or what the characteristics of the laser you have been using it. Next, I would like to end this with a big major part of spectroscopy, which I believe is one of the very prime tool for majority of the researchers over here. We have been having more than 400 spectrometers from Andor all around India now, many of them in RRCAT and other IITs around. The recent development, if I talk about, is the introduction of spectrometers with more number of gratings to enable you to have a wider wavelength coverage covering UV, visible, NIR, and up to SWIR in the same spectrometer without having the need to have a second spectrometer or having to replace the entire turret of the gratings. So these are some of the new recent development. Definitely the EMCCDs and ICCDs have been around since decades, but the CMOS, SCMOS, I would say, scientific CMOS technology, have been catching a lot. They are now able to match the back illuminated sensitivity of the standard CCDs and EMCCDs, and definitely with the advantage of having even more read speeds and higher frame rates. So these are the recent developments over here, and if you have any other requirements, please do feel free to drop at our stall. We are here till tomorrow. And these are some of the other instruments. You can just have a look. These are compact spectrometers, compact lasers, gas mixers. When you want to have a precise ratio of multiple gas and wants a complete control over the flow rates. These are touch control and very accurate gas mixing systems. Hyperspectral imaging systems, where you get an image cube and get the wavelength at each pixels, mainly used for various kinds of analysis, quality control, forensics, and many other applications. Yeah. With this, I would like to end my topic. Thank you so much for your attention. Will there be any questions?
Thank you. Is there any questions from the audience? No. Thank you.
Thank you, thank you.
The
I would
next
like to
is,
thank all the organizers before I leave, and special thanks to Hemant Krishna sir for helping me, helping the event go so smooth for us. Thank you, Hemant sir.
Thank you. Now it's time to hear from our silver sponsors, IPG Photonics. Shri Shirpad, please come over the stage. From IPG Photonics, Bangalore.
Good evening, everyone. I am Sripad from IPG Photonics India Private Limited. I will just brief initially about the organization, and after some time we will play our corporate video. So basically IPG Photonics, it's a US headquartered company having plant in US and Germany, and we have many type of fiber lasers starting from 10 watt and maybe up to now 100 kilowatt fiber lasers with different wavelengths and for different applications. The one more thing just I wanted to inform here in this stage is in this RRCAT premises itself, we have lasers from 100 watt up to 10 kilowatt lasers. Number of lasers since last 15 years, we have supplied number of lasers to RRCAT and of course many other government organizations. Okay, now we'll run one corporate video, and again I will put one or two. thank you for your attention. One thing I wanted to share with you all is we have application center in Greater Noida where you can see different type of lasers, single mode, multi-mode, quasi-CW, AMB lasers, adjustable mode beam lasers, and we do a lot of trials mainly with reference to welding applications and micro cutting applications. So since you are all into research work, so it will definitely help you to understand different type of lasers. So please do visit our Noida lab. And in here also we have a stall. I'm sitting there in the stall. Please visit. And you may not require all the products now, but at least try to understand what kind of products we have so that it may be useful in future. Thank you very much.
Thank you, Shripad. One thing I would like to add to all our vendors and the suppliers who had been supporting to us, the day they give lists to us, they feel like they are giving doctors to us. Whenever they come, they visit to us, see how the condition of the system is, and if there is any issue, they resolve, and many times without cost. So with this, I'll call our...
Thank you.
With this, I call our next presenter. He's Mr. Tapan Sharda, Director, New Age Instruments and Materials Private Limited. He'll be talking about the indigenous development of indigenous development in India. Over to Mr. Sharda.
इसको ओपन करने में इसका वो कहाँ है हाँ ये इसका वो माउस स्लाइड आ गया नहीं ये नेक्स्ट इससे good evening everyone. My name is Tapan Sharda. I am a managing director. Good evening everyone. आवाज आ रही है? Okay. So good evening everyone. My name is Tapan Sharda. I am a managing director instrument and materials. So most of the scientific community knows our company as a distributor company. We are still a distributor company, and we continue to be a distributor company in the future. But my today presentation is basically about the products we are developing in India. We are continue to supply imported product from outside, but we have make square feet facility in India, and we have started doing development in India. So I will focus my presentation on that. Next thing. So we started in around 2000, 2001. So we are already a 25-year-old company. For the last 10 years, we have started making some products in India. Some product we have developed ourselves. For some of the product, we have taken a technology transfer from different academia and different organizations, even DRDO, DAE, and other organizations. The total strength we have today is 65 people in India. So this slide is basically about the company growth. So we are growing steadily, and we expect that we will continue to grow at 10 to 15% every year. This is a picture of the new facility we have made in India. This is facility is a 12,000 square feet facility, which is dedicated for make in India products only. So there is no distributor activity inside. So only products which we are assembling, integrating, and designing in India, and doing the production as well. So we have a plan to develop this facility, increase this facility to 42,000 square feet in the future. So this is the first phase we have completed for 12,000 square feet. So in this facility, we are creating optoelectronic facility integration, mechanical design integration, electronic design integration. There are software development team, and we are also setting up some environmental test facilities also in the lab. So this is a drawing of inside. We have created some optical lab, we have created some mechanical lab, we have created some electronic PCB design lab, we have created software development lab, and we are in a process of setting up some optical lab in the near future. We have installed some vibration isolation table, and we have ordered few more vibration isolation tables. So we are creating not the clean room but a clean room to start our work. So, so we are doing all optical designing using ZMAX and Oslo, and also doing PCB designing using LT Spice and LTM softwares. So we do our own designing. We are not doing the PCB fabrication ourselves. We outsource that part to the other industrial partners. And then we are doing software development on almost all the platform, right from Python to LabVIEW to FPGA to Arduino to microcontroller. So all the platform available, we are using those platforms. Then for mechanical design, we are using a SolidWorks, which is a very popular software. So we are using that software for mechanical design. We have some in-house mechanical fabrication equipment as well. So all our design development is basically focused. We are discussing with different scientists, different applications. Sometimes they have already designed some instrument, so we discuss with them. And sometimes they want some industry to take up that, to modernize that, or maybe add some value to it. So we are taking up that thing from different academia. So we have a complete team for doing all this development. So we are doing the testing and validation ourselves. We have all electronic test equipment, right from oscilloscope to function generation to spectrum analyzers. So our core technology area basically focus around light source, lasers, optics, photonics, detection. So we have almost like a 4 different areas where we are doing most of our work. So in sensing part, we have designed different type of detectors. We are taking detector chip from outside, and we have developed our own electronics, data acquisition systems and software for that. And then we are doing different type of light sources. Even we have made LED based light sources, different type of halogen deuterium lamp light sources, xenon light sources. Even also we have made laser drivers. So we are even taking laser chip from outside and making the laser itself in India. And also in spectroscopy, we are doing different type of spectroscopy modules, right from fiber optic spectrometers to Raman spectrometer to terahertz spectrometers. And also in communication, we are involved in free space communication and quantum communication. In the next slide, I will show you more about it. So these are some of the products which we developed in the last few years. So in the Seeker detector series, we have developed balanced photodetector, photomultiplier tube detectors, photodiode, silicon photodiode module detectors, photomultiplier tube detectors, and PSD photo detectors. So all these chips we are buying from outside, and electronics, data acquisition system, and software and complete assembly we are doing ourselves. In the Lumen light source series, we are developing different type of light sources, right from LEDs to xenon lamps to deuterium lamps to halogen lamps to the lasers itself. And also in the multi-channel infinity laser drivers, we have developed different type of laser drivers in India. Even recently we delivered one VCSEL drivers to DRDO lab. They are working on some quantum magnetometer thing. So they gave us the VCSEL chip, and we developed the driver and complete integration of the assembly we have done for them. And then we are doing some spectroscopy modules, which is basically based on spectrometers and Raman spectrometers. So we have delivered around 20 Raman spectrometers so far in India. Even we are doing now export outside India as well. So we now have around 5 to 6 different variants of Raman system, which we have developed in India. The next one is a muzzle flash detector, which actually we developed for one of the ISRO lab and DRDO lab as well. And one of the European company from Italy actually visited that facility to install some of their system. They saw the performance of our system, and after going back, they released order to us from Italy. So we are now exporting to Italy and UAE. So that is based on the performance of the system they have seen in India. So we are now exporting to Europe and UAE. And recently we delivered a very big project in UAE which was more than 2 crores. So we established a complete lab which was for spectroscopy and laser based system. So we are doing that as well. So these are some of the other products which we have developed. So these are the different products or details. So I can give you more details if you come to our booth. So I will now giving you some of the project which we delivered in India, which was made by us from the scratch for different agencies. So we delivered this LIF based bioagent detection system for DRDO. We delivered 2 different variants. One was basically to detect bioagent a few kilometers in air, and second was basically detecting a bioagent in high vacuum chambers, and also in the hall. Suppose we are sitting in a hall and this is centrally air cooled. If somebody inject a bioagent where the central air AC is there, we will then all of us will breathe the air which is infected with that bioagent. So all of us can die within seconds. So this detector basically is designed for that purpose, for VVIP buildings. So it will basically test all the air coming out from the that central air condition system. Test that. If it found any poisonous bioagent, it will create an alarm. So that system we designed and developed, delivered to DRDO recently. So this is another system we developed. This is a 6-channel multi-channel laser ignition system. There is a DRDO lab who designed different type of explosives in India, and they would like to test at what energy density that explosive will be fired. So we delivered a 6-channel multi-channel laser driver, and also the complete laser assembled we did in India, and they are doing this testing in DRDO for different type of explosive. So they mix different type of ratios of different explosive and test at what energy this will be fired. Then we delivered one laser hyperthermia system. Basically this is a kind of a new research BRC is doing. This is a alternative to kind of a chemotherapy for cancer detection, cancer curing. Like we have all know chemotherapy, but this is a new technique coming up all over the world. So this system is basically for that purpose. And then we delivered to DRDO one LORDS, which is a laser ordnance disposal system. This is basically for destroying the explosive which are not used or unused. So this system also we delivered to DRDO. Then we took some customized project on lifetime measurement. So we delivered a complete lifetime measurement system where detector chip and laser chip was purchased from outside, but laser driver, detector driver, complete integration of the project and complete software development was done by us. So we delivered a complete project to DRDO. And then DRDO came to us for measuring a very high power laser. They were saying that they will fire only one shot, and they want to measure all the parameter of laser like power, beam profile, M square, spectrum in one shot. So they will fire only for a few seconds, and I want to know all the parameters. So we developed this system for DRDO. So this was initially for 1 kilowatt, but if somebody wants, we can deliver even higher also. Like IPG colleagues mentioned that they are delivering very high power fiber lasers. So we can actually have a solution which can even test up to 100 kilowatt laser, 100 kilowatt fiber laser. Then we delivered few more system for DRDO. This laser diagnostic of designator, actually I cannot give this detail to them because of the NDA with DRDO, and they specifically said that we cannot deliver, mention this detail about this in the open domain. But we delivered this and it is working in the field. Then we delivered some spectroscopy solution recently for BARC. They asked us to develop a TLD reader and OSL reader. This is a kind of a dosimeters. So we made the PMT driver ourselves. We made the different type of instrument, assembled them together and delivered a complete system. Even the software is also developed by us. Then we also delivered a spectroscopy module, which is having a all-in-one kind of a box, very small, you can carry anywhere. It doesn't require a PC, it doesn't require any outside power supply. So everything is inbuilt into the system. There is a touch panel display, software is inbuilt, PC is inbuilt, spectrometer is also inside, and you can operate the system anywhere. It is weight is more than, I think, around 2 kgs, complete weight. Then we delivered several Raman systems, compact size, to BRC also, to other organization also. So this is also made by us in India. So as we know, the National Quantum Mission is coming. So we have some initiative in the field of quantum. So we recently signed a contract with the CDOT. We are becoming their technology partner for quantum key distribution. And based on that technology, we have made 10 QKD system, which was delivered just in December 2023. So we probably are the only company in India who have made 10 quantum key distribution, fiber-based quantum key distribution, not free space. So this we delivered just in December to the customer, and we are now talking to other big organizations like Army, DRDO and Railways for hack-proof quantum key distribution system for quantum communication. Then we have basically different type of contracts, and this is basically a fund given by MATI to IIT Kharagpur. They are creating a national center, and there are 3 partners in that: CMAT Pune, IIT Kharagpur and New Age. And New Age is going to be the industrial partner in that. So whatever technology CMAT and IIT Kharagpur will make, we will have to commercialize that and do the field trials and suggest them what changes are required. So we are a partner in that. We have another contract which is basically an Indo-US project, which is on CVQKD, another quantum key distribution kind of a project, which is given by DST of India, and there is a DST in US counterpart. So there is a fund, so we have applied with the IIT Roorkee, and we got that project, so we are starting that work from next month. There is another project which is basically a combination of CBQKD and free space communication. So this is a technology development fund, so we have applied for that. This is also in the final stage. So they have informed us that technically our proposal has been accepted. So they are going to start the financial discussion with us. So this is also based on quantum communication. This is a fiber QKD system which we delivered. As I mentioned, we delivered 10 fiber QKD system to CDOT recently, and we are going to deliver another 4 to 5 systems to Army, DRDO and Railways, and we expect these numbers will grow in the near future. So because of the time limitation, I have not added more slides, but I can tell you that just a few months back we delivered 1 terahertz spectrometer to DRDO, which is working fine. Based on that performance, they are giving us a repeat order for terahertz spectrometer. So we are going to create another terahertz spectrometer, plus now we are going to start work on terahertz imaging also. That was a terahertz spectroscopy system. We are going to start the work on terahertz imaging system as well with the DRDO. And recently we are expecting an order from BRC for designing a LIB system, where we are going to have a laser from European company, and rest of the thing we are developing in India. All electronics, software, complete integration assembly will be done by us, and the system will be supplied to BRC. This will be a LIB system. So if you permit more time, I can explain more project, but...
No, actually you already over by 2 minutes. Okay. I was just waiting for you to finish.
Okay, sir. So this is a kind of a summary of development. We can talk about imported product. Everybody is talking about imported product, but what about the development in India? All our organizations, RRCAT, BRC and other organizations are developing a lot of technologies. So there are not many industry who are coming forward to take that technology and develop those systems in India. So we are tying up with the RRCAT also. We have applied to RRCAT for 1 technology transfer. So we want to take that technology and develop that technology further and supply to not only just in India but outside India as well. So we are looking forward to all the labs, be it RRCAT or any IITs or BRC, if they have developed any technology which has a commercial viability, we are ready to take up that technology and develop that system and supply to the industry and other organizations. Thank you all. Thank you very much to NS organizers for giving us opportunity.
Thank you, Tapanji. This is a really wonderful presentation. Yeah. I would just like to add to all peoples that now we have 4 incubation center in the DAE, at RRCAT, BRC, IGCAR and
IPR. All these are not only helping industries to take the technology, but also going with the value addition by providing space, expertise, and the systems. So this is again the open for all the industries. You must be knowing about it, but if you want to have more detail, please visit to us at AIC Pi Hub stall so that you have more details about it. The next presentation is from Interface Design Associates Private Limited, Mr. Srinivasan Iyer, who had been working with the academia for a while, and if you see the gray hair will tell the amount of the effort he has put to make the things. Over to Mr. Shrivar.
Sir, thank you for this opportunity. I'm happy to be here. First thing which I want to share is, you asked everybody to come and sit in the front. I was never a front bencher in my class, so I was, when the teacher asks you, you always get scared. What is going to happen? Why did the teacher ask me? So that was a nice funny moment which I could share with my colleagues also. So thank you everyone. I just want to share a few things, what we have been doing in the last couple of years, new developments in our company. So I'll give you an introduction to what we do, and then I'll also then share our latest innovations, what all we have been doing in our company. Yeah. Our company is known for making a lot of products, very, very different in different fields. People who are in metallurgy come to us, people who are in electronics come to us. So I will be sharing only those things which are concerned with lasers. Yeah. So we are founded by 3 IITians. I am from IIT Madras, passed out as Professor Dr. Paul said. Grey hair tells you that I passed out many, many years back. So we are based in Navi Mumbai, and we have facilities, manufacturing facilities both in Bhiwandi as well as in Nasik. And we have a very, I will say I am very proud of the infrastructure which we have developed, and we are continuing to develop more and more instruments we are adding, more and more equipment we are adding. Yeah. And like Mr. Sharda said, we also have invested a lot in software for both design as well as manufacturing. We have a lot of CAD/CAM tools both for electronics and mechanical. So I am Srinivasan. I did my BTech from IIT Madras. My other 2 colleagues are from IIT Bombay. Dr. Vaidhi, Dr. Vaidyanathan, who is our CTO and our technical director, he is a PhD in computer vision, and though his background is his BTech was in mechanical, so multifaceted personality. And then Mr. Narayan, he is a BTech mechanical from IIT Bombay. So our customer base, this is telling you most of the IITs, most of the NITs, they are our customers. IIC Bangalore also is one of our key customers. Most of the research organizations like from the DRDO or from CSIR labs, HAL, VSSC, ISRO, they are all our customers. And in the DAE, BARC, IGCAR, PRL, RRCAT, NPCL, they are all our customers. And we are talking about this relationship at least around 20 years or 20 plus years. So I'm moving straight to our latest things which we have done so that I can share what is new. So this is a very special machine which we have developed over the last 1.5 years. So as you see, it's a small micro milling machine, you can call it a CNC milling machine. You could remove the spindle and put a laser on that. You could remove the spindle and put something else, some sensor there. But it's a very, very high precise machine, very compact. And the real innovation which we have done is to make the controller which is having 5-axis simultaneous interpolation. So for people who may not be familiar, this is a very major breakthrough, and we are very happy. It's our own controller. We have developed it in-house. And we also have developed some software. You will see in the next slide. So the post-processor which we got developed for our controller is enabling a very, very smooth workflow for going from a design, if you have a 3D model, to get it either machined or to get, to get the CNC to move as per a 3D model is a pretty big challenge. Even with the best software, you need very, very highly trained people for it. Trained people who are trained on both the job as well as in that particular software or the tool which we are using. So what we did was we went and worked with Fusion 360 because it's a lower cost tool to experiment with. Colleges more or less get it free. So for them, for research institutions, it becomes an easy way to start off on their 5-axis journey. And because of the post-processor which we have developed, if you have a model, or if, say, for example, you scan the free-form surface, you can straight away generate the G-codes with maybe about half an hour of work, that is all. And we have trained engineers who can guide you through this process. Maybe once you buy our system, say you go through 3 or 4 iterations of different parts, you become very, very comfortable, and you'll realize the ease which we have, what we have actually done. Yeah? So I'll just play a video, just a second. There's no audio. I'm just speeding it up. It's a long one. So you will see this is actually machining a 5-axis part. Now I don't know how many people here have tried to get a 5-axis part manufactured. It is, I know how big a challenge it has been for us, and I can promise you that what we are showing you here, while it is looking very easy and very, I would say, trivial, it is we have actually, crossed a very, very big bridge with our software. So this is actually making a kind of a turbine blade. Sorry, not a turbine blade, some other part. Now, this is the latest thing which we did over the last 2 years. We have been working with RRCAT, and we have taken their technology for the LAMP DED system. And we are very happy to say that thanks to this association, we have got access to a technology which otherwise was something where we were only providing parts of that technology. We have supplied workstations to Dr. Paul, to IISc, to IIT Indore, so many people, but at the same time we never got down to making a complete 3D printing machine, metal 3D printer, which we have managed thanks to their help. So to talk about this machine, the technology has come from RRCAT. It is completely indigenous. The pricing is very affordable. We have indigenized many parts of it, including the cladding head, the powder feeder, the controlled atmosphere chamber, the motion controller. As I said, it's our own controller, and also the software. Yeah. So the target which Dr. Paul gave us was that you should build a machine which will cost less than ₹1 crore for the educational institutions. And that is what we have been working towards, and we have managed that also. So the specifications of the first model which we have launched is a 200 by 200 by 200 millimeter machine. That's how the 8000 comes in. 8000 cc is the size of the part you can make. The fiber, our cladding head power capacity is 2 kilowatts, so we can work with either 1 kilowatt to 2 kilowatts is what we are giving. Our basic machine comes with a 3-axis, but we can provide a 4th axis and a 5th axis also. We can provide a controlled atmosphere chamber, so we can have argon and do all your jobs in the controlled atmosphere. We have already 2 customers, IISc Bangalore. We have already delivered the system to them, And we have a delivery coming next week to SRM University, Andhra Pradesh. So as I said, this is our powder feeder. Looks like any other powder feeder from the market, but yes, this is completely made by us. So a lot of innovations we are doing in that. This is a fourth axis which we have added for cladding for the customer. And the cladding head which you see, except for the nozzle, everything else is here. So this is again built entirely by us. It is a made in India product. All the machining was done except for the lenses. Nothing else is imported. So this is what we have supplied to IISc Bangalore. What you are seeing, that white paper and all, is basically the acrylic has been covered, so they'll remove it once it's installed. This is how the machine looks from inside, the CNC part. This is the entire, we have given them a vacuum chamber, so there's all the feed-throughs. This is also indigenous. So I'll just play the video. Sorry? How do I switch to this? वीडियो बाहर है, स्लाइड में नहीं है, बाहर से हाँ, बाहर से ही चलाया मैंने.
Srinivas ji, time is getting up, so we'll...
Just last 2-3 things. I'll just rush through this. Again, 5-axis simultaneous interpolation, very important. Especially if you're trying to make any free-form surfaces. You know, if you have surfaces which have some kind of geometry which is easily handled with something, you can do it. But if you have free-form, then you need this 5. I'll just pause this. So other 3D printing solutions which we have done for other customers, what you see here is a micro 3D printing system which we completely designed, engineered and manufactured for Dr. Parani at IIT Indore. On the right is the machine which Dr. Paul and his team are using for all their trials. They've got it built by us. Then the machine on the left is what is with Dr. Kaushik Vishwanathan at IISc Bangalore. And on the right is again a microplasma based 3D printing which we have delivered to Dr. Nilesh Jain at IIT Indore. Some other systems we have done. This is a 4-axis laser welding machine. I'm just showing you the photographs. This is a laser shock peening machine which we built for NIT Trichy. And this is a 4-axis laser welding system which we have built for BRC Trombay. We thank you. Thanks Dr. Paul for this opportunity. My pleasure. If you have anything, please come and visit our stall. Yeah. Thank you very much. Yeah.
Thank you, Srinivas ji. Now it's time to hear from Mr. Anmol Malik from Photic Scientific Private Limited.
Hello everyone, my name is Anmol and I am from Photic Scientific. So we are comparatively a new company. We formed in 2020 and our main portfolio is lasers and spectroscopy as well as nanotechnology. So this is about us. So we have a lot of solutions for lasers and spectroscopy, starting from diode lasers to nanosecond, picosecond and femtosecond lasers. So I made this presentation in about half an hour, so it will be a little clumsy. So I'll
You
only
don't have to worry
discuss-
about clumsy. We short presentation.
Okay. Yeah, so I'll only discuss about the major companies that we represent. So we've started representing XPLA. So XPLA has DPSS lasers, ultra-fast and tunable lasers. So the first series is the Femtolux series, which is the award-winning tool for micromachining, and it recently won the Prism Award. And it comes in 3 variants, which is 3 watt, 30 watt, and 50 watt, with a repetition rate from 100 kilohertz to 4 megahertz, and energy as high as 1 millijoule. So it is basically used for micromachining and material processing like glass, polymers, and metals. And the advantages of this is it has a dry cooling, and no maintenance at all is required. And it has multiple modes like megahertz and gigahertz burst modes as well. The second product line is the picosecond lasers. XPLA does tunable picosecond lasers and has the highest tunability in the market from 193 nanometer to 16 micron. And a peak power of 50 megawatt, which is ideal for nonlinear spectroscopy applications. And then we have OPCPA-based femtosecond lasers. And these lasers can also be tunable. So we have energies as high as 14 millijoule, and with a repetition rate of 1 kilohertz. And we also do nanosecond lasers from 100 millijoule and very high energy nanosecond lasers as well to up to 10 joules. And XPLA can also do custom solutions, and they have very high energy lasers up to 30 terawatt as well. The next company that we represent is Teledyne. So Teledyne has 2 divisions, and we are doing both. Teledyne Photometrics, which is the industry leader for scientific CMOS cameras, and the most recent series of cameras that they have launched is the Kinetic series. So with Kinetic series, we get 500 frames per second with a quantum efficiency of 96%, and a field of view is 29.4 mm, which is a lot. So it is ideal for fluorescence applications, low light imaging applications, and as well as quantum optics applications. And they also have EMCCDs and machine vision cameras. The next division that we do is Princeton Instruments. So with Princeton has a spectroscopy and imaging solutions. The isoplane spectrograph being the highest order of spectrograph with the best resolution and no aberrations at all. The best part is that we have a lot of detectors, and the detectors quantum efficiency is as high as 99%, and the cooling is up to minus 120 degrees Celsius. So it is ideal for Raman spectroscopy and photoluminescence applications as well. They have in-gas and large format sensors cameras for astronomy applications, and we are in touch with a lot of astronomy, ISRO and SAC and IPR for development of these large area sensors. The third major company that we represent is Edmund Optics. So Edmund is the global leader in precision. They have a wide variety of lenses, mirrors, optics, and they've also launched the ultra-fast optics with very high damage thresholds. And the best part of Edmund is that all the prices are available in Indian rupees on their website. So anybody can visit the website and see the prices. We also have the second division, which is the nanotechnology division. With nanotechnology division, we do solutions for material science, quantum research, and semiconductor industries. The company that we represent is Vinci Technologies, a France-based company, which does ultra-high vacuum PVD systems and molecular beam epitaxy systems. So we do sputtering systems, E-beam evaporations, and ultra-high transfer tunnels, as well as we do molecular beam epitaxy systems, and we have delivered 2 MBE systems in India. One is in IIT Delhi and the other is in INST for 2D materials. And so why choose Photic Scientific? So we are representing a world-class branch, and we have strong expertise in lasers and spectroscopy, as well as a dedicated support team and after-sales service team. And that is it, sir.
Thank you, Anmol. Yes, now I request the last presentation from Trukut. I request Lavanya to please come forward and have presentation Trukut.
Good evening, everyone, and I would like to thank the organizers of the National Laser Symposium for giving us this opportunity to talk about the company and the products. As you all know, I've been working in this industry for last 20-25 years, and TrueCut Solutions is our own brand. So here we are trying to concentrate on the different markets which are the requirements of the science in the industry. And we also plan to do some Indian manufacturing. So after establishing for 6 years, we feel that this is the right time to go towards the manufacturing or the integration, whatever way you may put it. And in the last 6 years, we have tried to work on the different markets. One is the lasers, some in the ultrafast, some in the material processing. The different techniques of the 3D printing we have from the micron to the So we have companies. Then the core being the photovoltaics characterization. We all know that the semiconductor market is going to be very strong in India. And then a little bit of the optics and crystals. So we are now recently joined with Opto-Sigma or the Sigma Koki Japan for the optical components. They're soon going to launch the Indian office, so it will be the Indian website for all of you. So we are located in Mumbai. We are a team of 15 people with 4 service and the rest for the sales and the finance. So in the last couple of years, we have added about 300 systems for the different markets, and it's quite good, I believe, with the gem and the local content. So we believe we are happy about it. Yeah, these are the number of principles. I think if I start talking about it, I would need a lot of time, but most of the brands are known to many of you. Today, as the time is very short, I'll just concentrate on the one product line, which is the femtosecond fiber lasers, which is the core in all the science, in neuroscience, multiphoton, spectroscopy. Why? Because the fiber femtosecond is the technology for the future. So when we all talk about fiber femtosecond lasers, we always, at some point, we were always talking about the bulk lasers. But now this has been a first-class manufacturing. Like most of the companies have started this in the clean room. They're able to make the size of the laser small and small and small. So you can see the size of this fiber femtosecond lasers. These are 100 femtosecond fiber lasers and having different wavelengths here, 780, 1040, 1064, 520, and 780. So there is a group here who works on terahertz, and 780 would be a lot of interest to them. And there is a group here who works on spectroscopy, so it's 1064 as 1040. And the power here is up to 5 watts. So all these lasers are dispersion compensated. So you have a pre-compensation already inbuilt into the system. You also can have fiber delivery. You can also have an AOM. You can have a multi-beam option. So this module gets attached to each of these systems. So these are some of the specifications, but I think you can all come to my booth. We can have a discussion on the different power levels. So I gave you an idea, we already have up to 5 watts. This is the AOM Excite, which gets add on to the fiber femtosecond. And this is a mini 2P. So people working in the microscopy, they all know that you need to do some kind of an imaging. So you can just attach this to the head of the laser, and you can scan the whole brain of any of the animals which you're trying to read on. And this is a multi-beam. So on a single laser, you just add these attachments, and you can have 2 outputs, 4 outputs with the system. So these are the different applications. I did have a slide on the 3D printing, mainly for the micron printing. Why do we always talk about micron? Because it's always in the industry of MEMS. But because of the time, I would request you all to come and discuss with me. This is a very, very innovative technique on the sub-micron resolutions. So we use an AFM-based technique, and you use to do the whole printing through voxels. So I will just show you what are the, because you know there is always, when we talk additive manufacturing, we have the expert here, Dr. Paul, who always talks in the area, but there could be also on the micron, where we talks in the MEMS, in the packaging industry. So here, this is a system from Switzerland, and it's very innovative that they are using an electrolyte bath, the AFM technique, to build in submicron. So if there is few minutes, I'll run a video. If not, I just tell thank you. So this is in video. So you can see the direct material printing happening in an electrolyte bath. Through the voxels, you're trying to create the microprinting parts. So I would finish my presentation with this video, and I would like to thank everyone for listening to me. And please come and discuss with us in our booth.
Thank you very much. Thank you, Lavanya. And while we are seeing the video, we can also have a big round of the applause for all the industrial presenters. इसमें तो डिस्काउंट मिलने वाला नहीं है, थोड़ा हमें जोर के ही बजाना पड़ेगा राउंड ऑफ अप्लॉज के लिए, especially students, right? There should be energy in the room. Right. So now it's time to hear the most important presentation of this symposium. Because you know this symposium is DAE-BRNS National Laser Symposium. Unless we hear from the people from the BRNS, Board of Research in Nuclear Sciences, things won't be complete. So I request Sri Hemant Prakash Agnotri from Board of Research in Nuclear Science to please come forward to have a presentation on what BRNS does and how the things are being carried out in the DAE and other funding agencies. How does it work as a funding agency? Over to Mr. Hemant Prakash Agnotri.
Next. So, namaskar and good evening to all. First of all, I would like to say thank you to for inviting me in this presentation. So, today in this presentation, I will talk about collaborative and coordinated research projects which are in alignment with the DAE mandate. So I will talk about what is collaborative research projects, what is coordinated research projects, and what is research projects actually. So why these research projects are required? The basic question is, so for example, these research projects are mainly useful for the faculties, professors who are working in academic institutions, maybe in IITs, NITs, other universities. So these research projects are useful for both universities as well as Department of Atomic Energy, which is providing the funding for the research projects. So we can see any universities is a hub of innovative ideas. They have very talented researchers, but sometimes some of the universities may have limited resources, and some universities may have also limitations on the opportunities given to the young researchers. Also in the Department of Atomic Energy, we can see we have access to a specialized infrastructure. We have leveraging diverse expertise. We are doing research projects to address societal challenges. This also provides the career opportunities to young researchers. Of course, the necessary funding is required to carry out these research projects. So any research projects which are which has been done in collaboration with universities and Department of Atomic Energy, it will be mutually beneficial to both the institutions.
So in this slide you can see the web page of Department of Atomic Energy showcasing the various institutions under the Department of Atomic Energy. So under the Department of Atomic Energy, DAE, we have various units. For example, in R&D sectors, we have BRC, IGCAR, RRCAT, etc. We have also the industrial units like NPCIL, Bhavani, etc. Then service organizations, we have GSO, DCACM. Under the category of aided institutions and other organizations, we have a list of 13 institutions listed here. So in this red, you can see Board of Research in Nuclear Sciences, BRNS. This unit is responsible for all the funding, extramural funding of Department of Atomic Energy. So basically this BRNS deals with all the research projects and scientific events except mathematics. For mathematics, we have NBHM. This is called as a National Board of Higher Mathematics. So now I will go through the brief historical background of BRNS. So BRNS was born in pre-independence era in 1945. At that time it was named as Atomic Energy Committee. Then just after the independence, this committee was renamed as Board of Research in Atomic Energy, BRAE. Soon later it was renamed as BRNE, Board of Research in Nuclear Energy. Then in 1955 it was renamed as Board of Research in Nuclear Sciences, and till after that it is continuing the same name, Board of Research in Nuclear Sciences. After that it was in 98 or something, it was reconstituted with 9 committees depending upon the subjects. So time to time it is being reconstituted during 2018. Also earlier there were 5 committees. In 2018 there are 9 committees. So here you can see the structure of the BRNS. So basically the BRNS has a board which is being assisted by BRNS Secretariat and Scientific Advisory Committees. So depending upon the subjects of the project and symposia, the BRNS and committees assist the board, and board and secretariat are in contact with the Department of Atomic Energy for further advice. So here you can see a list of all the BRNS activities which are providing technical and financial support to following DAE activities. So it is divided 2 major parts. One is major activities is research projects. This is, I can say, around 75% of the BRNS funding goes for the research projects. This is, in this funding, we encourage the participation of JRF and SRF. Next, we deal with the symposia, scientific events like symposia, conferences, etc. Here also we encourage the participation of the students and young researchers. Then we have mega projects under the MOUs. This is helping us in building the national facilities and research lab across India. Then we have YSRP, Young Scientist Research Program. In this we encourage the young researchers who are below the age of 35 years. Apart from these major activities, we are also having supporting activities like International Science Olympiad. So students are under the HBCSC. They are performing very well internationally. Apart from this, we have DDFS scheme, DGFS scheme for MTech and PhD students. Then apart from this, we have other miscellaneous schemes also for Indian Physics Association, Raman Lecture Series, etc. So as I mentioned earlier, there are 9 committees. So here you can see the list of 9 committees. So once a project or symposia is submitted for funding to BRNS, depending upon the subject, this project is being reviewed by one of these 9 committees. So here you can see the subject and keywords corresponding to committees. For example, first committee, nuclear power program, deals with the mechanical and thermal engineering of the present and evolving nuclear reactors. They are also dealing with the construction technology, equipment design and prototyping, heavy water related technologies. So this is called as a CDP-1, Committee on DAE program. So CDP-1 is nuclear power program, which deals with the power reactor related projects. Next comes the URM committee, CDP-2. This is dealing with the projects in the subjects of uranium, rare earth materials. All the material technology related projects are being reviewed by this committee. Then we have FRR committee. This is CDP-3. So all the projects related to fast reactor technology and back-end fuel cycles, that is spent fuel related research projects, are being reviewed by this committee. Then we have healthcare committee. In this we mainly deal with the cancer related projects, not all the health science projects. Cancer related, cancer research, radiopharmaceuticals, diagnostics and therapy, radiotherapy, drug discovery and drug delivery, etc. We also have a committee on food security. So any projects on nuclear agriculture, mutation breeding, seed development, biopesticide, etc. These projects are being reviewed by the Food Security Committee. Next we have Water Management Committee. So the treatment of water purification and desalination, these projects are being reviewed by the WWM committee. We have Mega Science Scheme Committee. This deals with the projects on nuclear fusion, high energy and particle physics, cryogenics, charged particle accelerators, gravitational waves, astronomy, including gamma ray astronomy. Then we have Basics Research and Science Education Committee. So this committee deals with the projects in all the physics, chemistry, bio. It's a combination of all the three sciences. So I can say almost around 50% of the projects submitted to BRNS are being reviewed by this Basic Science Committee. Next is very important committee is called Directed Research Committee. So this committee reviews the projects on accelerators, lasers, electronics, nano, micro electronic devices. So basically in the projects in this committee should have a clear output of the project which will be useful for the department. So as I mentioned about the research projects, we have these 4 categories of the research projects. First one is relevant research projects. So in this project, there is one project investigator and project collaborator. In one YSRP project, this research project is for the young researchers. His age, as on the date of submission of the project, should be below the age of 35 years. PC means project collaborator from the Department of Atomic Energy is not necessary in this case. So this is to encourage the young researchers who have just joined an academic institutions. He can apply without collaborating in the department. Here only thing is a limitation in the budget. Next we have CRP project, coordinated research project. This project is being driven by the collaborator from the DAE. So basically in this type of scheme, the scientist or researcher who is working in the DAE unit will propose a project, and this proposal, after being reviewed internally from the DAE, will be put up on the BRNS website. So like indent, all the researchers who are in the similar fields, working in the similar fields, can see the detail of the project, and if it is matches with their expertise, they can apply and for this project. So now this PI and PC both in collaboration can apply for this coordinated research projects. Then we have mega research project. So this is project is for high value research projects. This is to be carried out in MOU mode. So the academic institution and DAE institutions, both the institute should form an MOU, and then we can fund this mega research project. So here I will go in more detail for the relevant research project, RRP. So here you can see the principal investigator. I use the name as a PI. So PI is from the non-DAE research institution or universities, maybe IITs or universities like Medicaps University, and he should find a collaborator from the DAE units, BRC, IG, CAR, similar, any unit of the DAE. So both this PI and PC should be working in this similar area, and they should make a joint research project proposal. And not only this PI and PC is required, the approval from the head of the institution of the PI is also required, and the approval from the head of the institution of the PC is also required. In case of DAE units, we need the approval from the group board. So we for this certificate 1 and this certificate 2 and 3, all the formats are available on BRNS website. So after the due approval from the head of the institution and a good proposal, we can submit online through the BRNS website. So as I mentioned earlier, the coordinated research project, this project will be announced on BRNS website time to time after getting approval from the head of the institutions or group board. So PC will propose the project, and PI from the other institutions will find if it is relevant to his area of expertise, then he can apply for that project only. But the proposal should be jointly prepared by both PI and PC, and with this coordinated, main point is that it can consist of multiple sub-projects also. Earlier I talked about RRP and YSRP. These projects, only one project is there, no sub-project. Here we can have 3 or 4 sub-projects. So for each sub-project, one PI and one PC will be there. But the outcome of this CRP should be a collective merit of all the sub-projects. Here, but limitation of the budget is up to 2 crore only. So, for example, a template of the CRP project is given here. Here, this is the title of the main project. This project consists of 4 sub-projects. So, every sub-project has one PI and one PC. We call it, for sub-projects, we call them co-PI and co-PC. For this main project, we call the PI and PC. So now I will discuss about what is the criteria of awarding new projects. So you can see the scientific content of the project. Of course, this is the main thing that we need to focus. PI's academic credentials is necessary. Sometimes your project may be very good, but if it is not relevant to DAE, so now we are not accepting such projects. Also, the capabilities of PI and PCs in executing the projects is required. Infrastructure availability in the institute of the PI is also being reviewed, and of course the budget and its justification to carry out this project is also required. Then I will show some points how to prepare a good proposal. So your proposal should include project title, committee keywords, summary, PI, PC, project duration. This is normal. Then you should focus on project objective should be crisp and clear. Research plan for 2 or 3 years project is there. So for each year 1, what is your objectives for in the PI's institute, what is your objectives which you will be carry out in the PC's institute, and at the end of the project, what will be the deliverables. It should be very clear. And budget details and justifications, we provide the funding for the equipment, consumables, staff. We also give the travel allowance, we give the overhead to the institutions also. But for every head, you need to give proper justification. If you are asking higher amount in consumables, you need a good justification also. Similarly for travel and all. So CV of the PI and PC is also required. As I mentioned earlier, certificates from the head of the institution of the both PI and PC is required. Sometimes if you are asking the equipment funding, if it is more than 1 lakh rupees, you need to give the quotation. So now I will come to the symposia funding. So BRNS provides the funding for organizing symposia, conferences, any scientific events, even theme meeting also. So there are two kinds of funding. One is partially funded symposia, one is called fully funded symposia. Today this NLS is a fully funded symposia. Around 20 or 22 symposia has been recognized by DAE as a fully funded conference. For other these fully funded conferences is to be organized by the DAE institutions only. So if other than DAE institutions is organizing any conference, that we give only partial funding, not more than 50% of the total expenditure. So only thing you need to consider that your application should be submitted at least 3 months before the event date. Otherwise, it becomes very difficult for us to process the application before the event is completed. Also, this scientific events should include the participation from the for the DAE researchers. Now, I will come to recent BRNS research projects, so that you can have a glimpse of how to submit a research project, how it is look like. So here you can see a research project by Dr. Annapurna from CGCI, Kolkata. This is regarding the development of cladding glass and optimization of process parameters of a 15-liter scale melting facility. So this project was PC from RRCAT Indore. So they have developed both cladding glass and laser glass. This project is completed now. So here in the outcome you can see the images, final pouring. In the first figure you can see the final pouring in the cast iron mold. Then how they are developing the glass, they have shown. In this project by Dr. Sumati from Chennai and PC is from IGCAR. So they have developed an innovative technology for imaging of the FBR fuel subassembly using ultrasonic method. Because the subassembly in PFBR, you may be knowing that it is in vertical and it is submerged under sodium. So it is very difficult to see the bowing of the subassembly. In order to monitor the bowing of the subassembly, this technique was developed under the BRNS project. So, and the deliverables you can see, all these deliverables were achieved by the in this project. Next project is a societal beneficial for mainly in Odisha region. So PI is Sanjaya Swain from BIT Misra and PC is from BRC Mumbai. So they have developed a kind of filter to filter the toxic metals like arsenic, and this metal in the next slide you can see this filter use no electricity, no regular maintenance, no overhead tank is required, regeneration of material, pre-treatment of water. This is very simple and removes both arsenic 3 and 4 to below WHO limits. So now this is a project under the Food Security Committee. Here this is under the MOU project. The budget is around 3 crore rupees. The PI is from IGKV and PC is from BRC, Dr. BK Das. Under this project they have developed R&D to improve the traditional farmers' variety of rice. So very big number of rice mutants they have developed and still developing. This project is now completed, but they have submitted follow-up projects to carry out the remaining objectives. So here the same project you can see how they are developing the food rice varieties, and they have improved the mutant variety of the seed distributed, and this has been recognized by the Gazette of the Government of India. So thank you.
Thank you, Mr. Agnotri, for nice full presentations. If anybody wants to have if they have some query about how to apply for the funding for the BRNS, yes, sir, please.
First of all, I would like to thank from our Medicap side for coming here and giving us a very good presentation for us. I also thank all the sponsors also for the time. I want to know what are the conditions for the private university to apply. That's very simple.
There is no difference for us, government institute and private institute. Even private academic institutions are also applying for the projects. Okay. And I will be very happy if I get some research projects from your university. Already I should appreciate that your institute is organizing this conference.
No, we are thankful for your people only. Thank you. Thank you.
Yeah, thank you.
So on behalf of organizing team committee, we would like to present a memento to Mr. Hemanji. So now I request Ms. Nikita to bring the memento, please. And I request Dr. C.P. Pal to present a memento to Hemanji. Thank you, Dr. Pal, for coordinating this session. Now we are at the last session of today. This will be followed by a special evening talk, which will be given by Padma Shri J.P. Mittal. I would request all of you to remain seated even after this technical session. Okay. So now this session will be chaired by Professor Tarun Kumar Sharma from our state. He is head of Semiconductor Lasers and Devices Division of RRK Tindar. I request Dr. Sharma to. Session 8 का क्या है?
Good afternoon. So in this session we have two talks. So I think they are going to display the CV of first speaker, Dr. Reggie Philippe, and he is going to, let me open. Dr. Reggie Philippe is here. Yeah. Yeah. So Dr. Philippe is from RIE Bangalore, and he is going to talk on machine learning based analysis of materials by synthetic Lipsch spectra generated from a 2-zone plasma model. So his CV is displayed over here. You all can read anyway. So Dr. Philippe, you have 30 minutes, and I request you to keep 5 minutes for discussion. Okay, you may please start.
So the pointer is there. Okay. Good afternoon, everyone. I am Reggie Philippe from the Raman Research Institute in Bangalore, and I thank the organizers for giving me this opportunity here to talk to you. The title of my talk is Stoichiometry Analysis of Elemental Concentrations from LIPS Spectra Using an Artificial Neural Network. So as the title implies, we are trying to analyze the stoichiometry of a composite material, and we make use of laser-induced breakdown spectroscopy for this purpose. And in addition, we also use an artificial neural network for making this evaluation very fast and smart. Now, this is the experimental setup for LIPS. So essentially, we have a laser. So here we have used an INDIAC laser of 1064 nanometers wavelength, 7 nanosecond, 50 millijoule energy at 10 hertz. And then we have an energy meter for measuring the energy of the laser pulses. We have a vacuum chamber in which we keep our target, and then there is a light collection system which collects the light emitted by the plasma which is generated on the target, because when we focus our laser pulse, energetic laser pulse, onto the target kept in the plasma chamber, it forms a plasma, a small plasma there. The plasma plume I'll show you in the next slide. And then this is collected using lenses, and then it goes to a spectrometer, and the spectrometer will give the spectrum of the plasma. And from the spectrum, we will be able to identify the elements present in the material. So this is our own plasma chamber in the lab, and then I don't know whether, yeah, you can see that a plasma plume can be seen inside the plasma chamber. So typically it looks something like this. And why do we use LIPS for material characterization? There are some advantages. So first of all, we don't really need any sample preparation or very little sample preparation. For example, it is possible to do remote measurement. So therefore, particularly in space probes and planetary rovers and all that, we usually have a LIPS spectrometer, so that you only need to have a laser there. The laser beam can be focused onto a rock or sand what is nearby and generate a plasma there, and the plasma can be collected by cameras, and instant analysis of the material is possible. So that's what we see here. It's a plasma spectrum here. So from this we can see like barium, strontium, both these are present in this material. And it is possible to simultaneously quantify all the components present, but there are some challenges as well, like there is a matrix effect where changes in the emission intensity can occur due to sample inhomogeneity, and there can be self-absorption effects in the system. So the overview of the work that we have done is how to use artificial neural network in the whole process is as follows. First of all, we either measure, or in some cases it's also possible to synthesize one LIPS spectrum like that, and then we model the laser produced plasma. LPP is laser produced plasma. We model that using equations. Basically, we synthesize the spectrum using the parameters. And once this is done, we generate thousands of synthetic spectra under the stationary state plasma model. That is one particular model which I will come to. Basically, we generate lots of plasma spectra by varying the parameters. And then a machine learning model is trained on these synthetic spectra. And once this is done, it is then possible to rapidly predict the elemental concentrations in any real measured spectrum. So that is what is done here. And the target that we have used is BST, which is barium strontium titanate. So this is the procedure how it is made. I am not going into all those details. BST is a ferroelectric ceramic material with a high dielectric constant with lot of applications in memories, in pyroelectric detectors, electro-optic devices and all that. And it is a ratio of barium to strontium that determines the dielectric properties of BST. So that's why in this kind of materials, there is a requirement for us to know what is the exact ratio. Now, once we make the plasma, we have to model it. So as I said earlier, there are a few things to consider, like the plasma can be inhomogeneous. Then there can be a nonlinear relationship between the elemental concentration and emission intensity that we haven't considered in our calculations actually. And the third one is self-absorption. So what that means is the emission by the plasma can be reabsorbed by the plasma to some extent. So we have taken care of the first and the third effects. And to take care of the first one, that's the inhomogeneity of the plasma, we consider a two-zone model. So what is done here, it is like, we consider that there are two regions in the plasma. So one is the core, which is hot, and then there is a periphery which is not as hot. It is colder in comparison. And we also consider that there is reabsorption happening in the system. So on this basis, so therefore, this is what we call the two-zone stationary state plasma model. Why I say stationary state is because we assume local thermodynamic equilibrium in the system. So separate LTEs for the central part and also for the peripheral part. So that is what is meant by stationary state. And now we start with, so what I do is I have the plasma like this. I'm looking from here, and then what I'm seeing is the emission which comes from the other side of the plasma. This is like kind of a conical, a cylinder which tapers. So light comes from the other side, it comes towards me where the detectors are. So therefore, it starts from the periphery, it travels through the central core and again travels through the periphery before it reaches me. So that's the way it works. So I have to start with a certain intensity I naught, and then I have to propagate that intensity through the plasma to my side. So in that process, I have to consider the initial intensity, which is given as B lambda T naught here, and then it comprises of black body radiation and also emissions from the various levels in the materials from the various energy levels. Then I have an absorption coefficient. I'll come to that later in the next slide. And then there is also the length of the zone that I am considering. So as I said, there is emission and also reabsorption. So this is characterized by the absorption coefficient K naught. What I have written here is for just one transition between two levels, but there can be many transitions like that. So therefore, I have to take a sum of all those transitions. Essentially, this quantity K naught is characterized by the transition probability. Then the Saha equations, which actually tell us what is the proportion of various ionized energy states that can be there in the plasma. Then there is a partition function, and finally there is a line shape function also there, which is Lorentzian. And here we consider stark broadening to happen in the system, and that is assumed to be the major broadening mechanisms as true in most plasmas, and therefore it is possible for us to find out the number density of the plasma, electron number density of the plasma, by knowing the impact parameter and also the line width of that particular transition. So once this is done, so this is the optical emission spectrum of BST, and this is collected at a gate delay of 500 nanoseconds and gate width of 1500 nanoseconds. The region of interest, that's what we have considered in this study, is from 402 nanometers to 460 nanometers, and that is shaded. So we have to estimate the stark width and the electron number density. So for this we have taken the TI2 line, so that means the first ionized state of titanium at 376.13 nanometers. This is used for estimating the stark width, and the line had to be deconvoluted because there are surrounding lines very close to this, and we find that the full width at half maximum is 0.12 nanometers, and it gives a number density of 5.33 into 10 to the power 23 per meter cube. So we use the radiation equation now to do the fittings. So these are the chi-square maps for the fit that we obtained. So in the first picture we see zone 1 temperature and zone 2 temperature on the y-axis. So the minimum chi-square value is determined, and similarly we also look for the number densities in zone 1 as well as in zone 2. So we have these quantities NE for zone 1 and NE for zone 2 as the inputs for our program. Now we have to validate the stationary state plasma model. So here we can see the simulated spectrum y hat, which is a function of the output, of the intensity that we have measured, then NE1, NE2, similarly then the temperatures of zone 1, temperature of zone 2, then the lengths of these zones L1 and L2, and also the elemental concentration. So F is a constant here, which depends on the instrument parameters basically. And so we find that we have a very good fit here when we run the program, and as we can see we have reference concentration. So we have tried the concentration of elements obtained are within an absolute relative error of 6 atomic %. So we get a reasonably good fit from this exercise. So this actually gives us, so we can basically run our program and we can find out the concentration. So then why do we really want to go for an ANN or an artificial neural network? The reason why we decide to use an ANN for this analysis is, first of all, it can be very fast. Once you train your system, once you do the machine learning, the finding the concentrations is extremely fast, as I'll show you later. And it is smarter because ANNs, because they work like our human brain, so it can model complex nonlinear relationships between spectral intensity and elemental concentration. Only thing is the program can be more and more complex when it gives you better and better results. It can predict elemental concentration even in overlapping spectral regions, and there is also more accuracy in the values finally given. So we have used the programs Keras and TensorFlow, which work with Python for the ANN. So how does it work? A basic neural network can be imagined as a function that accomplishes a task. They are computational models inspired by the human brain, designed to recognize patterns and make predictions. The network will consist of an input layer, some hidden layers, and an output layer. And if the goal is to find the elemental concentrations from the Lipse spectrum, the input layer will receive the spectrum and the output will just give us the concentration values. In networks, in an ANN, like in a similar way that every neuron in the brain is interconnected to many other neurons, here also each neuron is interconnected to every neuron of the previous layer through the program, and the connections act as weights, and each node has a value which is the weighted sum of previous nodes plus a bias term. So we have weights and biases, and for introducing any nonlinearity, an activation function is used. In order to learn, the model needs sufficient data. we need a lot of data to be fed into the system so that the model can learn it, which is fed in during the training phase. So this is basically what it is. There are three things. There are weights, there are biases, and there is also backpropagation. Frankly speaking, I'm not a computer person, so I'm not a computer scientist, so I can only tell you as much. So this is the way it works. And once the training is completed, the final weights and biases are saved, and then different input spectra will activate different neurons in the network due to varying weights, biases, and activation functions. And this results in the network predicting the corresponding concentration based on the specific input. So when we have more data, we have the ANN is better. So how do we get these many data? So in up to until very recently, for getting a lot of data for training the ANN, people used to keep on measuring. So you measure hundreds of Lips spectra and then use that as the input for training the for machine learning. However, this is not really required. We can generate spectra using only thing is you have to assume some models. I mean, you have to have some assumptions, which is true in any case. I mean, whatever you do with plasmas, you have to have some assumptions because it's a very, very complicated system. So once you have those assumptions, you can generate a lot of spectra. Actually, we generated something like 7,500 synthetic spectra, and then these were put into the program with the corresponding concentrations of B, S, and T, and also the plasma parameters. So that is what is done. Now this is a portion of the training and testing of the artificial neural network. So we put in what you see on the upside is those red histograms. They are the stuff that we put into the system during the training phase. And what you see down there, the green ones, are what the system gives back to us. So we can see that there is a very close correlation between what we have put in and what it has given back to us. So that means the learning is fairly good. And so here, basically, the time that we need for doing all this is for generating synthetic spectra and training the model. It took about 3 hours. So once we do this, I mean, I haven't counted the time it takes for measuring some of the initial spectra. If you have a system which is working, which many labs which work in plasmas, they have an experimental system that works. And there, I mean, maybe for taking 4 or 5 spectra, I mean, very good spectra, you may take a day or something. That's what I would say. Now, once you have those spectra, then for generating synthetic spectra and training takes only 3 hours. And once trained, the model can calculate the concentration of 100 samples in less than 1 second. So that's the kind of speed it has. And all this is done on a basic laptop. Now we test the neural network on experimental data here. So this is the prediction of concentrations of 5 BST samples, and we had taken 20 experimental spectra for each sample. So in total, we took 100 spectra. So that's our input. Now, here you can see the reference atomic percentage of barium in the first figure, the reference strontium atomic percent, the second figure, and the reference titanium atomic percent, the third figure. You will see that, in fact, we had varied only the percentage of barium and strontium. The titanium percentage was kept a constant. So there you can see how much variation the ANN, it gives some variation, by the way. It's not a perfect fit or anything. So on the titanium, you can see how much variation is possible. So even now, this is not a perfect program or anything, but we are just beginning. This is our very first work in this direction. So we are satisfied with what we get. Particularly, you can see in the first figure and the second figure, the fits are not so bad. I mean, they're pretty good fits. So the mean absolute error is less than 4 atomic weight percent in, from all these calculations. So the conclusions from this study is that we have used a stationary state plasma model to generate synthetic spectra to train an artificial neural network. negating the need to collect thousands of experimental data to train the ANN. Only one similar paper actually had appeared in literature so far, means, I mean, this paper came in May 2024, and for the last 2 months, I haven't checked personally, so maybe some new papers have come. I understand that in CAT also, in RRCAT also, people are working in very similar lines. So we expect quite a bit of papers to come out soon, like, in the next 1 year or something. Anyway, in this particular work, the authors had considered only one zone and no reabsorption. So we have put 2 zones, and we have also considered reabsorption of the emitted light. The ANN is capable of predicting elemental concentrations in materials within fraction of a second compared to conventional techniques which take much longer times, and can be used for quantitative elemental analysis in industry, in thermonuclear plants, planetary exploration, underwater conditions, and many other situations, of course. And I would like to thank my colleagues, Professor P.R. Biju from MG University, Kottayam, Amok, a joint PhD student with me and Professor Biju, Sebin, who was working with me as a research assistant. Now he has joined a PhD program in France, and then Gina, who works with Biju. These are the people who are involved in this work, and thank you very much for your kind attention.
Thank you, Dr. Philip, for timely completion service. So now talk is open for questions.
Thank you for this beautiful lecture.
Thank you, sir.
I have just some 2 basic questions. One is that what sort of computer you require? Is a normal laptop will work, or you have a special?
No special computers for this purpose. We used 2 computers. One is a normal laptop. The other one is a normal laboratory PC. That's all.
Okay, fine.
Yeah.
And the second question is this. See, when you draw you have shown a drawing of your flame, that flame that is produced.
Yes. Yeah.
So you show some red core, and then you show some yellow.
Okay.
What is the meaning of that?
Oh, that's a temperature. The core has the highest temperature.
No, we understand that the temperature will be, but why then 2? Why not 3? Why not core and 2 layers? Why is the core and only 1 layer?
Okay. I think you are asking why we haven't considered many layers, isn't it? Yeah, that's a very valid question. The thing is, it is computationally intensive. So we are beginning now. So in this first phase, we have considered only 2 layers. We will be considering more layers in future.
Okay.
Sir, just wanted to ask you that suppose you reduce the pulse duration to femtoseconds. So that expansion behavior is quite different from the nanosecond pattern. So there may be these 2 temperature distributions can be reduced to 1 or continually graduating 1. So the model can be simplified, number 1. Number 2, this is done for a particular BHT compound, and that is applicable for this one. If we vary the other component, suppose we take another molecules or another composite, then we have to repeat the same process once again, right?
Yes. We have to repeat the process because for every material that we are trying to study, we have to take some initial spectra, and then we can synthesize spectra, and then we can do it. And regarding your first question, temperature variation will be there irrespective of whether this is a femtosecond or nanosecond plasma. The only difference between these 2 is that when we generate a plasma using a femtosecond pulse, the pulse itself does not interact with the plasma. But when we generate the plasma with a nanosecond pulse,
that is precisely I am saying.
Yes, then the pulse, there will be variations in the temperature, absolutely.
Probably the number of lines in the Lieb spectrum will be much less in case of the femtosecond or sub-picosecond one.
Yes.
So whether that can help in identifying or quantifying the compositions?
I don't know the answer to that, whether it is more helpful that way. We have to really do the experiment, then we will know.
Any other question? Yeah, Sunita.
Yes, sir. So actually, I have a question about the synthetic spectra that you have generated. So I believe the synthetic spectra have been generated for the like BST compound,
Correct.
and you are also testing the pure BST compound.
Yes.
So
Not
when
pure.
Yeah, like the synthesized in your laboratory.
Oh, the BST compound.
Yeah,
Oh,
yeah.
no, we haven't synthesized it. We don't synthesize. We have just got it. We purchased it.
Yeah. But you know the concentrations.
Oh, yes.
Yeah.
Yes.
So when we go for practical thing, like matrix effects are always there, and sometimes they're unpredictable. Like we don't know what kind of matrix it may be.
True.
So when you are generating synthetic spectra, so what kind of changes you are making? Like you are generated thousands of spectra.
Yeah.
So what kind of randomness or the variations you have incorporated in your spectra?
Yeah, so initially we actually find out the values, like we find out the number densities, the temperatures, then the lengths, then also the concentrations of these materials. So once we have that set of parameters, we vary them. So we vary them within the normal bounds, which we know, and that's the way we generate the synthetic spectra. For every set of these different parameters, there will be one spectra. So like that, that's why we have to make so many spectra. Depending on the number of parameters we have, when we change them, we will have to make lots of spectra. That's why we ended up with 7,500 spectra, but then it doesn't take much time.
No, that doesn't take much time, but like from practical point of view, can we address the unpredictable matrix effects and all these things, because it cannot be the only BST compound always.
Yeah, we have
some
to
impurities and some overlapping from some other elements and all these things.
The other elements. We haven't worked with other materials actually. So unless and until we really start, because we are planning to work a little more in this direction, when we do that with other materials, we will get to know how things are going to work. So probably then we may have to increase the number of synthetic spectra that we make. We have to look at the bounds of these parameters. But I still believe that even considering the matrix effects, still we will be able to get some reasonable values for these concentration values. I mean, that's my hope on this, because whatever we have done so far is pointing towards that direction.
Thank you.
Thank you. Sorry?
Yeah. So
yes,
yeah,
yes,
so
absolutely.
maybe
Correct. Yeah.
Is there any other question? Yeah. So yeah. Okay. So thank you very much. And I understand that you have started doing this, and AI is very important.
Yes.
So probably if you can comment on the accuracy part with AI. So before AI and after AI, if you are in a position to comment that, that will be of good information.
Yeah, I would say that it all depends on the training, how we train our program, how dense is the learning.
So in this present examples, do you have the figure like before AI and after AI, the accuracy part?
No, we don't have a figure like that, because we haven't made such a comparison.
Okay.
So therefore, I don't have a figure
So
for that.
probably more testing is required, then you will be able to do that. But it's important work, so thank you very much, and
Thanks
good
a
work.
lot.
Congratulations.
Thank you very much.
Okay, so let's give him a big round of applause. We can, yeah, so there is
now I
a
request the chair
formality.
to, present a memento to our speaker.
Thank you.
Now I request Nikita to bring the Nitika. Sorry.
Thank you very much. Thank you. Thank you.
Thank you, sir.
So now we are moving on to the next talk. So probably you can flash the speaker's profile. Okay, so the next talk is from Dr. S.K. Ravi. Yes, so please set it up. Okay. No, the speaker's profile first, please. Show the profile.
Just copying it.
Okay. So Dr. Ravi is from IIT Hyderabad, and he is going to talk on hot carrier dynamics in halide perovskite nanocomposite for optical applications.
Sure.
And yes, his profile was not flashed, so probably please do that first.
Okay, probably he wants that.
It was flashed for a while.
It is okay. I think
Okay,
we are all tired.
Okay, so
yeah.
So anyway, it's ultra fast session, so even I missed it. So sorry for that. Anyway, that time can be added to your presentation. That's more important.
Fine, yeah.
So you have 30 minutes and maybe a few minutes for discussion. So
Yes,
Dr. Ravi,
yes.
please.
Yeah. Good evening all. I'm used to telling good afternoon, good morning. So today it is good evening. And this being the last talk, I thought I should excite you all with a discussion on the hot carrier. So what is hot? We'll talk about it. And before I start that discussion, I would like to thank the organizers for the invitation. Yeah. So this work is on hot carrier dynamics in halide perovskite nanocomposites for optoelectronic applications. Now, one of the points which I would like to highlight before I get into the talk is that these halide perovskites have been a chameleon kind of thing, material, and our group has been working for last 5 years. Many things are possible. I would just confine ourselves with this discussion on this dynamics part because it's a laser community. I thought I will concentrate mostly on the application part of it from the lasers perspective. So I come from IIT Hyderabad, Department of Physics. Well, all the funding from various sources, including BRNS. These are the students who worked quite a lot last many years. I thank them all and my entire network of people. Importantly, Professor Venugopal Rao, whose laser I have been using last 2 years because our laser was down. And yeah, this is the laser facility which we have it. Probably this is the only one right now in India from Amplitude. It's a hybrid system where we have the option of having 1 kilohertz amplifier up to 5 millijoule, delivering 5 millijoule output. Also a 10 hertz, delivering output of 50 millijoule. Pulse duration is 35 and we also have a OPA. Yeah, perfect. This is OPA. Yeah. Now, over the period, we worked quite a lot on various aspects of study on the exotic optical materials. I just recorded a few things. Main expertise with the ultrafast transient spectroscopy, where we sort of showed, this is one of our seminal work where we showed about the multi-step electron injection in a dye-sensitive solar cells. And in fact, I will not discuss more about it, but this work goes on to say that, injection can happen as fast as sub 500 femtoseconds from a much higher states. Again, it's another hot kind of work where the extraction is happening at the higher singlet state. This is another work where we talked about the torsional dynamics of a molecule. Then we have done quite a work on this luminescence spectroscopy. This is the latest work which we had in 2023. We made our own solar cells, and again, this is the device part of it. And recently we have ventured into making indoor photovoltaics. That is another nice idea where we want to use this nice highly absorbing materials to harvest light, indoor light, like something like you can have a photovoltaic device right in this room and still generate. So this is very important for the IoT kind of applications. So having said this, let's go back to my talk where I present our results on 2 important aspects. One is the doping of cesium lead bromide nanocrystals. Now this is a strategic co-doping. I will come to it why it is strategic co-doping. Then we also show how the nanocomposites can be used for various applications. In fact, for both of this, I am going to discuss how the study which we get from ultra-fast time scales help us in understanding the improvement in the performance. Okay, so again, word to inform, when I am talking about it, I would not discuss much over the material aspect. We can talk about it or we can discuss, I will share the papers with you later. So what are these halide perovskites? Now these have been very well explored in the field of optical materials last many years because they have excellent absorption, high PLQI, high charge carrier mobility, tunable band gap, very narrow emission line width, and easy solution processability. So it's easy to make. absorption is very good, and importantly, compared to other, organic, this kind of systems, they have high charge carrier mobility. The solution processable system, they're high charge carrier mobility. And this is the typical structure you have, ABX is a perovskite structure. They also have exhibited low dimensional hybrids. Now, the main difference between a quantum dot or a nanocrystal of typical semiconductors like cadmium sulfide, cadmium selenide, the difference here is that how this particular network is going on. So you can have a 3-dimensional network of it and make it very small. That would be a 3-dimensional perovskite nanocrystals. You can make sure that it's possible to confine the formation of this network in 2-dimensional, which gives you this 2D hybrid. It's a 2-dimensional material. Now I can also do this nanowire thing where the growth of the confinement of this, networking of this unit cell can be in one direction. That gives me 1D, and that can be how the confinement happens. You can have phase sharing, edge sharing, corner sharing, multiple things are possible. And we can simply make isolated, unit cells which gives you the 0D. So each of them have their own properties and they have their own kind of applications. So what I am presenting today would be nanocrystals which are of 3-dimensional networking. So size is still sub 10 nanometers, but they are 3D perovskites. Now why it is useful is that these are all direct band gap systems. Majority of it, recently people have figured out ways to make indirect. Okay, so importantly, the valence band maxima is composed primarily of the halide P orbital and metal, which is the B is the metal, S orbital, where the conduction band minimum has mostly the P orbital character. In 3D perovskites, the polarizable lattice screens the electrostatic attraction between the excited electrons and holes. This leads to small exciton binding energy. The exciton binding energy is small, because of which it has been used quite a lot for the perovskite applications, solar cell applications. And well, a lot of other things were also studied because of its tunability in terms of shape and size. Okay. Now this is the representative, this is a 2023 review article I just showed. I wanted to flash you to suggest that it is not a new material. It has been explored quite a lot, but the earliest was in 1958, and recently since 2014, what all one can think of from an optoelectronic application, it has been demonstrated with these materials. Be it a solar cell, which is now 26% and more, tandem solar cell, this is 31.3% is what is here, but experimentally, lab wise it has gone across 33%, dosimeters, lasers, and so on and so forth. So a lot of things have been done. Okay. Now what I am talking today would be on hot carriers. So let me just give you a quick background on what is hot carriers. So it's simple, all of us know when we excite a material, semiconductor avoids band gap, the excitation happens into the higher levels of conduction band, and then various things happen. Okay. Once you excite it, higher excited states of conduction band, then these are various things happen. So first thing is carrier thermalization. Okay, I just read it out for you. So you have this carrier lattice elastic scattering, which is hot electron interaction, which is less than 100 femtoseconds, which is called thermalization. So hot carriers occupy states through Fermi-Dirac distribution. Then you have start the cooling process. Okay, so this hot carriers starts getting cooled and come to the lower vibrational level of the lower level of the conduction band. Okay, so much higher than the lattice temperature. The temperature is still high, and this would start giving away through the lattice, right? So the hot electrons, energetically hot electrons, as they come down, they give up its energy to the lattice, and that's how you have the hot carriers losing the temperature while scattering with the lattice phonons. Now this is how the interaction of hot carriers with the lattice phonon happens. Okay, the black waves are the wave packets are the phonons, and colored ones are the hot carriers. So finally, hot carriers lose the energy and attain the temperature of the lattice. So typically, all these things happen between 100 femtoseconds to some tenths of picoseconds, and over the period, the electrons start stabilizing, and eventually it can be extracted using your device and to the energy selective layers, and the device works. Now, that is how it happens in actual device. Now, when we say hot carriers, there is a possibility if you can smartly find suitable energy selective layers, it's called ETL, okay, to extract the energy to hot electrons before they relax down. The reason is if you let it to relax down, there is every chance that there may be loss of these electrons happening, and our interest is to find a way to extract those hot electrons which are thermal before they go into the thermalization. So one of the points about those who are in the solar cell field would know that there is a Shockley-Queisser limit where major loss is through the thermalization with above band gap excitation. So that is something which can be thought of, and people like to extract it. However, no practically viable perovskite based hot color solar cells exist. Theoretically it is possible, but practically no one could do it. Nevertheless, the long diffusion length and extended lifetime of hot carriers highlight perovskite's promising potential for such applications. So we tend to work and see if we can really. So the idea here is that explore materials, see which can be used for delaying it, figuring out how to find a way to delay the cooling rate, and see if there is a possibility of making a device. So that is what people have been trying. These are just 2 papers in literature, and it is not just 2, lot many. These are all the papers which talk about hot carrier solar cells with perovskites, okay? And many techniques have been used. This is just from 2014 to 23, it's in this paper, last year paper. Now, what we do is we try to do a fluence dependent transient absorption spectroscopy study and obtain the carrier transfer temperatures. So idea is simple, you vary the fluence of your pump probe data, pump probe excitation, and you normalize the data, what you get it right in terms of EV. Then there are nice theory which is already existing, and you can use this particular theory to fit and obtain the temperature of these electrons which are hot, initial hot, okay. So I'll not read this, you can just look at this paper and get it, or we can discuss it later. Now, few recent papers have come which people have tried to do it. This is a 2025 paper, both are 2025 papers. Last month it has come, where they talked about hot carrier enabled photodetectors and also hot carrier enabled photodetectors with hot hole electrons. So this is from the IICS Kolkata group. Now what we wanted to do is similar, just that instead of figuring out what is the right selective layer, we thought we can strategically dope and see if there is a possibility of delaying the cooling rate. So that's the point which we tried to do in this work. The initial work on the publication and the data of the detectors are already published, but the story of hot carriers is not published. So I'll make a full story for you so that it is easy for you to understand what is happening in this work. Okay? So this is a silver bismuth co-doped CSPBr3 nanocrystals. We made the nanocrystals in the lab with hot injection technique, and these are all sizes less than 10 nanometers as I said. And the co-doped, which is AGBI co-doped, has 8.7 nanometers. CSPBr3 pristine without the doping is 8.6. Upon doping with bismuth, it has gone to 9.1. Silver, it has gone to 10.9. So one of the things which I would like to highlight is the moment we do the co-doping, we are able to come to the size closer to the pristine. Okay, so that is one point which I want to explain. Then the photophysical studies, we see that the absorption is more or less slightly varying. However, the PL is changing with doping. So this is the black one is the pristine. The bismuth, moment you dope with bismuth, PL quenches. If you dope with silver, PL increases, and we co-dope it, it is somewhere in the middle. Okay, so that is the main thing, and also this is the time scales. Let me not talk about it anymore. Now when you look at why did we do that? Why did we do the co-doping? So to check the reason why we do it, we check the ultraviolet UPS spectroscopy, where we find that upon doping and co-doping, the Fermi levels is shifting. So this is the simple raw data, and this is what is the numbers which we extracted from the raw data. 4.442 is the Fermi level of the pristine nanocrystals. Moment you dope with bismuth, it becomes N and doping, and Fermi level shifts towards conduction band. And if you dope with silver, it becomes P type. Fermi level shifts towards the valence band. Now when you co-dope, what is happening is very interesting. It is almost coming to the pristine Fermi level. However, by virtue of these dopings, we introduce the donor acceptor states, which is here, right? So these are all shallow states which you talk about it. Okay, so that's the main thing which we say. And now when we want to look how this would behave in terms of the device. So one of the ways to do the device is to make a ETL layer, electron transport layer, which is the titania. Typical devices have titania, and this is again the energy selective layer, as I said to you. So we want to see how this would behave, how this would behave in terms of TiO2. The idea is that how the injection happens, charge transfer happens. So now That's what we do in the pump probe spectroscopy. This is a just 2D picture. I'm not really interested in this. You can look at the paper. The point is the various injection dynamics which we try to fit with the kinetics, and we say that upon fitting with when we do the pump probe with perovskites, doped perovskites with titania on it, the injection is faster. This is the 180.8, 180 picoseconds is the typical time scales where the injection completes. Okay, for the pristine, moment you do the AGBI co-doped on titania, on titania this is 180, and on titania it becomes 112, it reduces quenches, meaning that there is a injection. Moment you do the AGBI co-doped, it has come down to 86, which means that there is a efficient charge injection happening into it. Right, faster components represent the carrier trapping, slower components represent the excitonic recombination. The faster components become much faster with titania layer, confirm an increasing rate of charge transfer. Right, then start looking at what is the contribution of this hot carrier. Okay, so that's still unpublished, so we are continuing to writing the paper right now. So one of the things, as I said, is to do fluence dependent study to into pump probe data. Okay, so TS spectra of the pristine and AG doped consists of typical CSB sandwich between the two PA. So this is what it is. The high energy stage tail of the GSB contains the information of the hot carrier, as the GSP is the ground state bleach, indicates the minimum energy required to excite the ground state. So this is the ground state bleach which we have, right? And then when we extract the temperature upon fitting, it's quite a lot of procedure. Maybe I take the inputs from Professor Reggie and see if I can do some AIML coding. So one can extract individually, do the fitting part and get the temperatures for each time scale and see how the temperatures vary. And this is the hot carrier temperature calculated with the MB statistics. I showed you one of the slides. Once the carrier reaches the quasi-equilibrium state. Due to the dissimilar hot carrier dynamics, hot carriers buildup is also different with dissimilar end of initial hot carriers. So this is how the variation happens. Importantly, if you look at it, this is the time scales when the hot carriers are there, and here the pristine has a faster, has a hot carrier lifetime of 351. Okay, when you do the AGBI, it is 483. It is slowed down, right? Then when we fit the temperature with the WHM, right? This is the gamma LO phonons. What we get, LO is the longitudinal optical phonons. We see that the pristine and the AGBI, the numbers are almost the same. With bismuth, this phonon has increased strong. With AGBI, it becomes strong. So higher coupling strength in the case of bismuth doped nanocrystals, faster cooling growth as excess happens. So the point is, for each doping, we see that carrier relaxation is changing, the phonon coupling is changing. Okay. Now finally, when we look at the fluence dependent data, we see that the fluence dependent indicates the observation of phonon bottleneck, which increasing the fluence, which is more pronounced for the AG and AGBI co-doped. So by AG and AGBI, the phonon bottleneck shows up and the delay happens. So carrier cooling is becoming more, or in other words, the temperature is relaxing bit more slowly because of this phonon bottleneck. Now that doesn't end the story. Okay, we also studied the calculated energy rate. The energy loss rate has been calculated to examine how hot carriers is relaxed to the ground state. A higher energetic carrier, or the carrier with high energy, rapidly loses its energy, as we can see the loss rate is higher for higher temperatures. Once the carrier reaches the lattice temperature, energy loss decreases, higher excess energy gained by the carrier increases the LO phonon accumulation and prolongs the relaxation dynamics. So overall, if I look at these things, we have this for AG, the dynamics is up to energy loss rate is 232. For AGBI, it is 160 femtoseconds, and CSPBR3 it is 130 femtoseconds. However, the fastest is for the bismuth. Then we do the temperature dependent PL studies to obtain the binding energy of these materials. Okay, we find that for the pristine, the binding energy of the excitons is 64.7 MeV. On the other hand, for the AGBI, it has come down further. It is 46.5. And the lowest among all these things is the bismuth. Okay, so bismuth binding energy is low. On the other hand, for the silver, the carrier cooling is more. Okay, now AGBI is co-doping is a sweet spot in the middle, and that's what we see when we do the pump probe. When we do the device, we see that the device's performance has gone very high for the co-doped case. And how high it is like 900% increasing the photocurrent, 600% increasing the responsivity, and 650% of the detectivity. So it is simply by choosing the doping, by making sure that you can play with the shallow defect rates, you can play with the critical dynamics between how the external binding energy and the hot carrier cooling rate can be controlled, one can get a better device, and that's what we try to show here in this work. So when we compare this with the existing literature, numbers are good. I will not go in detail of this, you can look at this work. So overall, in this story, what I would like to inform you is that by strategic dopant and co-doping strategies, one can really improve the device performance, not by trial and error, but rather with a really scientific way of looking at the external binding energy as well as the carrier cooling rate. So that is one point. I think I have just 5 more minutes, I'll finish the next part of my talk. So this is the idea how we can do the nanocomposites. Earlier I said about this particular material by doping, how we have done the photodetector. Now we show by taking a nanocomposite of WS2 and CSPBr3. Now this is the idea which we have. WS2 nanosheets are made, were synthesized with hydrothermal, and CSPBr3 is used to synthesize with the hot injection. So again we do that in the lab. Now once we have these two materials, we simply put them in a sonicator and sonicate it overnight. So after what happens, because of this, they keep hitting each other overnight and start forming small nanocomposites with van der Waals interaction. And we try to look at such materials and see how these materials are used for the detector applications. Before that, we want to say the same story with the carrier cooling. Now the story is clear. Do the pump probe, fluence dependent pump probe, calculate the temperature, see how the temperature is changing, and our story is there. Okay. Now that is the thing which we do this. Now this is the WS2 CSPBr3 hybrid nanocomposites. This is absorption. Okay. This is the PL quenching and faster decay nanocomposites as compared to the nanocrystals describe the electron carrier transfer from the CSPBr3 to WS2. So the electron injection is happening from the, it forms a type 2 heterojunction. So electron injection happens from the nanocrystals to the WS2 nanosheets. Okay. Similarly, the enhancement of PL is happening specific to the WS2, and that may origin from the energy transfer to the nanocomposite. So we have a situation where energy transfer is happening as well as electron transfer is happening. So all these things are possible with basic steady state studies. Okay. Then we do the pump probe measurements, and here you have everything. This is the WS2 specific to the WS2, specific to the CSPBr3 and the composite. So you see the contribution of WS2 peak here, CSPBr3 peak here. So both are there, but you will find the variation somewhere in the middle, and that's what we try to explore and understand how it is happening. Okay, so this is the fitting part of it. Now the decay is faster in nanocomposites at CSPBr3 nanocrystal regions as compared to the pristine, indicating electron transfer from CSPBr3 to WS2. This is a clear demonstration. The decay is slower in nanocomposite at WS2 nanosheet region as compared to the pristine nanocrystals, because this again has a situation where the electron injection happening from DSPBr to WS2 as well as the possibility of hole transfer from the nanosheets to nanocrystals. So both ways electron injection, the carrier electron injection as well as hole transport is happening. Right, then we do the fluence dependent TAs, obtain the temperature fitting, and what we conclude with all the work, this is right now under the second revision, it should come through in another 2 weeks in small. Again, I'm saying it's a long paper, I'm just discussing only specific to this audience. The obtained maximum carrier temperature for CSPBr3 and the nanocomposite is 856 Kelvin and 1081 Kelvin. It's really hot in the nanocomposite. The values of carrier temperatures range is between 572 as well as 73 for the case of nanocrystals and nanocomposites under various fluences. Now the electron phonon scattering effect makes the accumulation of hot phonons that lead to the slowdown of the cooling in order of few picoseconds, indicating a occurrence of phonon bottleneck. So using this kind of nanocomposites, we also demonstrated there is a hot phonon bottleneck, and this is what is the schematic which is happening. You have the electron transfer as well as energy transfer. That way both are seen. Importantly, in these nanocomposites, we see that because of the way that electron phonon coupling is happening, the way the phonon bottleneck is intervening here, there is a slowdown of it. Because it is slowing down, it is possible to extract these hot electrons in a device, and that's what we see that upon this kind of, when you compare the device performance with CSPBr3 and a nanocomposite, we see the enhancement is again in terms of 400% and so on and so forth. Okay, so with this I conclude my talk. I just gave you a brief overview of the story of how halide perovskites solar cells are and how the carrier cooling is helping in terms of improving these performances. Presented you the fundamental understanding of carrier cooling in both AGBI and CSPBR3 WS2 nano composites, and I demonstrated how the overall effect of this cooling is helping in terms of increasing the device performance with the photodetectors. Okay, with this I thank you all for your attention, and thanks the entire NLS team for this wonderful conference, and yeah, please come to IIT Hyderabad.
Thank you, Dr. Ravi, for finishing in time. The talk is now open for questions or comment, if there is any. There is any question? Okay. So,
yes.
Yeah, please go ahead.
So these all materials are in photovoltaic mode that you are using?
Yes, it's a device. They can be made into solar cell, but we tried only the photodetector part. It's a photovoltaic. They are self-biased.
Okay.
Basically, you don't need to give bias. They just work as a photodiode.
Can it work as a photoconductive mode as well?
I think so, yes. It should work. But they are all self-biased means zero voltage. You don't need to give any bias. They automatically absorb light and current generates.
And the band gap, you are doing the band gap tuning as well?
Yes.
Okay, I'll talk to you.
Yeah. So depends on various, because this is just one more point. Other dopants also we have done. Yeah.
Nice talk. Thank you.
Any other comment or question? So I have one comment or query. See, in photovoltaic, normally injection of hot electrons is assumed to be a loss, because higher you inject in the band, they will go into thermalization, and you actually, it's a loss basically.
Yes.
So because you are collecting those hot electrons by putting a electron transport layer, additional layer. So how it is, because see from sun for solar cell, you are getting a continuous spectrum. You don't have a choice of energy.
Yes.
So in that context, how it will be helpful as a solar cell?
Yes, that's what I was trying to say. See, this the entire story what you said is the Shockley-Kozer paper in 1952. That 1962 said that is what happens, that when the above band gap is lost because of the thermalization. What we are doing is we are not letting it to thermalize. We are extracting it upfront. So
Yes.
before this thermalize, you take it out. If you don't take it out, then the thermalization loss is happening.
So that is where actually there are 2 points. One is momentum relaxation, another is energy relaxation.
Yes.
So you are concerned only about energy relaxation, but depending on how deep you inject in the bend, momentum relaxation is very critical. So that probably you have not.
We did not look in detail,
fine,
but
that's
we
before
believe
100
that
femtosecond.
Yes.
So in fact, we are also concerned about that. We have, you are not alone in this community.
Yes. Yeah.
So we
I
have,
know.
similar to you, we also have 2 OPA in our lab. So maybe sometime
we should
can
discuss
it
it.
later.
Thank you.
Okay.
Thanks
So
for the
with that, if there is no comment, we will conclude this session here. And on behalf of organizers, maybe you can come forward. We would like to thank Dr. Ravi for his excellent talk. And we can give him a big round of applause. Thank you.
Thank you.
So we close this session here.
As a token of gratitude, we would like to present a memento to Professor Sharma. I request Dr. V. Ganeshan, former director of UGC DAE CSR, to present a memento, please. I request Nitika to bring the memento. Thank you, sirs. Our special guest has arrived. We are just about to start the special session. Please remain seated.
फर्स्ट आप ये दो स्लाइड दिखाइए, these two, this one and the other one, earlier one, ठीक है? And उसमें डाल इसको हटा भी कोई बात नहीं, इसको निकाल सकते हैं इस वाली साइड को। अच्छा अच्छा, फिर क्या करेंगे? तो अभी क्या करना चाहते हैं? अभी ये प्रेजेंट कर दीजिए, वो पहला वाला दोनों अलग अलग करेंगे, ऐसा करते हैं, ऐसा कर सकते हैं ना, वो तो कर सकते हैं दोनों के। पहले आप उसको करिए अलग से, ये हमारा भी दिखाया था नहीं, ये नहीं, ये तो खुला ही है, ये तो नंबर उसको दूसरा हो जाए। देखो देखो ये हो गया, एक ये ब्रेक ये होता है, पहले वाला इनको खोल देते हैं, जब दिखा दो कौन सा चलना है। हाँ, ये वहाँ से शुरू करेंगे, फर्स्ट एंड सेकंड, इसके बाद सेकंड, पहला दूसरा ये आएगा, तो हो गया, तो उसके बाद वो आएगा, ठीक है। आप मेरे को बताने के लिए रुक जाना, ये तो इसको फुल कर दो अभी, ये पहले करेंगे, दूसरा करेंगे, फिर उसके बाद वहाँ से शुरू करेंगे, ठीक है? सॉर्ट करना पड़ेगा लास्ट में, ये कैसे होता है भाई? कब होता है, क्या गलती किया होंगे इसमें? बटन दब गया, मैं इसको खोल के उसको देखा आया, अभी हाँ, और बताएंगे, कोई बोलेंगे क्या? ठीक है,
नीचे आइए, मजुमदार सर जी थोड़ा सा ब्रीफ करेंगे फिर।
मैं इसे खड़ा रहूँ?
नहीं नहीं सर,
आप हाँ उधर बैठा दीजिए, खड़ा। नहीं नहीं खड़े होके, हाँ बिल्कुल, वहाँ जाएंगे बैठने, इसको चाहे बंद कर दो अभी, जो दोबारा लगा सकते हैं, वो बोल रहे हैं, चलो कोई बात नहीं।
Good evening, everybody. So now we will begin our special evening talk session, and as you know that we are honored to have with us today Professor Jaypal Mittal, one of the eminent scientists in the field of chemistry. So let me, I am sure that many of you do not have any introduction of Professor Jaypal Mittal. So it is my pleasant duty to introduce him formally to you. And basically he is a luminary in the fields of photochemistry and radiation chemistry. Now, born on September 21, 1940 in Meerut, Uttar Pradesh, Professor Mittal's academic journey commenced at Agra University, where he obtained his bachelor's and master's degree in chemistry. In 1959, he embarked on a pivotal phase of his career, joining the training school of the Atomic Energy Establishment. Now it is called Bhabha Atomic Research Center, marking the beginning of his profound association with atomic research. Professor Mittal's pursuit of advanced knowledge led him to the United States, where he undertook doctoral studies at the University of Notre Dame, Indiana. Under the guidance of Professors A.L. Lamola and W.H. Hamill, he earned his doctorate in 1967, laying the groundwork for his future pioneering work. His academic excellence attracted the attention of Nobel laureate Willard Libby, who invited him to conduct postdoctoral research at the Radiation and Nuclear Chemistry Laboratory of the University of California. Subsequently, he accepted an invitation from Nobel laureate Willard Libby to conduct postdoctoral research, and in 1969, he returned to India, driven by a deep sense of national duty, and joined BRC as a pool officer. He embarked on a path of groundbreaking research in photochemistry, and his expertise was further honed during a year-long stint with Professor E. Han at the United States Army Natick Soldier Research, Development and Engineering Center in 1971. Upon his return in 1972, he established a formidable research group at BRC dedicated to advancing the frontiers of photochemistry and radiation chemistry. His visionary leadership was evident in the organization of the first national symposium on fast reaction chemistry and techniques in Trivandrum, which was a landmark event that fostered collaboration in innovation within the Indian scientific community. Professor Mittal's career at BRC ascended to remarkable heights, culminating in his appointment as the director of the chemistry and later he also, after demitting his office, he was DAE Rajaramana Fellow. Professor Mittal's significant contributions include the development of a nanosecond Linac-based pulse radiolysis system, enabling advanced studies of chemical dynamics using nano, pico, and femtosecond pump and probe techniques. He is widely recognized for initiating a new school of research in radiation chemistry and photochemistry in India, and his group achieved notable success in isotopic enrichment of hydrogen, carbon, and uranium isotopes. Professor Mittal's profound impact extends beyond BRC. He holds the esteemed position of M.N. Saha Distinguished Professor at the National Academy of Sciences, India, and serves as a Distinguished Professor at the University of Pune and the Indian Institute of Technology, Mumbai, nurturing the next generation of scientists. Professor Mittal's prolific research has resulted in over 300 scientific papers published in peer-reviewed journals, documenting his groundbreaking discoveries. He has mentored numerous doctoral students, leaving an indelible mark on the scientific community. Professor Mittal's leadership is demonstrated through his extensive involvement in professional organizations. He has chaired various basic science committees of the Board of Research in Nuclear Sciences and served as president of the Indian Society of Radiation and Photochemical Sciences, the National Academy of Sciences, India, and the Asian Photochemistry Association. He has been a council member of the Indian National Science Academy and currently serves as president of Asian and Oceanic Photochemistry Association and is a member of the Education Council of the University of Allahabad. He is also a past president of the Indian Chemical Society. Professor Mittal's contributions have been recognized with numerous accolades, including the Padma Shri in India's 4th highest civilian award in 2003. He is an elected fellow of all 3 National Academy of Sciences, the Indian National Science Academy, the National Academy of Sciences, India, and Indian Academy of Sciences. He is also a fellow of the World Academy of Sciences and the Maharashtra Academy of Sciences. He is a recipient of the Professor T.R. Seshadri 70th Birthday Commemoration Medal, the Golden Jubilee Commemoration Medal, the Fulbright Scholarship, the Humboldt Research Award, the Senior JSPS Award, the N.R. Dhar Memorial Medal, the Goel Gold Medal, and the Indian Science Congress Association Platinum Jubilee Award. Ladies and gentlemen, please join me in extending a warm welcome to a true pioneer, a visionary scientist, an inspiring mentor, Professor Jayapal Mittal. Sir.
Thank you very much, Professor Shovan Majumdar. However, my 10 minutes are not counted. We are lecturing such a long discussion. Anyway, when few weeks ago, when I received a letter from him, he said, I would like to very much invite you for an evening lecture. I thought I have given many scientific talks, but what is this evening lecture going to be? Then I remembered in various countries in America, etc., when they do evening lectures, somebody comes and with lots of jokes, and people are taking dinner at the table, and then they will joke and give many things of that kind. So I told him, hey, I cannot give evening lecture. If you want, I give some scientific lecture. That's what I have been doing throughout the life. But he said, no, sir, this is a program. We have to do evening lectures. So then I thought for some time, and I looked at my life, and this is the general thing first slide is showing, that for all of us, it must be true. There are 4 stages in the research scientist life. The first stage is you will do the work as a student, an advisor of yours gives the talk somewhere, right? You must have seen this happening in all of our cases. Second stage is when you are becoming a little more mature and you are looking for some awards or some Bhatnagar award and things of this kind, then you do the work and you will go and give the talk at different symposiums, different audiences and say, well, look, I have done this, so that I should be awarded for the kind of thing. Number 3, when you become a little more older, your student does the work and you go and give the talk thinking that, look, this is what the work is going on right now in my laboratory, but basically it is the students who are doing. And last one is nobody does the work, but still you give the talk. So I thought maybe this is the reason I have gone to this stage. And you are supposed to be giving talk, not on scientific thing, because you think you have become old enough now, don't talk about science. You give some general, futuristic, saying that what country needs, what science changes, syllabus has to be required, societal talk, burning issues, of the whole country, that something has to be done for that, science, where the role of science comes in the development of the country, and things of this kind, general things which you can talk anytime, while in the sleep also you can say all those things, but that's what happens at this time of the day. Let me see now, next slide. Where is the next slide here? Page down, is it? Yeah. Okay, you can see the same thing being told. What is written there with respect to age? You will see, where is the pointer here, please? Pointer. Good. When you start, you are a student, somewhere about 25 years or so at this time. You will write independent research proposals, defend, establish a laboratory of your own, and number of papers increase will give rise to the more grants, and that's 100% of the time in this triangle, you will be working hard to do this kind of a thing to get more and more grants, write to different agencies, go give seminars. After 45, you start looking, or before 45 years, you start looking recognitions, Bhatnagar Award, this and that, etc., and give attraction at the peers. So you will go to the symposium where C.N. Rao is there and other people are there so that you can show, look, this is what I am doing, so that people will know you in the companies when it's going on. When you go up slowly, you start doing less and less work now, as you can see. Instead, you will start giving review articles, and more others with their own hard days. You start more time in committees, sitting committees, promotion committees, and various types, and an expert on this kind of a thing. And you spend more time in dinners, advisory committees, etc., and giving all stories, which I am doing right now. I am at the start. Then I remember, now the evening talk comes here. Evening popular talks. Science is forgotten. You give something else, etc., of the talk. But so now I understood why the evening talk was required for me. But now let us see what kind of talk I will give, because it is difficult to change the culture of the people. I normally give scientific talks, but this explains. Next slide. Next slide. Go. बस ठीक है. नहीं ये अभी नहीं आया होगा next slide. चलो ठीक है कोई बात नहीं. So this time we will talk something about chemistry and some interesting things in the chemistry which we have all been told, but never understood what is happening in that kind and how lasers can help us to do that. And because it is a laser symposium, everything has to be done. So I thought we should say salute to the lasers which are doing wonderful jobs and solving some of the problems in different areas, whether it's chemistry, physics, engineering, biology. Now fantastic work is being done here at this biochemistry. Let us say, just to remind you of chemistry, what chemistry people do basically. Basically they take two compounds in a test tube, let us say, A plus BC, and then either give some kind of energy input, whether they give heat energy, whether they photon energy, whether it's the gamma ray energies, and finally see some new product coming out. A reacts with the B and you produce a new compound AB and C. So the A and B and C bond breaks and A reacts with that and reaction takes place. And normally this all chemistry we have learned in the books, A plus BC giving rise to AB plus C plus some energy either deposition. After some time when you go to higher class, they will say, look, this is what actually happens, but in between there is something which is intermediate state, which is called transition state. Henry Eyring got Nobel Prize to tell this idea that there is a transition state where A is approaching the BC. So this bond is getting slowly built and this bond is getting slowly weaker and weaker, and this happens. So finally, if this molecule contains some energy, it will give rise to fluorescence and you will see the after effect. So basically as a chemistry student, we know what we had before, A plus BC, by looking at different technique, gas chromatography, infrared, mass spectrometry, any of these things. And later on, what happens to that, we also know by many applying mass spectrometry and things of this kind, that a new compound has been made. But the question is, what is this transition state? This is called transition state, which also can be seen in some books. They will say there is a reactive intermediates here in between. Now the questions you can ask, or which our scientists ask, or chemists particularly, what has occurred by heating this or doing the energy? And then if they know what has occurred, that means these compounds have been made, this compound has been used up. But what has caused it? Whether it's the heat, whether it's the photon, whether it's the gamma ray, how has it occurred? Third question is, what is the mechanism of this happening? So the area in which we study how fast does A plus B react, that is rate of a chemical reaction, and what is the lifetime of this intermediate? Is it a short-lived intermediate? Does it stay for picosecond time scale or femtosecond time scale or the microsecond time scale? So look at this particular intermediate. So we want to answer this question, what is the lifetime of the intermediates and what is the identity of these new intermediates? So one would like to study them both at the spectral level to find out what is the structural identity, and also at the temporal level to look at find out their lifetimes of these particulars or the species, whether it's a picosecond to femtosecond. And this has become now possible very routinely, and I'm sure some of you might have heard me before giving more details of this particular area of the chemistry where you try to study reactions in the picosecond to femtoseconds in use of lasers, because lasers give you that handle to look at that on this guy. Okay, now let us see the next slide. So then we look at these excited states, whether they are excited states, whether singlet state, triplet state, whether they are free radicals, radical cations, radical anions. There's odd electron spectroscopy on carbon cations, carbon anions, even electron spectroscopy. This is a revision for all of you who have studied. I'm sure all of you have studied chemistry up to 12th standard. So all this was told at that time. Now what kind of energy input or release? That is called spectroscopy, that we put some light and then we find out some light coming out, that is fluorescence, and that is absorption. And this study of these comes under spectroscopy, and you have different kinds of spectroscopy like thermal energy, UV visible, infrared, microwave, and all these energies can be used to do chemistry, and also they are all connected as the end product of the whole chemistry. So monitor the time evolution of the identity of intermediates. That is, you take a snapshot to view the whole chemical reaction taking place in real time scale. That is, you take a video picture of a chemical reaction, just like we go on marriages and things like that, videos are made. You try to get a video of this chemical reaction taking place. At what time scale these things are happening? What time scale A is approaching to BC, and then B bond and C bond is breaking, and another form is forming. So if you can get the complete story of that, then we will know the chemistry, how it is happening, and how fast it is happening. But in today's lecture, I will not talk about that because that is, I have given many times different species looking at the various reactions in picosecond, femtosecond time scales. Today we'll ask another question: does chemistry change with the kind of energy input? That is, if you put heat, ultraviolet light, infrared light, etc. That is, you give the same amount of calories, same amount of energy, but given a different modes. Instead of translational mode, ultraviolet absorption, electronic band, or in the infrared absorption band. Same amount of energy, but different modes of that. If you excite, will the chemistry change? And that is the question, and that is what chemistry people dream all the time, that I should have a fantasy in which I would be able to break the bond, whatever bond I like, by putting energy into different modes. And that's what I said. The title of this talk is Breaking the Bonds at Will. That is, whichever bond is there, I would like to be able to break that. Can I preferentially make or break a particular bond in a molecule? And that has resulted in entirely new chemistry, so-called bond selective and mode selective chemistry. And this is the real dream for all of us, that power to do, not like this chemistry may normally, if you go to a lab, you will see they mix up the thing together, put it in a flask and go and heat it up with a Bunsen burner, go ahead outside, have some tea, and come back and analyze what has happened to this. But it will happen only certain ways for certain reactions, and that's what we are all asked to remember, and we cram up the whole chemical reaction, and that's why some people don't like chemistry, because they do not understand how the mechanism of the whole thing is, how it is happening. So if you want to see that, that's the real dream. The dream is still alive, as I say. Can I enhance the rate of a chemical reaction? Normally people put some catalyst inside the system. If you must have heard in chemistry that if you want to enhance the rate of energy, instead of 2 days, it may happen in 2 minutes, then you will use some catalyst. But catalyst means some third component of that chemical reaction you are adding, and that may give rise to different qualities. So can I use photons as the catalyst to do a chemical reaction? And photons can be from lasers, from ultraviolet light, visible of this kind. And if I use different kind of photons, will I get different kind of chemistry? This is an unbelievable thing. That is, how can you change the chemistry? Because everything happens with the bond dissociation energies, and bond dissociation energy will tell you which way the bond will break. So another question we can ask, can I enhance the rate of a chemical reaction? As I said, you are like a catalysis, but can I do without having any external compound except photons? So next slide. What really happens is the chemists shoot chemistry during the act. Atoms and molecules have an enormously complex sociology, and for centuries chemists have been trying to understand why they sometimes like each other and sometimes hate each other, just like in the human beings. This love and hate relationship is extremely important. It determines why some substances can exist and how they behave, and some other substances are unstable. And like humans, as I said, the only way to find out how they behave is to watch them in action. And that's what I say, you should have a video of a chemical reaction. If we know, then we will know how the reaction is taking place. Oops. Not moving. So normally all of you might have read this in your intermediate, that there is a potential energy curve, and there is this bond dissociation energy is given here. So unless and until you go up to that energy, reaction cannot take place. This is internuclear detents and potential energy and molecular vibrations. So this is where the making and breaking of the chemical bonds is explained in a simple physical chemistry class, if you will be going. And that will be shown here as reactants and going up the activated complex energy called, and delta E is the reaction free energy of that kind. So which without that, you cannot have a chemical reaction. So first you have to put energy to overcome this activation energy, and then finally products come out at a low energy time state. That's how we understand physical chemistry at that time. And this is given by famous Arrhenius equation, where if you heat the temperature more and more, the activation energy is put, and that's why the chemical reactions take place depending on the activation energy, which is E star, which is given here. This way you can calculate how much temperature required will be there. But however, of whatever you do this way, we cannot go against the lowest energy requirement channel. That means the diktat was the reaction will go through the lowest energy requirement channel, whichever is the weakest bond will break. And nothing can happen, highest bond will not break because the energy is not sufficient, so the lowest energy bond will break. So now comes the question, since the time of alchemy, chemists have been trying to probe the sluggish reactions by heating. That's what we know on thermal chemistry, it is collision-induced energy given to the center. Then came the input of energy through a visible or UV photons in well-defined excited states, that is spectroscopy, well-defined state like singlet state, triplet state, and then see the energy chemistry taking place, which it could be quite different than the thermal chemistry has been. And that's the field of photochemistry, which we all study well. But synthetic chemists still had to live with the idea the reaction is occurring predominantly via the lowest energy reaction channel. I'll explain to you by this simple example. Take up a case here of SF5Cl. There are two kinds of bond, sulfur and fluorine, and sulfur and chlorine. Now, you know the bond dissociation energy. You can go to a book and you can see sulfur fluorine is a stronger bond than sulfur chlorine. So what will you predict as a scientist? That if you heat this molecule, the chlorine bond will break sulfur and chlorine, and you should get compounds as SF5 dot plus chlorine dot. That is how the chemistry should take place. But lo and behold, and that was creating the excitement. Chemists have long been tantalized by the dream of altering the probabilities or choosing themselves the bond within a molecule to vibrate and break to order, whatever order I give. Chemists have been trying this to realize this, knowing all the while that it may be like Don Quixote's an impossible dream. But now they have a new mighty sword to use in their quest, one that was not available, let us say, 40 years ago or 30 years ago till the time recently. And that is the fast excitation by the infrared lasers. Normally up till now in photochemistry, we always using ultraviolet photochemistry, photons, because the energy requirement of ultraviolet was 3 to 9 electron volts, and bond dissociation energy is in the same region. But now this infrared photochemistry area has started giving a new chemistry, photochemistry in the electronic ground state. You are still in the electronic ground state, but you are doing a chemistry. And why it was not possible? Because I don't have to tell you in this center, which is based, all the laser work is being done here, but just for some students to know that why is the lasers requirement? Because they have some very unique properties of the lasers. They can be pulsed short time duration, keeping the high power as low as 6 femtosecond. 6 times 10 to the minus 15 seconds is routinely now being used in different laboratories, including our laboratories in Bombay and things like that. So that comes under the area of fast reaction kinetics, the time-resolved studies. In addition to that, the lasers are highly monochromatic of very high order. They can have 0.001 wave number monochromaticity or anything, nowadays even better. So that allows us to put energy into well-defined bonds, and that will give us the selectivity which is required in our photochemical studies. And that can also happen with having the very high intensity in the infrared. That means you will escape the black body limitation of the thermal sources which we normally use in infrared. So by this can be done. If this can be done, keeping the high intensity in the infrared so that we also get large amount of materials of availability, the photochemistry in the electronic ground state called is the infrared photochemistry. You can even change the polarization of the light, linearly polarized light, which can be easily converted into circularly polarized light, by passing through a quarter wave plate. Quartz, asymmetric photodestruction of asymmetric synthesis, photo resolution of metal complexes, and things like that. You have opened up a new areas of work. As you can see here, you all know this slide, that 1 kilowatt of xenon arc lamp gives rise to the photon flux of, let us say, 1.5 times 10 to the 6, 10 to the power 6 million, 1 million kilowatt back body. Like in sunlight, for example, you can get 1.5 times 10 to the power 10 photons. And if you just take, on the other hand, 1 milliwatt helium neon laser at this for wavelength, you will get 3.5 times 10 to the 13. That is higher, 1,000 times higher photon flux you can get at centimeter square per second. A small helium neon laser, which I am using here or anybody else. And if you just use a 100 kilowatt CW CO2 laser at 10.6 micron, you're already getting 6 times 10 to the 21 photon flux per centimeter square. And of course, all of you here use kilojoules of neodymium glass lasers. They're actually very high in photon flux. You can get 9 times 10 to the 25 or so, and that's why this can be used for fusion and things of this kind. So you can see, not only it can give very high photons, monochromatic photons, but at the same time enough photons so that you can produce the compound chemistry which you like in large quantities, not just 1 or 2 molecules to break, but you can produce grams, kilograms of the quantities depending on the number of molecules. Already you see here, it is 6 times 10 to the 21, which is almost Avogadro number, and if you 10 to the power 25 is 100 times more than the Avogadro number amount you can get. So that tremendously excited people and said, well, let's use the lasers for doing this kind of work. And that is the story of this whole today's lecture. And this started happening because of a very important accidental discovery. It always happens. That is, we, including we and some other people in Moscow and some places in America, Los Alamos particularly, were working with the SF6 molecules gas and using it for Q-switching from the CO2 laser at 10.6. So they put a cell in which there were 2 windows and filled with SF6 molecule and irradiating with the 10.6 carbon dioxide lasers to do some Q-switching work. But lo and behold, what they were finding, that their windows were getting very much fogged. And when they said there's a white deposit of the new material was deposited on the window, light was going from one window to another window. By the time it reaches another window, white precipitate was almost solid, was deposited. So they ran through their chemistry friends and I say, what happened? We started with SF6 and now we are getting entirely different solid particles. So for chemistry people, it's very easy to differentiate. Look at the mass spectrometry of sulfur hexafluoride. We started off and we're getting now sulfur tetrafluoride. That means SF bonds have been broken and fluorine has come out of that. But most interesting thing was, even apart from that, that you could do with the carbon dioxide laser, bond breaking, but the bond break only took place isotopically selective. Only you see sulfur 32 has 2 isotopes, 32 and 34. 32 has the highest number, 90% or so, and 4% is actually here sulfur 34. The amazing thing was that person who was doing this analysis, you could see isotope abundance, and he saw that sulfur 32 has not only decomposed, and sulfur 34 absolutely has no reaction. That remained as it is, no decomposition took place of sulfur tetrafluoride. So that was a big story at that time, published, and then they said, well, look, what has happened? How can you do a isotopically selective chemistry by using the lasers? And that brought not only, first thing what happened is the cost of the sulfur 34 isotopes tremendously went down in the market. Sulfur 34 isotope, when we were buying in the, let us say in 60s or not even 60s, I think in 70s, it was $1,000 per gram we used to buy that. And by this reaction, we could make them as $0.30 per gram. Because there was energy consumption was very less. It was only just carbon dioxide laser which was putting there. Normally, this sulfur 30 isotope requires very high energy separation by which you distill sulfur hexafluoride a million times again and again and again, and each time it increases by 0.001%. Again distill, again it will increase. normal method of isotope enrichment is, that's why it is so expensive. So this led us, all of us, to believe that there may be a new method of the isotope separation has now been discovered. But as a chemist, you will try wonders. So you'll say, what is this foolish thing you are telling? Because the chemistry, sulfur-fluorine bond is 90 kilocalories energy required to break this. An energy of a 10.6 micron, which is from photons, is only 2.86 kilocalories per mole. So that means approximately 30 infrared photons required to break the bond. How does this energy pulled up inside this molecule? 30 photons have been absorbed by this particular bond. Are we saying that Einstein was wrong because Einstein was saying that one photon gives rise to one particular reaction? No, but something else is happening and we have to try and see. And that led to this birth of new chemistry, which is called new concepts of multiphoton dissociation dynamics. And if you now look at this spectroscopically, it is quite easily to understand because sulfur 34, if you take the infrared spectrum of this mixture, which has 32.6 and 34, you will see two bands very clearly defined. One belongs to sulfur 34, another belongs to sulfur 32. And they are separated by each other by about 17 centimeter minus 1. And remember, our lasers can be tuned to very small, very monochromaticity to 0.01 wave numbers. So what really has happened in that experiment, where we were sitting only on the 32 isotope, right now the energy was absorbed only by this isotope and not touching at all because this is 17 centimeter minus 134. So all the energy was pulled up only in 32 SF6 because of the monochromaticity of lasers, and only one isotope decomposed, another isotope was not touched at all, and that gave rise to the isotope separation. Many people, skeptics, when we published papers, were saying, well, no, maybe something else is happening because you are having such a high power of carbon dioxide laser, maybe this is heating up the whole thing, and you are using lasers as a strong Bunsen burner. But then if that was the case, it will not be isotope selective. Otherwise, because heat will heat both 32 and 34. So that led to this new area of the whole thing of application of, now after that, it was applied to large number of different isotopes, lithium, beryllium, boron, carbon. Everywhere we could succeed to get into different isotope separation, and very cheap method compared to this because energetics were very useful to this. And you can see, compare this. Normal method of uranium isotope separation is gas separation of isotope uranium if you want to do. And you know why you want to do that. You must be reading or listening to the television. Iran has reached to 60% enrichment already. It may reach 70%, and 70% and above is extremely dangerous because then you can make atomic bomb for that. So people are very much worried on this whole thing. But energetics is so bad that means it requires so much amount of energy. It is considered as the most inefficient. It is considered as the most inefficient activity ever devised by human being. It requires 3 million electron volt of energy to separate one uranium atom from 235 to 236. Imagine how much energy you require to produce large amount of separated isotopes. Presently, 3 diffusion plants of separation of uranium isotopes in the United States cost $300 billion to build and maintain. Uranium-35 separation is $5 billion per year industry. In a single year, that's why in India or other poor countries cannot go into this uranium separation methods because there's such a high energy. You can see the order of magnitude is in a single year, it will consume as much electricity as the whole state of Minnesota, or you can say whole state of Tamil Nadu here from this right state. So much amount of energy is separated to have 3 MeV of uranium atom, or 6 Kalpakam plants for the 1 year. So then they opened up the whole idea that why not we use lasers to do that? It will be much cheaper. And as soon as the paper, this was published, everybody got into this effect. In the back of the envelope, they could do the simple calculation that if you take the molecule and put them into certain temperature and certain pressure, this is the assumption of that. You can see assumed density of this, etc. by this method. Time required to produce 20 kilograms of 90% enriched uranium-234. Remember that, 20 kilogram of 90%, that means 5 bombs, atom bombs are required for the 5 bombs of this one will be. It will be in 60 days you can produce in your garage. And if you do molecular approach, which so far we have been using it at this time, and they will take only 3.5 days to produce 20 kilogram. This is a simple calculation you can do on a basic paper. And as soon as this paper was published, everything became underground. That is, nobody published after that any work because thinking and it is a very dangerous business to work in this area because all countries will have isotope separation on making bombs. But let us forget for the time being about the sensitivity and also about the dangerous nature of this business. Look at the chemistry. What is happening? Why is it happening? It can happen, or how could it happen? The reason for that is simple. Thermal chemistry, when we heat compounds, is an equilibrium process, while laser chemistry is a non-equilibrium process because it goes in one direction. Advent of infrared laser made possible infrared multiphoton dissociation, vibration energy region divided roughly into 3 regions, low energy discrete region, etc., high energy quasi-continuum. So the molecule absorption spectrum, potential energy curve will look like this. And this is where the 2 isotopes are separated by certain amount of isotope shifts. So gradually when you go up, you will see these distances are becoming like a continuum. So initially if you put the selectivity in this level, after that it just breaks down on this whole affair. High energy quasi-continuum is a stepwise excitation, fluence important. And true continuum, both laser intensity and fluence are important. 10 to 40 photons are needed for the dissociation of this kind, but 10 to 40 photon is very cheap compared to infrared laser business. So it became a very exciting topic to learn, not only as isotope separation business, we will leave it at present at this stage, but what is the chemistry? What is the new chemistry we can do with this whole business? How it will be explained, very large famous scientists like Bloombergen, Martin Quirk, Joshua Jortner from Israel, put their brain and try to see how this whole thing is happening. There are initially energy is going into different systems here and isotope selectivity is measured, and then resonant absorption takes place in broad bands, and by the time a molecule like UF6 or SF6 is there, which has got high energy densities or vibrational motions, so mixing with other vibrational motors, molecule dissociates here. But only that molecule will dissociate which has been excited by the particular laser line. This is one of the theories, but there are many other theories, and many of you who are interested in the theoretical work are invited to take up this project because still people do not know how this happened as such of this kind. But it does happen, it can be reproduced. So a new chemistry is this, that SF5Cl, which I told you some time back, if you take these bonds, so now put energy directly, instead of heating it, you put from the CO2 laser 947.2 centimeter minus 1 and stretch only sulfur fluorine bond. Oops, sorry. And all other bonds are remaining untouched. And this you have to do very fast, and you have to do that before the vibration energy transfer randomizes the energy absorption. So that's why two things are required now. You require a laser beam, which is very monochromatic, to absorb in sulfur fluorine and not touch sulfur chlorine absorption. And you should do it fast enough so that randomization does not take place. So you can produce different kind of thing, SF4 Cl fluorine or SF5 plus Cl, whatever you want to do, depending on your energetics. So that started talking of bond selective chemistry and a mode selective chemistry, which mode you are putting the energy. So different kind of things, results will come. And that, of course, opened up the whole area by putting this energy from the lasers. Well, okay. For example, you take this, this has come from Basov's laboratory in Russia. He showed this molecule, tetrafluoronitrazine, for example, here, and he heated for 1300 degrees centigrade. 2NF2 radical came as the product, and no reaction took place with NO. But if in the case he heated with a or irradiated with the H 943 centimeter minus 1, only absorption by nitrogen fluorine bond. So only that bond stretches and that bond breaks, and you get a different altogether chemistry than what you had here. Here your 2 NF2 radicals, here FNO and N2F3 radicals are produced. So what have you done? Just look at the energetics. You have not broken a 20 kilocalories per mole, which is the weakest bond in this molecule, but you are, by putting the energy specifically in a particular vibrational mode, you have been able to break nitrogen and fluorine bond, not saving the nitrogen-nitrogen bond. If you had done this by heating, nitrogen-nitrogen bond would have broken. But by this technique, because the activation energy is lowest of N things, you do that. So like that, lots of experiments were done, and Basov's laboratories, different our laboratories, so many people, different laboratories they did, and look for some very specific chemical reactions which we can do entirely differently. So motivation was more than 50 different infrared laser-induced chemical reactions have been studied. However, it is preferable to choose reactions where the reaction products could even be qualitatively different from what we get from the thermal or electronic photochemistry. And that gives rise to a different area altogether. This was a work of one of the graduate student, very good student whom I get. He said, sir, can we do this experiment? I said, what? He said, retro-Diels-Alder reaction is a very well-known reaction which, according to the symmetry rules, is allowed only in the ground electronic state and not in the excited electronic state. So it created the possibility of carrying out reactions obeying symmetry selection rules of thermal reactions and having thermodynamic properties of the photochemical reactions. And that opened this area of the infrared laser chemistry. And I can give examples of them, but it doesn't matter. See, for example, you take these molecules. We have done this, all this published work now. DFCH, you will get this product. If you heat this, you get these products. If you ultraviolet light, you put these products, perfluorinated compound. If you take infrared laser on the same compound, see, the same compound we are irradiating by different source of light or sort of different source of energy. And now you get entirely different molecules, hexafluorocyclodiene and hexafluorobutadiene. So you can get now, clearly you can see that the energy input means something to give a different chemistry altogether, which you could not have imagined that the lowest bond should break. To look at this, just like a scientist or graduate students who are working, they will say, if that is the case, the referee said, let us look at the spectroscopic evidence. And then we put this photo arrangement of flash photolysis. Basically, instead of using light there, we used TCO2 laser and flashed it on a sample. So this is the sample here. And do the spectroscopy of that and see what is the transient species coming out. And this, of course, you see that, which is exactly what we predicted, HFBD, which is a vibrational excited state, and the spectrum is given by Hertzberg in his optical book that this is how this molecule should look. So we could justify, now if he's a graduate student, he would like to do his PhD, he would like to get some more, many graphs, so by which you can see the formation curves, how much time it takes to form that particular identity, how much time it forms the decay of that. So the chemistry of that, for example, started from here in 1 microseconds or so, this particular vibration state produced, and this kind of the product comes into this. Like that. So this is why I can answer now this question is, IR laser photochemistry produce different chemistry. Retro-Diels-Alder reaction produce this, and IR laser chemistry produce this, and UV photochemistry produces a different chemistry altogether, different kind. Then we became more courageous. We started looking at different molecules, and all the molecules showed this different species by different energies. But not only that, sometimes we could get even the bond selective chemistry. If you do which bond you are putting the energy, you will get a different product. For example, here, in the new 5 mode of infrared 980 centimeter minus 1, you get this particular product, while on this case, 1042 wave number CO2 rock frequency, you get an entirely different frag. So see how wonderful it is. 980, you're just grating, you're just tuning slightly. 980 to 1042 is not even enough energy. But because the absorption is shifted into a different bond and different skeleton, you get a different chemistry altogether, just by simply put. So it gives you, a scientist, tremendous power to look at the chemistry and change the chemistry in the way he likes to do and in the way he wants the chemical to break. And it has tremendous applications, for example, in the waste disposal in the chemical industry. Waste disposal is because there is some extra things are being produced. If you take some dye or something like that, which are spoiling water in the different places, or in the Gangas where there is so much amount of dirt is there. So now if you know that what molecule is bad and what molecule is good, what you should do, you can decompose in the different modes of the compound making of this kind. You can get, if you want to do PhD, these are the original graph from his thesis, so you can see all this bad looking thing rather than more smooth looking thing definition slides. You can get decay, you can get formation, you can do all rate constant, you can measure. So you can see if this is, for example, it can break this molecule. If you look at the chemistry, you will see it can break either this way or it can break concerted mechanism, all of them together. So you can do this kind of reactions and you can monitor which way the chemical reaction take place. This is another example which is very popular in the literature is CF2Cl2, the refrigerant which you put in our refrigerator. If you put the CO2 laser, it can either break this way or it can break this way, 8% of that. And if you turn the frequency differently, you will break it in a different manner to what you want. That's what the chemist is really looking for. The laser is giving fantastic power to the lasers, to the person, what you want to do. That is, laser-induced isomerization you can do. Wavelength and mode selective products are observed. Role of collisions are excited. For example, in this case, you see how just this asymmetric stretch, if you heat, you get this way, this is the product. And if you take in wagging frequency of 1031, you get a different product. And with this product is the same when you do the heat. For example, if you take molecule this and heat it up, you will get this product. And this was, so he showed Calder from Exxon that all different kind of the chemistry you can change by changing the frequency of input of the energy. Another molecule which is tuning the wavelength selects the product. If you take 3 different kind of lasers, laser 1 which will absorb in the frequency of that, laser 3 which will absorb boron and hydrogen, for example here in this absorption mode, or in the bending mode between bearing casing. Every time if you take 1, 2, 3 different kind of frequencies, different products are coming up here in this whole thing. So that you are actually breaking the bonds to your order, that I want this should break, that should break, not above break. And irrespective of the lowest energy channel, I hope I have been able to convince that to you. Yeah, this slide I want to show you because I was presenting that at a Gordon conference in New Hampshire. And as you know, Gordon conferences are prestigious conferences and many people, very selected people, 100 and so, are selected to attend that. And when I showed this slide, I said, look, we take ethyl vinyl ether and we do the photon with carbon dioxide. With the same amount of energy, fluence is the same, but we are getting different products in the sense, sorry. Yeah, if you have the lasers of one frequency which has a pulse width of the, here I am going to show you another factor that is same fluence now from the laser, same frequency even, but you just take the pulse width of the laser, you get a different processing. If you take a pulse width of picosecond and you hit 100 nanosecond, you get a different product. And why I remember this and show it to everybody else, because when I was talking to this, Bloomberg got up and he said, Jay, look, you are showing the product to be this. And I am getting the product like this, which is entirely different product. I was almost getting, my pants were getting worried, okay, what to happening now? They're doing mistake. But he was very kind. He said, no, Jay, what is happening is simply is a question of pulse width. In case of your lasers, you are having 1000 nanosecond pulse width and randomization has taken place and you've got this product. While in my case, when you have a 20 picosecond pulse, the randomization has been stopped, so you get a different product altogether. So that led to the basic mechanism of that. the lack of intramolecular energy randomization requires during the laser up-pumping process. That is, if you want to do it regular, in a large scale, you have to make sure that intramolecular energy randomization does not take place. So you must measure the energy by which required, or time scale which is required intramolecular randomization. So bond-specific chemistry can be done. So no longer synthetic organic chemist will have to resign to lowest energy channel. And that is the message which I wanted to give you, that with the lasers, you will be able to do a different kind of chemistry altogether. Oops. All right. Okay, we can skip this. I think time is running out. So I have shown here that you can do different kinds of path A, path B, depending on this. In this case, earlier cases, we had done the time differences, 100,000 picoseconds, 65. Here you see, you can also change the joule, that is the total amount of energy per square centimeter, fluence or something, what you call. So if you use 0.1 to 1 joule per centimeter square, you get this product. If you use 2.5 joules per square centimeter, you get an entirely different product giving rise to molecular fluorescence. And if you take path C, which we are doing 10 joules per square centimeter, then you get complete decomposition of the molecules and swap bands of the spectroscopically cleared thing. So you have all the three properties we have shown you example by changing the frequency, by changing the energy, changing the time scale of pulse width, can differ. All the three properties of the lasers can give you different kind of chemistry what you want to do. And that's what I want to prove in this lecture, that the molecules chemistry, in which direction it goes, is in our hand. We can do, these lasers allow us to do what chemistry we want. You can also do rate enhancement. I think there is a rate, and without any catalyst. You just make photons. For example, this case has been done by Brooks and Kasper at Rice University. He took potassium plus hydrochloric acid, which HCl laser. So this particular HCl got excited into nu 0 to nu 1, and you get KCl plus H. And the rate was 100 times faster than if the same amount of energy was given in the translational mode. If you heat it up and do it in translation energy, 100 times slower reaction. In Max Planck Institute, my friend Jürgen Wolfram at Heidelberg showed a fantastic reaction here. For example, not only he got isotope selectivity, but the rate enhancement was fantastic. Look at this reaction here, which is giving HCl35 isotope. Chlorine has two isotopes, 35 and 37. He took isotope HCl and reacted with the bromine atom. And bromine replaced the HBr and chlorine 35. And as to a chemist who knows all the energy at his fingertips can say that this is an impossible reaction, because energetically it is not possible at all. But look at this now. That means this reaction, which is an impossible reaction, bromine cannot replace chlorine. Normally chlorine will replace the bromine. So the change of this reaction rate increased by 10 to the power 11. Can you believe 10 to the power 11 times the rate has become faster? That's why he got chlorine 35 as the isotope, as the product. He could measure that. So the selective, this is really the dream come true, where you can increase the reaction of a rate 10 to the power 11 times. You know, 10 to the power 11 times, what does it mean? That is a picosecond time. So short time in scale, you can put the reaction going. And this has a tremendous implication in the chemical industry. And I will show you some industry who work on these principles. Selective stimulation of endoenergy can exchange reactions, and reaction is isotope specific. Reaction rate is enhanced by a factor of 10 to the 11 by input of energy in vibration mode with the help of the lasers. You can now do separation of rare earths from the radioactive waste without further addition of any chemicals. Direct relevance to separation of nuclear waste disposal or making it harmless, and that was called, that's why we used to call it as laser alchemy. Just like people are saying you can change gold into mercury, mercury into gold and things like that. You can do entirely good, nice things of exactly that kind. Very soon gamma ray lasers will be available, and I think right now they are available. Hopefully restructuring the nucleus of an atom could be done, leading to laser alchemy. Standard. Now I will show you, can you make money by doing all this? What is this whole thing entirely business teaching? Can you make money out of this? Now young people want to make money. Ultra purification of silane, which is required for silicon nowadays, all the time silicon is in talking terms because you need silicon chips. Now silicon has some impurities like arsine, phosphine, etc., and they can decrease the power of the silicon purity. So by the conventional process, if they want to pure by distillation of that, you require very large input of energy. But in the lasers, if you use, because once you can isotope separate, you can separate these two chemicals from this very easy. It is like left hand, job of a left hand of a chemist. When you tune the energy into this, this will decompose, tune the energy into this will decompose, and this will remain pure. At 1 ppm impurity, 1 gram impurity, and 1 ton of a food stock, you can prepare. It destroys the impurity without affecting the bulk. This is in contrast to the conventional methods where entire gas stream has to be passed again and again and again like chemical engineering people do for a projected goal of 1,000 tons per year silicon. 400 watt average power laser is required. Very, very easy to make argon fluoride. And right now IBM has this company working with a capital cost of 0.7 kilograms per silane, operating cost of 0.5 cents per kilogram. So $1.2 per kilogram of silane, which is very, very cheap compared to the normal method of silicon. And that 10 to the power 4 times cheaper than the what process right now is working. Since simple chemistry, since photons react here with the laser primarily on the impurity species which are in minute quantities, so significant economic leverage compared to any conventional purification process of chemical engineering, distilling again and again, where entire bulk has to be processed again and again, particularly when the impurity content is very, very low, let us say 1 ppm. So 1 gram of material must be removed to process 1 ton of the feedstock, and the photon economy is there. So presently photons of made to order colors are available. I'm sure your cat can give you any photons of what kind if you want. Removal of highly toxic dioxin, which is always in the now product in your news, because the plastics, when you decompose them, they give you a very dangerous compound dioxin in a commercial dye-filled plant in DuPont. And DuPont, because this is a cost here is inconsequential, and DuPont has a big plant working or removing this. You take silane, you take photons, you come to silicon, and you can take the ammonia, you react silicon nitride, you take ethylene, you can produce carbide. Depending on what metallurgists want, it is a very simple process to do this, and chemical reactions will take place. And at present, for example, there is a 15 megawatt CO2 laser at this point synthesized powder, and powder is produced very fine single type of a nanometer pi size distribution, 50 to 100 nanometer, very fine and uniform. A joint venture production of plant running at production rate of 7 kilograms per hour, 50 tons per year. And that's why I showed you some early slide in which I can say Avogadro amount of materials can be produced, not just a gas phase just emitting few molecules. Large amount of molecules can be done at a cost of $5 per kilogram, which is very, very cheap. And that's why the whole plant is working now. So in the end, I would like to say, we may now dream of orchestrated trains of accelerators, which are here available, synchrotrons and laser pulses appropriately located at the CAT, which prepare reactants to our highly specific specifications and will monitor all intermediates in direct time domain and probe all nascent products and their final conditions with complete specificity. It is perhaps too early to speculate, but it seems that for the first time, we are on the threshold of being able to probe specific steps of a chemical reaction on the potential energy surface and take a video picture of a chemical reaction. Truly, a dream come true for a chemist with the help of lasers. And thank you, all of you who have been giving us all the help in lasers. Without this, nothing could have happened. And I think next slide again says, Edward Teller, all of you know, person who was considered father of hydrogen bomb when he was shown this result. He said, put it, laser chemistry can be linked to a chemist reaching into the molecular structure of a compound with his own hands and fingers, rearranging the structure at will. Chemistry is undergoing a laser revolution. Type of intellectual ferment in the chemistry, picosecond, femtosecond chemical kinetics, state-to-state chemistry study, implications of these is staggering. Newer compound, new rate enhancement, exotic materials with unusual properties we are making. So dear friends, future is in the hand of using lasers for chemical reactions to do rather than heating up everything in the test tubes. So now chemistry you will do like this. You take a laser beam, tune the wavelengths and take the bonds whichever you like, break and have a different kind of chemistry rather than test tubes and things like that. So this is the new chemistry going to be. And in this is my thanking slide to all my friends, students and friends who have helped us to do all this kind of work. Jyoti Subaya, who now is doing postdoc at Stanford Laboratory, who did all the SF6, UF6 work, Cesar Sarkar, who was at Columbia and now he has come back, and KVS Ramarao from University of Notre Dame. All of them have helped us. P.K. Chaudhary, who is University of Heidelberg, who did the DFFC, OFFC, PFP work. Parthasarthi, who is in Lausanne, Switzerland, CF3CL, carbon-13 enrichment. Karve, who did in Moscow this work of deuterium and tritium separations. Watsa in Heidelberg. Chakravarti, volatile uranium compounds in case of uranium separation of this kind. And of course, nothing would have been possible without Dr. D.D. Bhavalkar. I must pay tribute to him and salute him for the wonderful center he had made here, initiated, thought, conceived of a place where we can indigenously make our lasers. We don't have to depend on other outsiders. Let them put whatever kind of things they want, not to give us this. There was a time when they were stopped giving us even optical windows of 1 centimeter, 2 centimeter. So we built our own laser windows by Dr. Bhavalkar's help. So he was completely, all the deserves, all the thanks for that, for not only lasers, but also data acquisition system. And of course, lots of money with respect to Bhabha Atomic Research Center, who gave us the freedom to do this kind of work, which was looking so crazy. And at one time when chemistry used to get something like 1,000 rupees, that's all, the whole grant. And when I asked for some large amount of money, Dr. Ramana said, Rick, what is this? Chemistry people only use test tubes and lasers, why, test tubes and beakers, why do you want so much amount of money? Then I told him, sir, you come to us and I will give you a seminar for about 2 hours and you listen to us. So we had a special meeting on Trivandrum on this for the business. What can be done by the chemist if you give them the money? How total amount of some money we said offered. And he stayed. He said, I will stay for 3 days with your seminar. There was a very famous symposium in Trivandrum ISRO Center, which I organized, and Dr. Ramana was present through all the 3 days. And he understood that what the chemist can do if you give them material money, because these things cost money of that, it's not test tubes and things like that. And after that, I must admit openly, he never said no to any money which I have asked. In the BRC, whatever the money required, I will go to him saying, sir, this is the money required. He will go to Trombay Council, various committees and all. He will say, I have heard Jay Mittal giving a speech, give him the money. So if you are confident of the kind of thing which you would like to do, which you think you can do, I think the money is not a problem at all. Any management will give money, only you have to make them feel that, yes, you are not cheating anybody, you are telling the truth. You want to do that, you are very passionate about what you want to do. Then any management, good management will try to support all this I particularly want to say to young student and other people who are sitting here, that money has never been a problem in India. Even now, I would say, even though we had difficult days, etc., but we managed to go through that, and now we are competing in the whole world, and we can do same work. And actually, other people now are jealous of us because they say we have such a large population, we are making a big army of scientists here. One conference we were arranging, and he told Dr. Ramana, "Arey, Dr. Ramana, you have a big army of scientists. How can we compete with you?" This was said by head of the Argonne National Laboratory, saying that we have very few scientists, and that too, half of them are from India. So how can we compete with them? So I think have hopes, and I think India will be on the top after some time. All of you put your hard work. Thank you very much.
Thank you, sir. Thank you very much for such a wonderful evening lecture, I would say, and going down the memory lane and also underlining the importance of lasers and what is the relation of lasers and chemistry, the way you have seen it and all the world has seen it. So very, very, it is a real honor for us to have you here, and it is I don't think that any of the persons sitting over here has heard you before. So it is really they're really fortunate to have this to hear your talk here. So thank you very much, sir, once again.
Thank you so much. Any questions you have? Anybody has any questions? I am ready to tell. Any questions?
Yes.
Please ask. Without questions, lectures are not good.
Sir, I feel fortunate that in my lifespan I could attend such a talk, and just I want to, if you can comment, because for selective bond chemistry, one way of doing is you tune the laser so that it resonates with particular bond,
Yes.
and you can selectively
Frequency.
break the bond. And because because I have read information in bits and pieces, and this has covered everything in the talk. So now people are talking about using ultra short pulses or femtosecond pulses. With that you can map the excited state of the
Yes.
molecule, and you can do the coherent control before IVR comes into
That's
the
right.
picture. And
That's
people
why I
can-
showed one slide that the IVR is the crux of the matter. You must measure that IVR.
Yes.
In some cases which I have shown, it was fortunate that the IVR was helping us. But in all the cases it may not help, because when sometimes some organic chemistry people say that, oh, this compound I can do. And yes, you can do, but we have to measure some things. So IVR you must understand. And for that, second hand of my works, that is for fast reaction kinetics. You must know the energy flow in the molecule. You have put energy into one point. Does it go from here to some other bond? If that happens, you have lost the game. So you must know it will happen eventually, but how much is the time scale which takes for the energy to flow from one place where it was initially deposited to finally where it is standing. So if you can beat that time scale with your laser beam, then you have made it. Otherwise, you will lose the game. Correct?
Thank you very much, sir, once again,
Yeah,
for a
thank
very
you
wonderful
very much
talk.
for understanding. Very good question.
Thank you, Mithil sir, for the beautiful talk. So I was just wondering, like, this ties very beautifully with the Fermi's golden rule, like all of these things which you have explained. So like shining a laser on a particular structure, it perturbs the electron density locally.
Yeah.
And that also alters the wave functions in certain ways.
Yeah, absolutely.
And certain pathways which were not possible before have been altered, and the densities and the density of states have been modified, and overall rate probabilities have been enhanced, which were not possible before.
Yeah.
So along the same line, the intermediate states which are forming, which are not stable, which are just an intermediate part of the reaction, can they be stabilized using lasers? And can their lifetime be enhanced?
But the question, why do you want to stabilize? Number one question is to monitor what it is.
Yes.
To know what it is and whether it will stay for how long. So that can be done very easily by looking at the femtosecond chemistry, or now attosecond chemistry also. You can see what is the lifetime of this intermediate, whether it is a picosecond, attosecond, femtosecond, and can I now keep it as it is so that the reaction rate will be faster than the life of this. So this is a question of only competition between reaction rate A plus B versus the time scale required. So one has to play this game, that is you measure the intramolecular vibration and then tune your laser in such a manner that you do it within that time scale. It is possible to do that, and that's the challenge of all of you. Younger people should measure as many things as possible. Yeah?
Okay, sir.
Any further questions, please, from the back side? No. Okay, all of you are getting hungry now. I think it's okay.
Thank you once again, sir, for taking questions and explaining them.
Thank you so much for inviting me.
It's our honor, sir. Sorry, sir.
Thank you, sir, for your gracious presence. Now, this is the end of this today's program. Now, we should move forward for the dinner at the Sunrise Hotel. Bosses are waiting outside. Thank you.